Discrete mathematics is the language of computer science. One needs to be fluent in it in order to be able to work in fields like data science, machine learning, software engineering, and others.
To help you to learn this language and to make the learning process as enjoyable as possible, we use a try this before we explain everything approach. You will be solving many interactive puzzles that were specifically designed for this specialization.
Their main goal is not only to visualize the important ideas in discrete mathematics, but also to help you to invent these ideas yourself. We look forward to seeing you in our specialization.
Hello, this is the first part of our discrete math course, and this part is about proofs in general. And you probably will be surprised why we so care about proofs. You know, mathematicians are crazy about them, but programmers, why do they need proofs? If you write a video game or a search engine, probably you would not try to prove its correctness. Still, if you are interested in some more complicated system, not more complicated, but different types of system, like operating system or cryptographic protocol, to prove that this operating system will not stop or at some point, or cryptographic protocol is safe, it's something worth proving indeed. And main reason why people don't like proof is they don't understand what it is actually. So they think that proof something boring, long, meaningless, you need to learn them to reproduce them during the exam, but it's kind of nonsense. But it's just a bad understanding. Proof is not like this. Proof is an argument that should be convincing, really convincing for you. And it's so convincing for you that you are even ready to convince others using the same argument. This is what is a proof. In a real life and in mathematics, the tools are different, but still the proof is something like this. And to get such a proof, you need to understand the problem. So this is why the proofs are important. And last but not least, they are funny. And these are course objectives. So we want to learn how to understand proof, how to invent proof, how to explain proof, and how to enjoy proof. This is most important thing. And we don't assume anything. No, you should know what are numbers, or some common sense is also needed. But no special things except for a curiosity. If you give a puzzle, you should immediately stop and think about this puzzle before not wait until we provide the solution, but just think immediately whether it's true or not, or what is the solution, and so on. Then it will be much better. You will much better understand our explanation later. And let me tell you a story. There was a Hungarian mathematician, Paul Erdős, very famous one. And he used to say that mathematicians should not, it's not important whether they believe in God or not, but they should believe, what they should really believe is the book, that God has a book that contains all the proofs, for each statement contains the best possible proof, clear, nice, and funny. And you see that some people even try to write a draft of such a book, and this draft is rather popular. You see it's 5th edition, so many people enjoy it. This book is probably more difficult. There are more difficult proofs than in our course, but still, if you see it, you can try, and many of them are easy. And let's start with a puzzle. So it's very easy puzzle. Probably you will wonder why we ask this. But starting slowly. So can a chessboard, here is the chessboard 8 × 8, can it be tiled by domino tiles? Domino tile is a rectangle 1 × 2, and you can try to put them somehow. They should not overlap, and there should be no empty space. That's what is required. So can you do it or not? So the answer is positive. Actually, you can do this, and probably you know how to do this, but let's show it anyway. We want to prove that the chessboard can be tiled with no overlaps, no empty space by dominoes. So how do we do this? Obviously, actually. You just try like this and you are done, no problem. And this is not the only possibility. You can do many of them. Here are some more strange one, but why not? And you don't need many of them for the proof. One is enough, but still there are many. And now let's consider something more difficult. Can we tile this board? So this is a board without one square. Can we tile it? Okay, let's try. And that's probably the first thing when you see some puzzle. It's just to try to get an idea of what is happening. So click, 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 click. Now things are more interesting. Oops, one cell is not covered. Okay, maybe we did something in a wrong order. Let's try a different way. Click, 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 click. Now things are more dangerous. And okay, one cell is not tiled. So where we are. So we did not find a tiling. But also, what is worse, we did not prove that such a tiling is impossible. So we are in a bad shape now, and we need to recover. So can we do one of these two proofs? Can you do this one of these two proofs? No, this tiling is impossible, and we will see this impossibility proof now. Probably you already know it, but still we want to move slowly. So question is, can we tile this board? And the answer is negative. One cell will always remain untiled. Because of what? Because just the number is bad. So we have 63 cells. The entire board is 64, and one cell is missing, so there are 63. And 63 is an odd number. It's not divisible by 2. So we can use 31 tiles to cover 62 cells, but one remains. And if we use 32 tiles, then it's too much. Doesn't work. So our goal is not achievable. We proved that it's not possible. This is our impossibility proof. And now more complicated things. Imagine we have two corners cut. There are now 62 cells. And so we can use 31 tiles. Why not? So the tiling is possible. Okay, if you believe me, just think more, and let's try how it works. Let's see. We prepared some attempts. Okay, so click, 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 hop, 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 hop. Things become more interesting. Yeah, you see that two cells are left, and there are two of them. It's good, but they are in the wrong position, so we cannot use a tile to cover them. Okay, so let's try again. If it doesn't work, maybe we did something wrong. Let's try another attempt. Click, 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 click. Hop, 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 hop. Oops! Again, two cells are not covered. They are now in a different position, but still we cannot cover by one tile. So what? Should we try harder? Maybe there are zillions of possibilities, so why maybe some other will work? Or it's impossible? This indeed is impossible. So let's see why it's impossible. It's our second impossibility proof. It's a bit more complicated than the first one, but not that complicated. So the question is, can we tile this board? And the answer is negative, and there is a reason for that. So stop now if you don't want to see the spoiler, and I'll show it now. So this is the chessboard coloring. So you know that the chessboard has black and white cells, and we have two corners and we deleted, they are both black. And why this is important? Because originally we have 64 cells and 32 of them were black and 32 white. They were just 4 in each, black and 4 white in each row and in each column. So now we have, if you use a tile, we use always one black cell and one white cell. So if we have an equal number, we have 32 white and only 30 black. So 2 whites will remain because they don't have pairs, black pairs. So it's impossible to cover the board. So let's make the serious, explain it like mathematicians seriously, pretend that we are serious mathematicians. So a theorem, a chessboard 8 times 8 without 2 opposite corners cannot be tiled by dominoes 1 times 2. Why? The proof. First, we note that in a coloring we have black and white cells, and in each row and each column we have 4 black and 4 white. So the total number we can count the total number of cells. And opposite corners are black. They can be also white, but let's consider the case when they are black. And then we have 30 black and 32 white cells. And these numbers are different. Each domino has 2 different colors, so it covers 1 black and 1 white. And there is no chance that we cover everything. At least 2 white should remain. And like mathematicians say, quod erat demonstrandum. It's Latin saying, which means that that's what we wanted to prove. So this is the proof. Now let's see what we can learn from these examples. So I hope that you are now convinced that indeed we cannot tile the board. The proof can be really convincing, hopefully. And there are many questions we can ask after that. Imagine we cut two corners, but they are not opposite corners, but corners on one side. Can we tile the rest? They are actually of different colors, so this is, the obstacle doesn't exist. Can we tile the rest? Or imagine we just cut any 2 cells of different colors. Is it always possible to tile the rest? And I will not tell you the solution, but I will just show you some picture which contains some idea. So this picture is a bit strange, but still it's like this. So why the snake, so there is a snake going like this. So why this snake? What is the connection of the snake with our problem? So we cut 2 cells of different colors, black and white, and we want to tile the rest with the dominoes. How the snake can help us? Do you see this? Now we return to the simplest kind of proof, which is called existence proof. And this is the case when one example is enough. So if somebody sends you somewhere for a unicorn, they should explain you how this unicorn looks like. Otherwise, you will not recognize it even if you see it. So the same with proofs. If somebody wants you to find a proof, first you should understand what does the proof looks like. So, and of course it depends on what you want to prove. So we are now considering something which is called existential statement. The claim is that an object with given properties exists. So this is the claim, and to prove this claim, it's enough to show an example. And what is important is one example is enough. If you found an example, that's all. Now, of course, you should check that it's really an example, that the properties are true, but still one example is enough. And let's see how it works on some simple geometric problem. So this problem is about cutting things into congruent pieces. So congruent is just a mathematical word which means very simple thing. It's just the pieces of the same shape and the same size. So they can be in any place, you can rotate them, you can move them, but the shape and size should be the same. And the task is to cut this figure this figure made of 3 squares, then this figure should be cut into 2 congruent pieces. Again, probably you see how to do this immediately because the figure is symmetric. There is some axis of symmetry like this. So you can cut along this axis and you get 2 symmetric things. So we should have a prepared slide for this, yeah. So these are 2 parts. This is part 1 and part 2, and they are congruent because you can reflect 1 and make it like 2. Okay, more. If you asked to cut this figure into 3 congruent pieces, this is even more trivial because they are just 3 squares. But what is interesting is to cut into 4 pieces. Can you cut this figure into 4 congruent pieces? So what do you think? And I can tell you some hint. The hint is that these pieces should be also of the same L shape but smaller. So if you need 4 pieces, then each of them has area divided by 4. So it should be twice smaller in both directions. And so think like this. So you should cut the big L shape into 4 pieces of the same shape but smaller. So this is the last chance to invent the cutting yourself. I will show it. And here it is. Yeah. So you see these pieces 1, 2, 3, 4, and they are all congruent. So we are done. We don't need any other example. Actually, I think it doesn't exist, but okay. Now a more interesting puzzle, I guess, a more difficult one. Again, you should split, but now you should split an octagon. So here is this octagon. Yeah, here. And you should split it into congruent parts. Now, if you look at the picture, it may at first look difficult, but still there is an easy solution. And actually, the solution is easier because the cutting line goes along the grid line. So you don't need to cut something strange. You just follow the grid line and you can cut into 2 congruent pieces. Can you see this? So this is the goal. And here is the solution. So stop now if you want to think. And here it is. So you see that these 2 pieces, 1 and 2, are congruent, and then can be, if you move the piece 1 by 2 units to the right, it just fits into piece 2 perfectly. And now you can think about other problem. For example, you can try to cut this into 3 congruent pieces. And it's also possible, and maybe you already see it, but if not, just think about this a bit. Now we switch to some example from the real life. Sometimes indeed, if in the real life you could be interested in constructing something which looks strange and impossible at first, looks impossible at first, but then you show this and this is funny. So that's one of the construction. It's called Tensegrity. It's a special artificial word. It's made of tension and integrity. So what is Tensegrity? So imagine you have a lot of thread and you have some drinking straws. Actually, you need only 3, as it shown here. And your goal is to create some solid construction where these straws do not touch each other, but they are just connected by these threads. You can connect some points there. And what you should not do like this. You cannot tie them together. You should only they should be on some distance, and only you should have this thread. So at first it looks impossible, but it's not so. So now we will try to make a tensegrity with some things which we have here. So the idea is that, let me try to explain you. We take 3 things which are somehow like this. And then the endpoints form something like a vertices of an octahedron. if they all go through one point, it will be an exact octahedron. But now it's kind of approximation. And the idea is that we connect all of them by our thread. So I prepared some kind of needle to make it easier. So, but for that we need some things to keep in a correct position, to make holes and so on. So this is for making fixed position. Okay, so the first thing we should make hole in the potato to fix them. Okay, so let me try. Okay, so this is our first stage. Now they are fixed, but now the plan is to connect all the things with a rope, and for that we need to make holes with a special device and the candle. We'll try to make holes. Actually, I don't know whether it will work or not, because I never tried it seriously in this way, but let's hope. So, holes. So it seems we have all the holes are done, and actually each vertex would be connected to 4 others. So there are 2 threads going, so we need 4 holes, and we made them, hopefully. Okay, so now we should balance things more or less to make it symmetric as much as possible, and then we try to make this with a thread. So let's see whether it goes through. Okay, more or less. Not completely. Okay, we need a lot of time. So our next stage is just connecting vertices together. Let me try. Actually, there is a mathematical question. So each vertex is connected to 4 others, and we need to make it is a kind of graph, and we need to make a path in a graph which visits goes through all the edges. It's called Eulian path. So, and we will know later why it exists, but now it's enough that it exists. So that's what we achieved, and it seems more or less okay, but the question is whether what is holding them together, this potato inside or the ropes. So to finally be sure, we need to kind of cut the potato out, which is also a delicate operation. So now we made clear all these things, but then the question is how we can take the potato out. It should somehow get out, but not destroying the entire thing. Okay, like this. Oh, look, everything is perfect. You see that there are 8, this is an octahedron, there are 8 triangle faces, and the big diagonals are made by this straws, and you see that they don't touch each other, and the entire thing is rather stable. You see I can rotate it and move it and everything, they don't touch each other anyway. So we have a tensegrity, and Buckminster-Fuller should approve us now, I guess. Thanks for watching. Here is this ready thing. So you see that there are 3 straws, and they do not touch each other. Now, it's not, in the video probably it was seen better, but you see there are some space here, here, and here. They really don't touch each other. And if you want to see the scheme, you can look at of actually a bit different tensegrity. You can go to Wikipedia page, and there is even an animation. So compared to our example, some things are missing here. There is one thread missing here and one missing here. Topologically, it's the same. Now, if you add these 2 threads, topologically the same construction. But our is more, it's an octahedron, which is more regular, but this is another shape. Okay, and here is the animation. You can see how it rotates. Finally, you can even travel and see tensegrity in the real life. And so here is the photos also from Wikipedia. It's something called Needle Tower. And this is made by Kenneth Snelson, who was a student of an American architect, Buckminster-Fuller, who was the inventor of the word and who made many of things, many of tensegrities, and placed them in different places. And this one, you see the two views, the view from side view and view from the bottom. And it's clear that there are only, you see this sticks, now there are serious tubes and some threads, or I don't know what, rope, string, or whatever, which connect them. And as you see, this construction is rather stable, so it's okay. Let's return to the existential statement and their proofs. So, what is important to understand here? Let's start with some example, again, simple example. Imagine you want to find a 2-digit number that becomes 7 times smaller when the first digit is deleted. Well, it's a very easy question because there is not so many 2-digit numbers, and also it should be divisible by 7. So if you remember the multiplication table, you start, the first 2-digit number is 40, and then they go, and then you get 63, and the next one is 70, and then division by 7 gives 10, which is not 1 digit. So it's simple, small list, and you can check that 35 is the only thing. And if you ask for something more complicated, for example, imagine we asked you for a number that becomes 57 times smaller when the first digit is deleted. Then it's not so easy. And what is important, that if you come, next day and say, look, here is the number, then you are done. We have no right to ask you why you choose this number and how you found it. So it's just you give the example, we check the example, and we should be completely satisfied. And this is from the student's view. But of course, the teachers, as usually, the teachers do not have the rights the student have. So if you are a teacher, then you should explain how you find the solution. And now we'll try to explain how you can do this. So no, just let's write again. What do we want? Here is the number. Here is the first digit, which should be deleted. This is what remains, and this is our equation shows what should be achieved. Okay, but this is not very common for algebra because there is some dots here, so the number is written in a decimal notation. It's not very good. So let's rewrite it some. Imagine, let's denote this part by x. And then on the right hand side we have 57x. It's easy. But on the left hand side we have x plus a 0, 0, 0, and we need k zeros. And what is important, that if we add 1 0, this means that we multiply a by 10. So actually this thing is just a times 10 to the number of zeros. And we will write it now in a, so we assume that x has k digits, and we write this equation. So this is a shifted to the k places to the left, and then we add x and get 57 times x as we should. Okay, now it's a better equation because we can move x in the right hand side and get that a times 10 to the k is 56 times x, and 56 is 7 times 8. And now if you meditate a bit, you see how can you find a. So from this equation you can find a. Do you see how to do this? Look, here is in the right hand side we have factor 7. So in the left hand side also 7 should be somewhere. And here 10 is 2 times 5, so it's 2 to the k times 5 to the k. So here's 7 cannot hide. So the 7 should be here. And a is just one digit. So a should be 7. There is no other possibilities. And this should be written in the next slide. No, this is a should be divisible by 7 as our first. It should contain 7 as a factor. And only a is only 7, only one case. So we know a now. And then if we know that this is 7, so we can cancel the 7. And then we know that 10 to the k is 8 times x. So the question, what we don't know? What we don't know the k. So 10 to the k should be divisible by 8. This is the only thing we need. And for, you see the 10, 1000 are not multiples of 8, and 10 and 100 is not multiples, but 1000 is a multiple. So we know what x is. For this case, we know that x is 1000 divided by 8. And we are done. This is exactly the example we looked for. And of course, we can take bigger powers of 10. If we take not 1000, but 10,000, we get just 1 0 additional 0. So there are other solutions, but other solutions are just the same plus 0 at the end. So now we see how this problem can be solved. And of course, it's useful because it helps us to solve similar problems with a bit different number. This is a warning that if somebody asks you for an example, maybe such an example doesn't exist. So you should be prepared to the cases when the search doesn't help. So let's look at the problem of splitting weights. So imagine that you and your friend are preparing for a hike, and you have identical backpacks, and you want to be completely fair. You want that you have many items to bring for the hike, but then you want to split them into groups of exactly the same weight. And for example, if you have three, it's a trivial example, if you have three things of weights 1, 2, 3, then of course you put 3 in one side and 1 and 2 at the other side, and you are done. So you can write like this. And also it's convenient to represent in another way. So you can write instead of asking to split into two groups, you can ask what kind of signs should be here, plus or minuses, so that the total sum becomes 0. So plus are equal to plus terms are equal to minus terms. So for our special case, it's just 1 plus 1 plus 2 minus 3. Okay, so this is the problem, and the parameter of this problem is just the set of weights. And let's try to consider some other more interesting example. So imagine we have weights 1, 2, 3, 4, 5, 7, and we want to split them into two groups of equal weight. But how do we do this? The simplest question which you should ask yourself is just, what is this equal weight? So we compute the total weight, and we see that it's 22. 1, 3, 6, 10, 15, 22. Yeah, it's correct. And then if we want to split 22 into two groups, each group should be 11. And it's very easy to see a group of 11. And after you find one group of 11, the rest, of course, should be also 11. And indeed, 1 plus 2 plus 3 is 6 plus 3 11. So you are done. You find a group of weight 11, and then you know it, and the rest is also 11. So everything is okay. But not always you are so lucky. So there can be cases when the task is impossible. So imagine the weights are 1, 2, 3, 4, 5, 6, not 7, but 6. And then if you think what is the total weight, it's 21. And maybe you already see that you cannot split this into two equal groups. For a very simple reason, because 21 is not divisible by 2. And if you have two groups, then each group should have some integer weight, so 21 will be a multiple of 2. So, not possible. Now, just think of other case. Imagine we have not 1, 2, 3, 4, 5, 6, but 2, 4, 6, 8, 10, and 12. Is it possible or not? Do you see? Actually, it's not possible, but do you see why? Because it's actually the same problem. We just take the same weights, but twice bigger. So essentially, we just change the unit. We make a unit of weight twice more. But you can also say that the total sum is not 21, but 42 now, and this 42 is divisible by 2, but the quotient is 21. So it's not it's odd, and you cannot get it by summing the even numbers. Okay. Anyway, so this is just the bad news. Now, of course, not the special case. There is nothing bad. Just the condition. We asked for something which doesn't exist. But the bad news are coming, and the bad news can be illustrated by the next example. So imagine we have some other case, 1, 2, 3, 4, 5, 17, not 7, but 17. And if you count the total weight now, it's 10 units bigger, so it's 32. So now it's divisible by 2, everything looks okay. But, of course, if we divide it by 2, we get 16. And we have one piece of 17. So 17 is too big. If we put 17 somewhere, that is not enough weights to put in the other side. So this is another obstacle. And the bad news really is that obstacles can be of different types. And the problem is that there is no complete list of obstacles. Of course, it would be nice to have some rule. So if you want to split things into two group of equal weight, you should check whether the sum is even, whether there are not two big pieces, blah, 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 blah. And if there are some conditions are met, then it's possible and you know how. It's not the case. For this problem, nobody knows the complete list of obstacles and nobody knows the way to check whether this is possible or not. And maybe you heard the name NP-complete problem. It's something actually in scientific language, it's translated into normal one as some infeasible problem. So if you have, say, 10,000 numbers, which is for computer 10,000 is something rather small. But for this problem, if you have 10,000 numbers, then there is no way to check whether they can be split into two groups or not. So this is even worse. We don't know, when I said there is no way, it's a simplification. We don't know how to do this. And unfortunately, we cannot prove that such an algorithm doesn't exist. You maybe heard about this P and NP problem. This is exactly this question. So whether there is an algorithm which solves the splitting weights problem. So you see that you are now rather close to the boundary of modern computer science knowledge. Or better to say that the boundary is very close to us, because actually the problem is that people do not know much about the NP-complete problem. They tried it hard, but no real success. So what should you understand from this part of our course? First, that the structure of the proof depends on what you want to prove, of course. Second, that if the statement is existential, then you need only one example to prove it. And also, you have no obligation to disclose how you find an example. So if you cheated and asked the example from your friend, probably it's morally not okay. But from the mathematical point of view, it's completely valid proof. It's just a valid proof obtained by bad tools. But still it's a proof. And you should be prepared if you look for something, this something may not exist at all, and then you should not spend the rest of your life looking for a solution. It may not exist, and even maybe in some cases you can prove this, but in some cases, unfortunately, it's very difficult. So maybe you are still in bad shape, you don't know whether it exists or not. This is also a possibility. We have said that one example is enough to prove an existential statement, but of course you need to find this example, and it's a kind of a difficult thing sometimes. So we will show with some examples and show some tricks that can be used. Okay, usually when a teacher doesn't know what to say, how to solve the problem, can give, when there is no advice, teacher says just be creative, try whatever you can and meditate and so on. So this is we start with a nice picture. It's engraving of Albrecht Dürer. It's an old engraving called Melancholia. Maybe now it will be called the missed deadline, but at that time it was Melancholia. And here is some part of this picture. You can see in this picture there is on the wall there is a magic square. So what is this magic square? It's just a table with numbers, and what is magic here is that the sum is the same for all 4 rows or 4 columns and all 2 diagonals. You can check with the square. So this you can, okay, 13 plus is 21, 33 and 34. So the sum is 34 for every line. And in general, a magic square is just a placement of 16, not necessarily 16, but if you have n times n square, you need n square. But the first natural numbers, into a square, and this is the condition of the same sum in all columns, in all rows, and in two diagonals. This is the definition. And now the question is how to find these magic squares. And we know that Dürer somehow proved that a magic square of size 4 exists. Actually, if you are more careful, you could see that some letters, some numbers on Dürer's engravings are a bit strange. And even you can see that he changed some numbers. So even it seems that there exists a version of this print runs which have another number. But anyway, you can reconstruct this number using the magic square condition. So Dürer proof is correct. But if we look for a magic square of size 2, then it doesn't exist for a very simple reason. Here is this reason. Look, if we know that in magic square all the sums should be the same. So a plus b should be equal to a plus c. But then it means that b is equal to c. And we are not allowed to place the same number twice. So 2 times 2 magic square doesn't exist. And now natural question is, what about size 3? Can we make a size 3 magic square of 1, 2, 3, 4, and so on up to 9? So what do you think? Now we learn how to narrow the search. Actually, there are many combinations, but some clever tricks can condense, delete most of them and restrict our search to some small set. So let's see how it's done. We are looking for 3 times 3 magic square, and in fact, the truth is that they exist for all n starting from 3, 4, 5, and so on. It's not so easy to prove actually. But we are now interested only in 3 times 3 magic square. And what is called brute force search is mean that we should check all the possible positions of these 9 numbers. And actually, we know how many of them we have. If you don't know, you will know after the combinatorics course, part of this our course. But there are 9 possibilities for the first cell, and for each possibility for the first cell, there are 8 possibilities for the second one, and so on. And if you multiply all this number, you get 300,000. It's not much for a computer, but still for us it's completely impossible. So let's try to think how we can narrow the search. The first observation is we can know in advance we know that the sums in all rows and all columns are the same, but what is the sum? We can find it in a very easy way. So we know that in all the square together we have 45, and this 45 is made of 3 rows or 3 columns. So each column should have some 1/3 of 45, so it's 15. Why it's important? Because now let me show it before going further. So now, if for example we know what is here, then the rest is determined uniquely. So we don't need, we can make a search only for all possibilities to fill this square. And this is much smaller. Actually, we have only actually 8, 9, 8, 7, 6. So I think it's 120 times smaller. Still, it's a large number anyway. So we need more tricks, and this is one of the tricks which I showed to earlier. And the trick is that we can predict what is in the center. So look, we sum up 4 lines. This is the 1 line. This is the second line, third line, and fourth line. So first we know that if we sum all these numbers along these lines, we get 4 times the constant, this s, which is the sum of each line and each diagonal. So we have 4s. On the other hand, we can see that everything is counted exactly once, except for the center, which is count for 4 lines. It's count 4 times. So there is additional term, 3 times center. So 4s is the total sum, which we know is 3s, and 3 times center. So the center is 1/3, so there's 4 and 3, so the difference is S, and the center is 1/3 of the sum on every line. In our case, it's 5. So here is the equation, and here is the solution in general, and in our case, it's 5. Good. So we know that we have 5 here, and this is again our search is our search space becomes smaller and smaller. And the next step is to think where we should place 1. There is a minimal number 1, and it should be somewhere. And there are essentially 2 possibilities. Either it's in the corner or it's in the middle of the side. So this is our question: corner or middle? Now we should make a case analysis. So let's imagine 1 is in the corner. What happens then? Then we know that if this 1 is 6, so we have 9 here. Okay, what do we know about other things? So there is 3 lines which should have give 15. This line, and this line. So this is 14. So this should be 14, and this should be 14. But then let's look how we can get 14. So 14 is 5 plus 9, it's this one. And then there are other possibilities. This, for example, you can get 6 plus 8. You don't have number bigger than 9, so the only thing you can decrease this 9. And then you get 6 here. And the next step is get 7 plus 7, but it's not possible because we cannot use 7 twice. So actually there are only 2 ways to get 14. 5 plus 9 and 6 plus 8. And we have 3 positions when the 14 is needed. So we get a contradiction. 1 cannot be in the corner. This case is closed. Okay, then it should be in the middle. Let's put it in the middle, for example, in the bottom line. Now, actually there is also symmetry, like we can turn it over this line. So we can assume, for example, then on this line we should have 14, and this 14 we know that the only possibility is 8 plus 6, but the question is whether 8 here and 6 here or vice versa, but it's symmetric, so we consider one case. And now everything is determined. If we know, we can compute all the things. So if we have 13, we have 2, and in this line it's 11, 4, and there is 12, 3, and 2 plus 6, 8 plus 7, and what is very important, which cannot be predicted, that we have correct sums everywhere. You can check this, and also all the numbers are different. We can also check this easily by looking at the picture. So we are lucky, and indeed we get a magic square 3 times 3. So we know that our existential statement that the magic square of size 3 times 3 exists is proven. We have an example, it's enough. Our next trick is that we can transform the known solution into solutions for new problems. And this will be illustrated by a multiplicative magic squares. I will explain what it is. It just, instead of sums, we have products. So in magic square we have sums for rows, columns, and diagonals the same. And now we want products to be the same. And of course, now we cannot hope to use all the sequential numbers, because can you see why it's impossible? It's easy. So for example, look at 7. 7 is somewhere in the square. I don't know where. Then it appears in some products, but in some other products it doesn't appear. So we have no other numbers can give 7 in combination. So these two products will be different and no hope. We forget about this requirement. We just require to have different integers, but they can be arbitrary. So now the question, is there a multiplicative magic square? What do you think? Which looks rather strange. It's just an algebraic formula. 2 in the power x plus y is 2 in the power x times 2 to the power y. And mathematician will say that exponentiation transforms addition into multiplication. It's a homomorphism of an additive group into a multiplicative group. But anyway, we have this simple formula. Can you see what is the connection, how it can be used to transform the additive square into a multiplicative square? So this is the general slogan. And here is the trick. So instead of each number is replaced by 2 power this number. So if we multiply, for example, this 3, then according to this rule, we need to just to add the exponents. And the sum of the exponent is here. And so it's all the products are here. The sum is 15. And so here the product is 2 to the 15. And we get a multiplicative magic square. Good. But the numbers are rather big. The maximal one is 512. And can you find smaller one? There is a very simple observation. If you want numbers less than 300, what can you do? Actually, you see that the minimal one is 2. So we don't have 0 here. So we have all this number start here from 2, 4, 8, and so on. And so we can just divide all the numbers by 2, and instead of 2 to the 9, we have 2 to the 8, which is only 256. So this is the trick. But it's not the best thing we can do. Let me show you how we can do better. So we can even get them less than 40. And this is again use exponentiation, but in a more clever way. So let's start with a very strange magic square. It's almost magic in terms of the sum. It's all these are 3, but of course the same numbers appear many times, so it's not magic. But we can transform it into a multiplicative magic square, but again not magic, but with the products. So why does it help? Let's do the same thing for a bit different square. We just rotate it. And here we have the base 2, and here we have base 3. So we get 2 bad multiplicative magic squares, not where the numbers are not different. So what do? We can multiply them. So actually, if you we just have 2 times 1 is 2. Or 4 times 9 is 36. So in each cell, we place the product of the numbers in the corresponding cell. So why it's good? Because if we now take the product, for example, here, actually this is product of things here and here. And so here we have always 27. Here we always have 8. So in every line, we have 27 times 8, and so it's just a number, so we have the same number in all the lines. That's what we wanted. And additionally, you see that all the numbers are different, so it's multiplicative magic square, and all its numbers are less than 40. That's what we promised, and we achieved this in this funny way. In this part, we have several different non-related puzzles. Each of them is rather simple, but they show different sides of this search process. Our first puzzle is to find a 6-digit number which starts by 100 and is divisible by 9127. So this is our goal. We should prove that there exists such a number. And actually it's not so many candidates. So there are 3 here. We should have something starting from 000 up to 999. So if you are lazy, you can just write a program, and then the program will print you the list of all candidates. So it's programmer's solution. But if you are a mathematician, or if you are lazy in a different way, you don't want to program, then you can think a bit. Okay, let's try find a pencil and paper solution. Let's divide just the minimal possible candidate by this 9,000 something. And then we get something which is close, smaller than 11. but close to 11. And so the most natural thing to try is to try 11. And then indeed you get a number which is of the required 4, and it's divisible by definition, it's divisible by this number, and the quotient is 11. And you can see that the next one is too big. So if you have something divisible by 9,127, the next one be 9,127 apart. So it will be much bigger. This digit will be 9. 9, yeah. So actually this problem has only one solution. If you tried this programming, if you run this code, you will see this solution, hopefully. So this is easy. Next problem is to find a 3-digit number that produces a remainder y when divided by 2, 3, 4, 5, 6, 7. In all cases, it should produce remainder 1. And there is why we ask for a 3-digit number. Of course, if we just otherwise we can just use 1. It has only 1 digit, but otherwise it's okay, because if 1 is divided by anything starting from 2, we get remainder 1. So it doesn't work. But how can we find this n? Again, we can try a computer, but let's think a bit more. So n gives remainder 1 when divided by something. So what about n minus 1? What will be the remainder? Of course, it will be 0, because if we delete this outstanding 1, then everything, the rest should be divisible by 2, 3, 4, 5, and 6. And what is divisible by 2, 3, 4, 5, and 6? It's common multiple, it's called. And you see that this number works. 2, 3, 4, 5, and 6. So you can find here all the numbers. And actually, this is the minimal possible. So in number theory, you will see that this is a minimal possible number. And all others are multiple of this. And this number is 400. So now we recall that it's n minus 1. And so for n, we have 421. And you can check, then if you divide it by all this 2, 3, 4, 5, 6, 7, you get remainder 1. What about others? Other 3-digit numbers? Yeah, so we have already said that you can take any multiple of this number. So the next one will be 840. So if n minus 1 is 840, then you get the next one. Here is this computation. And the next one is too big. So there are actually 2 candidates for this solution. But we need only one. If you want to prove that there exists something, it's one example is enough. Good. Now our next puzzle. We want to find a perfect square, which means that the square of a natural number that starts with this strange digits. It's actually a first digits of pi, but doesn't matter. Just we can just take any sequence here. So we want to find an integer which such that n squared starts with a given sequence. We have to prove that such a number exists. How do we prove it? And there is a very important observation. It's enough to find a decimal fraction. So if we have some decimal fraction, and there is a decimal point and something, and then if we multiply this fraction by 10, this means that we move one decimal point, one position to the right. And in the n square, if we multiply x by 10, then the square is multiplied by 100. So in the square, we have moved 2 positions to the right. But anyway, it just the position changed and the digits are the same. So if we move the decimal point, we do not change anything in the sequence of digits. Now, everything is very easy because we can just compute a square root using a pocket calculator. It's useful, but still, if you don't have it, you can do it by hand. So you get this. And then you can try to move this point somewhere and see what happens. So let's see. Just we take all these things, and we see that we get almost what we wanted, but we have this something very close to this, but just a bit smaller. So we need to take something bigger. Oh, let's try something. Probably we don't need so many digits. So here is what we can do. So 177.243 square it starts in the right way, but this is not an integer, but we know what to do. We just move these things 3 positions, and these things move 6 positions, and we are done. And here is the answer. So we have an integer n, and n square starts with what we wanted. Good. Here is just the next one. It's also okay here. But there is more. Imagine we want to find 2 perfect squares starting with this number and which are different, essentially different. Prove that there is another number n, and n has a different first digit, and still n square is also starts with 31415. So we need to prove another thing, another n. What can we do? Actually, we can do the same trick with square root, but in a bit different way. So can you see what to do? Yeah, here is this. So let's put a decimal point in a different place. So let's put the decimal point here. Then the square root is different. Actually, we divide it more or less by square root of 10. But the first digit is now completely different. But we can use the same trick. We can try something a bit bigger than this. So it would be natural to try 5605, but we see that it's too big because we have here we have 6 instead of 5. So we need more digits actually. We can try this replace 2 by 1, and then with this we get what we wanted. So here is the desired sequence. And now we have 2 perfect squares, 2n, which start with different digits, and still their squares are okay. And this is from the previous slide, and this is what we get now. Problem is solved. Now we have a scientific name for our topic. It's integer linear combination. But the problem is quite elementary. Let's see. So imagine a country where there are only 2 types of coins. I don't know, the unit is, for example, florin, and there are 2 coins, 7 and 13. And there are 2 people, I don't know, a buyer and a seller, and each of them has many coins of each type. And one of them wants to pay 6 florin to the other. Is it possible or not? Probably you will say that say that we are kidding because it's obvious. 6 is 13 minus 7, so it's trivial. You pay 13 and you get back 7, and everything is done. But now, what about paying 1 florin? Also, you can explicitly compute this. You pay twice 7 is 14, and you get 13 back, so it's 1. But also you can make a more, bottom-up approach. So we know that we already can pay 6, but initially we can pay 7. So you can pay 7 and get 6, and you get 6 back, and this is 1. So you somehow capitalize on what you know already. What about 2 florins? Again, you can make a direct search and find something like this. So it's okay. This is everything is correct. So you get 2 in this way. Again, you can capitalize on what you know already. Do you see how? You see there is possible to get 1, and so if you can pay 1 florin, you can do it twice, and then you pay 2 florins. So it's just 2 times 1 is 2. 1 is possible, 1 is from here. And this works for every integer amount. So any integer amount is payable. And in mathematical language, one can say that for every integer c, this equation, this x and y are just the number of coins, and the negative number means that the coins are go in other direction, and this equation has integer solution. And in other terms, every integer can be an integer linear combination of 7 and 13. That will be a mathematical way to say the same thing. Now look at another case. Imagine another country which has only 15 and 21 coins. Again, how can we pay 6? And again, it's trivial. It's 21 minus 15. But now look, can we pay 8 or not? What do you think? There is an obstacle. Look that all the coins are multiples of 3. So whatever you pay or you get is always a multiple of 3. And 8 is not a multiple of 3, so no chances for 8, and for the same reason, there is no chances to pay 1. And 3. Can we pay 3? What do you think? We know that we can pay 6. This we already know. Now we see that we can pay 9. And because it's 15 minus 6, 15 we know, and 6 we also know. Now we know 9. And so we can capitalize on this and say that we can pay 9 and 6 and get 3. So this is called Euclid's algorithm. Actually, probably you heard about this, and we will come to this in number theory again. But for now, we see that 3 is payable. And if you want to unfold this, you can just compute for each of the number. You can compute how you pay it. So how you pay 9, how you pay 6, how you pay 3, and then you get this. And you can also check directly. This is 45 and this is 42. Yeah. So 3 is payable, and for the same reason, any multiple of 3 is payable. And we can say that this equation has integer solutions if and only if c is a multiple of 3. So if c is a multiple, then there are solutions. If c is not a multiple, there is no solution. So in other terms, a integer linear combination of 7 and 13 are exactly multiples of 3. This is the general statement of this form says that they are multiple of the, if we have coins of two types, their linear combinations are multiple of the greatest common divisor. But this will be the topic of the number theory course. Now we switch from number theory to graph theory. It's also a part of our course, but now we are using this graphs in a very simple way. So here is the puzzle. So there are 3 hotels in a town, A, B, and C, and you have vouchers. You have 10 vouchers for hotel A, 15 vouchers for B, and 20 for C. But there is a restriction that the hotel doesn't allow you to use the voucher 2 nights in a row. So you need to change hotels. Every night you should move to a different hotel. So somehow you can symbolically draw this A, B, C as hotels, and this every night you should take, every day you should take a green line, move along the green line from one hotel to another. And the question is whether it's possible to do this for 5 consecutive nights. What do you think? Here is the hint. You can, it's not obligatory, but let's try. We can try to repeat 5 times a path of length 9. So you see that all these numbers are a multiple of 5. So if we can use the same, solve the same problem with 2, 3, and 4, then we can repeat the solution several times and get the solution for the original problem. There is one subtle thing here. Did you see what is wrong is what I have said? actually this path for a smaller problem should have different endpoints. It should not end when it's where it started, because otherwise when we combine this path together, we get a problem when switching from one to the other. So initial point should be different from the final point. Okay, but still let's try to find this. So we have a path of length 9, and it should use 2, 3, and 4 times A, B, and C. So path of length 9 and C should appear there 4 times. And so C cannot appear twice in a row. So it's natural to try C with distance 2 and put something in between. So let's decide that every second point is C. Let's try it. And then it's rather easy. We start with A, C, A, C. So we used A twice as it's required. And then we switch to B since A is already used. B, C, and B. So we have a path of length 9. 1, 2, 3, 4, 5, 6, 9. And the end point is different from the starting point. So we can just repeat it like this. A the same second time and 5 times. So we get, in this way, we get the solution. We proved that we can find a way to spend all our vouchers without violating the rules of the hotels. This is the positive case. But sometimes the task is impossible. Let's look at an impossible case. So imagine we have more vouchers for C. We have 30 vouchers for C. And then we can try to spend 45 nights there. Is it possible or not? What do you think? Do you see an obstacle for that? And the obstacle is that we have too many vouchers for C. We have 45 nights and 30 vouchers for C. And we cannot use them twice in a row. So between every 2 C, there should be at least 1 A or B. So if we have 30 Cs, when we should fill somehow at least 29 holes. And we have only 10 and 15. So that's not enough hotels that can be used between Cs. We need at least 29 others, and we don't have them.
Hello everybody, welcome back. In this lesson we are going to discuss ways of showing optimality. As a warm-up example, consider the following situation. Imagine a small chocolate factory that produces 2 types of chocolate, milk chocolate and dark chocolate. The price per box of milk chocolate is $10 and the price per box of the dark chocolate is $30. Okay, so the estimated daily demands are 500 of boxes of milk chocolate and 200 boxes of dark chocolate. Unfortunately, the factory cannot fully satisfy these daily demands because it can produce at most 600 of boxes per day. So under the given constraints, the natural question is, what is the optimum production plan? To find it out, they go to a consulting company. And the consulting company claims that the optimum profit per day is $10,000. So the question is now, how can the consulting company convince the factory that it is indeed optimal? So in general, such a proof of optimality consists of 2 parts. The first part is the so-called existential part. In this case, we need to show that there exists a production plan achieving the value $10,000. Right? And the other part is the so-called universal part. We need to show that for all plans, the profit that they achieve is at most 10,000. Okay? Okay, let's start with the existential part. So once again, for this we need to give the explicit production plan achieving $10,000 per day. And for this, the consulting company suggests that the factory needs to produce 400 boxes of milk chocolate per day and 200 boxes of dark chocolate per day. First of all, we need to check whether all the constraints are satisfied, and it is not difficult to do. First of all, in the proposed plan, the factory produces no more than 500 boxes of milk chocolate, right? And also no more than 200 boxes of dark chocolate, and in total no more than 600 boxes. And indeed, the profit can also be easily computed. This is 400 boxes of milk chocolate times $10 per box plus 200 boxes of dark chocolate times $30 per box of dark chocolate. This gives exactly 10,000. So we are done with the existential part. Now we need to show the universal part, namely we need to show that in any production, in any valid production plan, namely in any plan satisfying all the given constraints, the profit is at most 10,000. Okay, so for this, let's denote by M and D the number of boxes of milk and dark chocolate respectively produced per day. Then we are given the following constraints. M should be at most 500, D should be at most 200, these are estimated daily demands, and M plus D should be at most 600, okay, because the factory cannot produce more than 600 boxes per day. What we would like to show is that under these constraints, the profit is at most $10,000, and the profit is computed as 10 times M plus 30 times D, okay? So to prove this, it is enough actually to compute the sum of the following two inequalities. The first inequality is 10M plus 10D is at most 6,000. So it comes from just by multiplying this inequality M plus D is at most 600 by 10. When we do multiply it by 10, we get 10M plus 10D is at most 600, right? 6,000, I'm sorry. On the other hand, we can also get this inequality, D is at most 200, and multiply it by 20, then we will get 20D is at most 4,000. Okay, then if we compute the sum of these two inequalities, then what we get is exactly what we want to get, that the profit is at most 10,000. Well, that was easy, right? So, and that it was actually clear from the very beginning that in this case the optimal production plan actually is to produce as much dark chocolate as needed and only then to produce milk chocolate, right? But the message of this short warm-up video was not about chocolate, of course, but about optimality. So once again, to show that some value alpha is optimal, what we usually need to do is to show that first of all that this value is achievable, that is to provide some solution that achieves the value alpha. This is the existential statement. And then we need to show the universal statement that all solutions achieve the value not greater than alpha. So in this lesson we are going to show several such examples of optimality following the same pattern. Our next puzzle is the following. We are given two-digit numbers, that is integers 10, 11, 12 and so on 99. And we would like to take as many of them as possible subject to the following constraint. We are not allowed to take simultaneously two numbers x and y if x plus y is equal to 100. Put it otherwise, we are not allowed to take simultaneously x and 100 minus x. So the question is, what is the maximum possible number of two-digit integers that we can take under the given constraint? So let's start solving this problem. So first of all, if we take the smallest possible number, which is 10, then it is immediate that we cannot take 90 simultaneously together with 10, right? And vice versa. If we take 90, then we cannot take 10. So in a sense, 10 and 90 form a pair, such that from this pair we can take at most one number. For exactly the same reason, the numbers 11 and 89 also form the same pair. From this pair we can take at most one number. So continuing in the same fashion, we discover 40 such pairs, starting from 10 and 90 and going to 49 and 51. Also there are 10 like 3 numbers remaining. So these are numbers without any pairs. One of them is 50, because 50 is a pair for itself, and the other 9 numbers are 91, 92, and so on, 99. For all these numbers, there are no 2-digit number that can be added to them to get 100. So this tells us already that we cannot take more than 15 numbers under the given constraints. Why is that? Well, because we have 10 free numbers, but all the remaining 80 numbers are paired, and from each pair we can take at most 1 number. So in total we can take at most 10 plus 40 numbers, which gives us 50 numbers, right? So this is actually the universal part. We've just proved that any solution cannot be of size more than 50. At the same time, it is not so difficult to construct a solution of size 50. Just take all the numbers which are at least 50. There are 50 such numbers, and it is clear that it is a solution. If you take 82 numbers from this set, the sum is going to be greater than 100. Okay, so it was not very difficult, but just to follow the same pattern that we discussed in the previous video, let's wrap it as a formal theorem, and let's prove it following the same pattern. So the statement is the following: the maximum number of 2-digit numbers that one can take, subject to the constraint that there are no 2 numbers whose sum is equal to 100, is equal to 50. So the first part is, as usual, universal. We need to show a solution, and our solution is, for example, the numbers starting from 50. It is not difficult to check that it is indeed a solution. On the other hand, let's show the universal part, that any solution has size at most 50. To show this, note that we have 40 pairs, and we have 90 numbers in total, and we have, among these 90 numbers, there are 40 pairs, and from which pair we can take at most 1 number. So in total, from each pair we need to exclude at least 1 number. So in total we have at most 90 minus 40, which is equal to 50 numbers. Our next puzzle deals with rooks on a chessboard. Let me remind you how rook moves. So it moves horizontally or vertically. For example, the rook that you show here on the slide can move along either vertical line or horizontal line. Okay? So the natural question to ask is, what is the maximum number of rooks that one can place on a chessboard such that no 2 rooks attack each other? While analyzing this problem, it will be instructive to use the well-known Pigeonhole Principle. So very roughly it states the following: if you have 9 holes and you have 10 pigeons, then there is absolutely no way of putting these 10 pigeons into these 9 holes such that in every hole there is at most 1 pigeon. And it is more or less clear. If you put at most 1 digit in every hole, then the total number of pigeons that you have is at most 9, right? While you have 10 pigeons. Well, using this principle, we can argue then that in our solution there should be at most 8 rooks for sure. Why is that? Well, just because if we have more than 8 rooks, then there must be a row, for example, a column in which there should be more than 1 rook. So, for example, if we have a row where we have 2 rooks, then these 2 rooks definitely attack each other. So, in every row there should be at most 1 rook. So, in total we have at most 8 rooks. So what we've just proved is that the size of any solution is at most 8. Our answer, the answer for our problem is at most 8. At the same time, it is not so difficult to place 8 rooks, for example, like this. And this tells us immediately that the answer for our problem is exactly 8. because we've just shown that it is possible to place 8 rook, and we've just shown that it is not possible to place more than 8 rooks. As a final remark, let me also show you that this is not the only optimal solution. In fact, there are many optimal solutions. For example, you can place rooks like this, or even like this. Our next puzzle is about knights on a chessboard. So a knight moves in an L shape. For example, the knight shown here on the slide can move to any of the shown 8 positions. So the knight moves by 1 cell vertically and 2 cells horizontally, or vice versa. Okay? So the natural question, you can guess it already, of course, is what is the maximum number of knights that one can place on a chessboard such that no 2 knights attack each other. So while trying to solve this problem, let's take a look once again on the allowed moves for the knight. Okay, as we see, the knight here stays on a white cell, and all the 8 cells that it attacks are actually of an opposite color. They're all black, right? So this already tells us something. So it tells us that if we place knights on all 32 white cells, like here, then definitely no 2 of them are going to attack each other. So you can either check this manually, or you can either once again notice that a knight standing on a white cell only attacks black cells, right? So okay, so this is already good. We have a solution where we have 32 knights. It is still at the same time not clear whether it is optimal or not. It is clear that this one cannot be extended. We cannot put more knights here on the chessboard. At the same time, it is still not excluded that there is some other solution whose size is greater than 32. So let's try to understand how one would show that it is not possible to place more than 32 knights. First of all, why we cannot just place knights to all 64 cells? Well, just because in particular it is not possible to place knights simultaneously to these 2 cells, to the leftmost, to the left bottom corner, and to the position shown here on the slide. So, in a sense, these 2 cells form a pair, right? Because, so for this pair of cells, we can select only one of them. We cannot select them simultaneously, like in one of the examples shown, considered before. Right? So let's just, to reflect this fact, let's connect them by a segment. And now let's realize the following. It would be great if we could partition all our 64 cells into such pairs. In this case, we would be done just because this would mean that everything is partitioned into pairs, and so the number of pairs is 32, and for every pair we know that we can take at most 1 cell. I mean, we can place at most 1 knight into these 2 cells. This would immediately mean that 32 is indeed optimal. The only thing which is still not clear is how to partition the whole board into such pairs. So let's at least try to do this. So first of all, we have this pair. Let's add this symmetrical pair. Let's now add 2 more pairs, which are also in a sense similar. And now we have this nice picture. Why it is nice? Because it is already a rectangle. It is a 2x4 rectangle. And so what we already know is that for this 2x4 rectangle, the number of knights that can be placed inside this rectangle is at most 4. right? Because there are 8 cells in this rectangle, and all these 8 cells are partitioned into 4 pairs. For each pair, we know that for each pair of such cells, we know that we can place at most 1 knight into them. So there are 4 pairs, and for each pair, we can place at most 1 knight. So at most 4 knights, which is great already. And the fact that this rectangle is of size 2 by 4 actually implies that we can partition the whole board into such rectangles, right? Like this, which in turn means that we can partition the whole board into such pairs, which finally proves that 32 is indeed the answer for our initial problem. Our final chessboard puzzle is to place as many bishops on a chessboard as possible. A bishop moves diagonally, so it moves either like this or like this, right? So in order to solve this problem, let's just try to divide our board into diagonals. In case of diagonals, it is particularly easy. So if we just consider all possible diagonals that go like this, the whole board is going to be partitioned into 15 diagonals. So first of all, we definitely know that there will be no more than 15 bishops in our solution. But in fact, if you look closely into this picture, you can actually see more than, we can actually extract an upper bound better than 15. Because, for example, the diagonal that we've numbered 1 here, it consists of just 1 cell, this one. And the diagonal 15 also consists of 1 cell. So we know that we can place at most one bishop to the first diagonal and at most 1 bishop to the 15th diagonal. Well, simply because each of them consists of just 1 cell. At the same time, we cannot place a bishop to the first diagonal and to the 15th diagonal simultaneously because they are on the same this diagonal, right? So this improves our upper bound to 14 actually. So we have 15 diagonals. For each of them we have at most 1 bishop, but at the same time we can place at most 1 bishop to the first and 15th diagonal. And 15th diagonal, right? So this gives us an upper bound 14. So if we manage to place 14 bishops on a chessboard, then we know for sure that this is optimal. And in fact, it is possible. So you can easily check that in this case there are 14 bishops and no 2 of them attack each other. Well, just because, for example, this bishop attacks only these cells. This bishop attacks these cells and this cell and so on. So no 2 of them attack each other. So this is once again a solution of size 14, and we've just proved that there cannot be a solution of size more than 14, which means in turn that 14 is an optimal answer. Our final optimality puzzle is it deals with numbers once again, and it is slightly more complicated than the previous ones. So in this case, we're given numbers from 1 to 50, integers from 1 to 50, and our goal is to take as many of them as possible with the constraint that we are not allowed to take x and 2x simultaneously. Okay, so the question is, what is the maximum number of such integers that we can take to satisfy this constraint? Okay, let's try to reason about this problem as usual. So first of all, the simplest constraint says that we cannot take 1 and 2 simultaneously. So there is a conflict between 1 and 2. But this is not the only conflict that 2 participates in. The other one is between 2 and 4. You cannot take 2 and 4 simultaneously. And you can actually extend this further. So we extend this to a so-called chain, which consists of 1, 2, 4, 8, 16 and 32. right? So from this chain we know that we are not allowed to take any two neighbors in this chain. So this is just one of the chains. Another such chain is, for example, it starts from 3. So it is 3, then 6, then 12, then 24, and then 48, right? For this chain we also know that from it we cannot take any two neighbors. And in general, you can partition all the ground set into such chains. Each such chain starts with its own odd number. So it is probably instructive to visualize it like this. So in this case, the first chain starts with the number 1, and we've seen it already: 1, 2, 4, 8, 16, 32. So this is our first chain. The next one starts with the next odd number: 3, 6, 12, 24, 68. So it is already shorter. The next one starts at 5, then 10, then 20, then 40. It is already of size 4, and so on. So when we reach the number 27, all the chains already of the length 1. I'm sorry. So for all the chains starting with 27, for example, with 29, 31, 32, all these chains consist of just a single integer number. Okay. Then what it claims here is that chains are independent. So what this means? So first of all, each number appears in exactly one chain. To actually find this chain, just take your number, for example, I don't know, 46, and start dividing it by 2. So if you divide 46 by 2, you get 23, which means that this is that you know the beginning of your chain. So each chain has a unique odd starting number, which means that all of them do not intersect. And what is also important is that there are no conflicts between different chains. So if you take any number like 8 and you take any other number from any other cell, for example 20, we know for sure that these are not numbers of the form x and 2x. All numbers of the form x and 2x, they lie in the same chain. Okay, this is already great, because this means that we reduced our problem of taking as many numbers from our ground set of all the numbers from 1 to 50 to the following problem. We have chains, they are independent, so our goal is just for each chain to select the possible, the maximum possible number, right? But this problem is much easier. So if you have a chain, for example this one, and you know that you cannot take any two consecutive numbers, any two neighbors from this chain, and you would like to maximize the number of elements that you take, then of course the optimal strategy is to start from the very beginning and to take every second number. For example, in this chain it is going to be as follows: 1, 4, and 16. For the next chain it is going to be, for this one, 3, 12 and 48. For the next one it is going to be 5 and 20. Clearly for the chain starting with 5, so 5, 10, 20 and 40, you cannot take more than 2 elements, right? So this actually shows us that the optimal strategy of taking as many numbers as possible is in any chain to take every second number. So this gives us a solution which consists of the following highlighted numbers. So we first take all the odd numbers. There are 25 of them. Then we take also these 6 numbers and these 2 numbers. So it is 25 plus 6 plus 2, which is 33. So first of all, it is a solution. We see that it is indeed a solution, so there are no two numbers that of the form x and 2x. And why it is optimal? Well, just because we partitioned the ground set into independent pieces, and for each such piece we proved that we've taken as many elements from this piece, from this particular piece as possible. So this finally proves that 33 is indeed an optimal solution in this case. Hello and welcome to the lesson Computer Search. To prove that an object satisfying some particular properties exists, it is actually enough to construct and present such an object. At the same time, there are cases when it is not so easy to do this by hand. And it is exactly the situation when it makes perfect sense to ask computers to help us. And this is exactly the thing that we're going to do in this lesson. Namely, we will consider two challenging puzzles, namely n queens puzzle and 16 diagonals puzzle. If you try them, you will notice that it is indeed not so easy to find a solution. Instead of constructing such a solution by hand, we are going to implement a simple program that is going to help us to find a solution in blink of an eye. So we start with the n queens puzzle. Let me first remind you how the chess queen moves. So it moves horizontally, diagonally and vertically. So for example, a queen that you see here on this slide can move along either this vertical line or horizontal line or two diagonal lines. Okay? Then the natural question is the following. Given an n by n chessboard, your goal is to place exactly n queens on this board such that no two queens attack each other. Okay? So, first of all, we know that the solution for this puzzle exists whenever n is at least 4. At the same time, if you try to solve this puzzle by hand, you will notice that already for n equal to 8, it is not so easy to find it by hand. Not to say about n equal to, say, 20. So let's try to find a solution, and let's try to find and implement a computer program that will find a solution almost immediately. First of all, let's try to understand how to represent a particular solution in our program. And for this, let's notice that if there is a solution, then in every column there must be exactly one queen. Why is that? Well, exactly because if there are at least two queens in some column, then they definitely must attack each other. So there must be at most one queen in each column. At the same time, if there is a column without a queen, this means basically that in total there are strictly less than n queens. And similarly, we conclude that in each row there must be exactly one queen. Okay? Now let's consider the following solution for the case where n, the size of the board, is equal to 4. So in this case we have 4 by 4 board and there are 4 queens, exactly one queen in each row and exactly one queen in each column, such that they do not attack each other. So what the title of the slide claims here is that this solution can be represented as a permutation. To see this, let's index all the columns and all the rows by numbers starting from 0 to n minus 1. So in this case n is equal to 4, so n minus 1 is equal to 3. Okay, so now let's represent the corresponding placement of queens by the following permutation of the numbers 0, 1, 2, 3. So how it is represented by this permutation? Well, it is easy to see. So this is an array. Right? It is of size 4. This is its indices 0, 1, 2, 3. So the contents of the cell 1 actually tells us that in the zeros, the contents, of the cell 0 tells us that in the zeros column, this is the zeros column and this is the zeros cell, we have a queen in the first row. This is the queen in the first row. Right? And this is exactly corresponds to this one. For the second column, that is column number 1, because we start from 0, we have 3 in this cell, and this is exactly indicates the fact that for this column we have a queen standing at the third row in this column, and so on. So at this point it should be clear that every correct solution can be represented by a permutation. This is exactly because in every row and in every column we have a single queen. At the same time, not every permutation defines a solution, and this is shown here on the slide. Again, so on the left we have our previous solution, on the right we have also some permutation which defines some placement of queens such that in every row and in every column there is exactly one queen. At the same time it is not a solution, right? Because we have two queens here on the same diagonal, so they attack each other. So we definitely need some procedure that will check whether the given permutation is indeed a solution. So we need to implement the procedure that will be given a permutation, and it will output true if and only if in this permutation, in this placement of queens on the n by n board, there are no two queens that stay on the same diagonal. So let's try to design a formula which will tell us when two queens stay on the same diagonal. This is our initial picture. Actually, it shows our initial queen, and it shows all the positions where it can move. So what I claim is the following: two queens stay on the same diagonal. Consider, for example, this queen and, for example, this queen. So they stay on the same diagonal because this horizontal shift exactly equals its vertical shift, right? And this is true for all the positions shown here on the slide. So in this particular case, we have 4 cells here and 4 cells here. Now let's consider, for example, this queen. So these two guys stay on the same diagonal exactly because the difference between their coordinates with respect to columns, is equal to the distance. It is equal to 3 in this case, is equal to 3 with respect to rows. And on the right here we see a formula. So if we have two cells with coordinates I1 and J1 and I2 and J2, so this means that we have a queen standing at I's row and J's column, and we have another queen standing at I2 row and J2 column. So then they stay on the same diagonal if and only if the absolute value between I1 and I2 is equal to the absolute value between J1 and J2, right? So this is our formula, and it allows us to immediately implement a simple program, just 4 lines of code, that will check whether a given permutation is indeed a solution. So to check this, we do the following. We just, given a permutation, we go through all possible indices of rows, I1 and I2. So here we just iterate through all possible such pairs using combinations from Atthur tools. Okay, so then we just check whether the absolute value of I1 and I2 is equal to the absolute value of J1 and J2, where J1 is computed as permutation of I1, so this is J1, and I2 is computed as J2, is computed as a permutation of I2. So if these absolute values coincide at least for some pair of I1 and I2, this basically means that there are two queens that attack each other. In this case, we immediately return false. If there is no such pair, we return true. So after this procedure is implemented, we do a small sanity check. We just check whether for the previously two considered examples, the first one is indeed a solution and the second one is indeed not a solution. Okay? So when given such a check whether a given permutation is a solution or not, we can actually implement the whole program for finding a solution for the 8x8 board, for example. So this is our our procedure that checks whether a given permutation is a solution or not. And then what remains to be done is just to iterate through all possible permutations. And fortunately enough, in Python we can do this very easily. So we just iterate through all possible permutations, and for each one we check whether it is a solution or not. If it is a solution, we print it and we stop immediately. Okay, and this is basically it. So if you run this program, you will notice that it will find a solution for n equal to 8 almost immediately. At the same time, already for n equal to 13, for example, it takes a noticeable time. Okay, not to say about n equal to 20. It will never stop for n equal to 20. In the next video, we will actually optimize our program so that it works quite fast, even for n equal to 20. In this video, we're going to further optimize our program so that it is able to compute a solution for the n queens problem, even for n equal to 20. The method that is going to help us is called backtracking. Its main idea is the following. We are going to construct our solution piece by piece. What it means for the n queens puzzle is the following. We are going to first place a queen in the first row. Then we're going to place a queen in the second row, then in the third one, and so on. If at some point there is just no possibility to place a queen in the current row, then we will get back and adjust the position of some of the previously placed queen. And this step is called backtracking. Once again, it means the following. If the current partial solution cannot be extended to a solution, then we get back and try to adjust our partial solution. This is probably best illustrated with an example. Let us prove that there is no solution for the n queens problem when n is equal to 3. So initially we have an empty board. So our goal is to place 3 queens here. We know for sure that we must place a queen in the first row somewhere. So let's try the most obvious choice. Let's try the leftmost position in the first row. So here we are, we placed a queen, then we need to place a queen in the second row, in the next one. However, as we see, these two cells are already attacked by the single queen that we have. So the only possibility where it still makes sense to place a queen is the last cell in the second row. So we try to do this, but this is a dead end, because this cell is already attacked by this queen, this cell is already attacked by this queen, and this cell is also attacked by this queen. Right? Which means that we need to go back. And this is what we do. We return back here, but remember that in this case, this cell is already attacked, this cell is also already attacked. So the only possibility to place a queen in the second row was to place it into this cell. So we tried this and it doesn't give a solution. So we get back even here. So and here we try to place a queen into the second cell in the first row. Okay, let's do this. So here we are. We placed the queen into the second position in the first row. But then we see that there are just no possible cell where we can place a queen in the next row. Right? Because all of them are already attacked. So once again, we get back, we backtrack. And then we try the last available option for the first row, that is the rightmost cell. Then again, we need to place a queen to the second row. This cell is already attacked, and this one is already attacked, so we place a queen to this cell. Okay, and in this case again we have no choice for the last row, because all the cells are already attacked. This is attacked by this queen, this cell is attacked by this queen, and this cell is attacked by this queen. Okay, so what we've just proved is actually that there is no solution for the 3 by 3 board. Let's now consider a slightly more complicated example when n is equal to 4. So once again, we try to place a queen to the first available position in the first row. This gives us the following picture. So in this case, this cell is already attacked in this one. So the first available cell in the second row is the third one. So we try to place a queen into this cell. Now this cell is attacked by this queen. This cell is attacked by this queen. This cell is attacked, and this cell is attacked by the second queen. So this is a dead branch. So we do not try to continue it because definitely it will not lead us to a solution, right? Just because for this particular row we cannot place a queen. So we get back here and we try to place a queen in the second row in some different position. And the different position is the only remaining position is this cell, right? So let's try to do this. We place a queen here. So for the next row we place a queen here, and then we see that for the last row all the cells are attacked. So we get back here. We place the queen to the last available position. So again we get back, and then we get back here, and then we adjust the position of the first queen. Okay, then let me proceed faster. Then what we see here in this branch is that we were actually able to extend the solution to the 4 queens. Okay, so what we get here is actually a solution. So at this point we actually might want to stop and to report that this is a solution. But if we would like to find all possible solutions, then we can continue this process in a similar fashion. So we get back to the initial state, and then we try to place a queen in the first row in a different position. For example, in this case in the third position. And then we do essentially the same. We try to extend it, and then we try to place a queen into the rightmost available position in the first row, and then we again enumerate all possible cases. So what we see here now on this slide is a complete recursion tree of all possible kind of partial solutions. All the final solutions are shown here on the last row, and all these guys are actually dead ends. So these are solutions or partial solutions that cannot be extended. So in this case, for example, we cannot place a queen to the next available row just because all the cells are already attacked. In this case, we cannot place a queen to the next available row, which is the last row, because again all the cells of this row are already attacked. Okay, so this is the main idea of backtracking illustrated on this 4x4 queens puzzle. Now we are going to try to implement this idea, and before doing this we need to actually be able to generate all possible permutations. As you remember from the previous video, we were just using built-in procedure for generating all possible permutations, but now we need our own procedure because we would like to partially extend permutations, and for some partial permutations we are going to stop trying to extend them because they are not going to be extended to a solution to our n by n queens puzzle. Okay, so to generate all permutations we would do the following. We are going to do this recursively. Namely, we are going to implement a procedure that is going to call itself to generate all permutations. So this is called to generate permutations. Initially we call this procedure with the parameter perm, which stands for permutation, of course, which is initially just an empty list, and the parameter m, which is equal to 4. What this procedure is going to do is the following. First of all, if the length of the current permutation is equal to n. So remember that we're going to construct our permutations piece by piece. So we first will add the first element, then the second element, the next element, and so on. So if it was already extended to a list of size n, we just print it and return. We do not try to extend it to some other permutation anymore, because it already contains n elements. If it contains less than n elements, we try to extend it by some new element. And this new element is denoted by k, and it ranges through all possible values from 0 to n minus 1. First of all, we check whether k is presented in the current permutation. If it is presented, of course, we are not going to try to add it, because we need a permutation. We want all the elements in our permutation to be different, right? So if k is not in the permutation, we add it to the current permutation, and we call the same procedure again. So we try to construct it, we try to extend it piece by piece further, and for this we call just exactly the same procedure. And in the end, when we make this call, we remove the just added element k from this permutation in order to add another element to it, right? So, and this is the output of the corresponding method. So it generates all possible permutations of 4 elements, 0, 1, 2, and 3. Okay? Now, what we're going to do is to combine 2 methods that we already implemented. So, on one hand, we have this recursive generation of all possible permutations. On the other hand, we have a method which checks whether a permutation is a solution or not. And we can actually adjust it to just check whether, if we have a partial permutation, whether it can be extended to a solution or not. And for this, it is actually enough to check whether when we extend the permutation, this actually corresponds to the case when we place a new queen to the current row on our board. And for this, it is enough to check whether this last queen actually attacks some of the previous queens. So we need to implement this check. We need to implement the check whether the current partial permutation can be extended to a solution of the n queens problem or not. So let's try to implement such a procedure. So we're given some partial permutation in this case, and we are implementing a procedure called can be extended to solution. So for this, we take the last queen. Okay, so we just compute the length of the permutation and subtract 1. So this is the last element of the last index of our permutation. Then we iterate through all possible previous indices. Okay, so G ranges from 0 to I minus 1. And we check whether the last queen and some previous queens, they stay on the same diagonal. So for this, we check whether I minus j is equal to absolute value of perm of I minus perm of j. So we do not use absolute value of I minus j here, because we know that I is greater than j, because I is the last element of our permutation. So if this equality holds, we return false immediately, because this means, once again, that these 2 queens stay on the same diagonal. If there is no such pair, we return true. So this means that we still believe that the current permutation can be extended to a solution. At least there are no conflicts in the current permutation. Okay? And then this allows us to implement the program as follows. This is just a combination of generating all permutations together with checking whether the current partial permutation can be extended to a solution or not. So let's see. So the procedure is called extend. Initially, it is given a partial permutation which is empty, together with a parameter n equal to 20. Okay. So we first check if the length of the permutation is n. We just print it and stop the whole program. So this means that we found a solution. Otherwise, we try to extend it. Once again, we try to extend it by an element k, which ranges through all values from 0 to n minus 1. We only do this if k is not currently in permutation, and we append it, and then we check whether there is any conflict in the resulting partial permutation. So this is done in this check. So if there are no conflicts, we try to extend this partial permutation further, and for this we call the same procedure extend again, right? And then after we try to do this, we pop the last element k in order to try to add another element to this permutation. So if you run this program, you will notice that it computes a solution even for n equal to 20 on your laptop. Okay, and this is the power of the backtracking method. So once again, its main idea is to construct a recursive tree of all possible solutions. But when our current partial solution, when we realize that our current partial solution cannot be extended to a solution, we cut the corresponding branch immediately. For this reason, it works pretty well in practice. Now, when you know what backtracking is, you will have a chance of using this powerful method to solve another challenging puzzle, which is called 16 diagonals. The goal in this puzzle is to place many diagonals into a square grid such that no two diagonals have a common point, or in other words, they do not touch each other. So we start with a very simple version of this puzzle. In this case, we're given a 3 by 3 grid, and our goal is to place 6 diagonals in this grid. It is not very difficult for this case, so you see one solution here on the slide. And this is another solution where again we have 6 diagonals and no two have any common point. Now let's gradually increase the size. Let's consider a 4 by 4 board. Now the question is to place 10 diagonals. It is already not so simple, but here you are. This is a solution where there are 10 diagonals. And now we come to a challenge. In this case, we're given a 5 by 5 grid, and our goal is to place 16 diagonals. You may want to first place such 16 diagonals by hand, and you will find out that it is not so easy. So instead of trying to do this by hand, you may also want to implement a backtracking procedure. And this is your exercise actually. And this is a suggestion for you. So to implement a backtracking program for solving this puzzle, you may want to do the following. So consider your 5 by 5 grid. So this is 25 cells which are initially empty, or to be more formal, let's assume that initially we have -1 in all these cells. -1 indicates that we haven't yet decided what to put into all these cells. And then you start processing all these cells one by one. Say you start from the first row and you first consider all the first row, then the second row, then the third one, and so on. So for each cell, for the current cell, you do the following. You consider all possibilities for this cell. Either it has a diagonal which goes from this corner to this corner, or you consider a diagonal which goes from this corner to this corner, or you consider a case when there is no diagonal in this case. So, for example, you may store just an array of 25 cells, where in each cell you store either -1, which means that you haven't yet decided what to put into this cell, or, for example, 0, which corresponds to the fact that there is no diagonal in this case, or 1 if there is a diagonal going from this corner to this corner, or 2 if there is a diagonal going from this corner to this corner. Finally, when you place a new diagonal, when you fill in a new cell, if you place a new diagonal into this cell, you need to check whether it produces any conflicts, whether it touches any other diagonal. And this should be implemented very carefully. And if it doesn't touch, then you continue trying to extend it. If it touches, you stop immediately and you backtrack. Okay? Well, good luck implementing this program. Hello and welcome to the lesson devoted to recursion. We start this lesson with a very soft introduction to recursion. So imagine a line to a museum. Imagine a person that just gets in a line. Call her Alice. And she has this natural will to know the number of people before her. So she asks Bob, which is a person just right before her, could you please tell me the number of people before you? So what is important to realize at this point is that Bob faces exactly the same problem at this point. So Bob somehow computes that the number of people before him is 239, for example. So at this point, Alice knows that the number of people before her is equal to 240, right? And this can be implemented at the following very simple code. So we call this procedure number of people before some person in a line. So it is implemented as follows, just as 4 simple lines of code. If there is nobody before this person, then we just return 0, of course. Otherwise, there is a person before A, let's call him B. So what we do, we first make a recursive call for B. By saying recursive call, I mean the call for exactly the same function, because we need to compute we need to perform exactly the same computational task. So we make this call, it returns us some result, we add 1 and then we return it. Okay? So another very standard example is the following, is computing the factorial function. So the factorial of a positive integer n, it is denoted as follows, so pronounce it n factorial, is by definition equal to the product of all positive integers from 1 to n. So for example, 5 factorial is equal to 1 times 2 times 3 times 4 times 5, which is equal in turn to 120. And you can notice that it is actually the same as 1 times 2 times 3 times 4 multiplied by 5. But this is just 4 factorial, right? Just by definition, right? So this can be as well expressed as 4 factorial times 5. And this gives rise to the following recursive definition. So n factorial is equal to 1 when n is equal to 1, or it is equal to n times n minus 1 factorial when n is greater than 1. So it is a recursive definition because it defines n factorial, so it defines a function in terms of itself. So it expresses n factorial through n minus 1 factorial, right? So a recursive definition defines an object in terms of itself. A recursive program calls itself. So when we have such, and at the same time, if you can continue this further, right? So n minus 1 factorial is also n minus 1 times n minus 2 factorial. And n minus 2 factorial in turn is n minus 2 times n minus 3 factorial. So we somehow need to ensure that this process of calling itself will terminate at some point, that there will be just a finite number of steps. So we need to somehow ensure this, and we will get back to this just in a minute. So before this, let's first implement a very simple program for computing the factorial, and we first turn its basic definition into an iterative program. So here we first make a check that n is indeed greater than 0, then we just declare some new variable which is going to store our result, and then we iterate through all possible values from 1 to n. This is down here, and we, for each such value, we multiply the result by it, and finally we return the result. So this is iterative program. Okay, and in turn the recursive program gives rise to the following recursive procedure. Again, we first check that n is greater than 0. Right? Then if n is equal to 1, then we immediately return 1. In this case, there is nothing to compute, of course. Otherwise, we return n times the factorial of n minus 1. So what will happen here actually during this recursive call is that first the factorial of n minus 1 is going to be computed. Then it will be multiplied by n, and then it will be returned. So this way we transformed our recursive definition into a recursive program. And once again, the way we ensure it that the number of recursive calls is going to be finite in this case is exactly because we have this base case, the so-called base case. So with each recursive call, n decreases by 1. So eventually it will hit 1, and at this point our recursive procedure will return 1 and will stop producing new recursive calls. Okay, so termination is important, and usually it is achieved, as we've discussed already, by keeping track of some parameter and by ensuring that it always decreases and that at some point it will hit a base case. Okay, so when we were computing the length of the line, we actually why our recursive procedure will eventually stop? Well, just because with each recursive call we get closer to the head of the line. Or put it otherwise, the number of people before the current person, it always decreases by 1, right, with each recursive call, and it cannot become negative. And when it is 0, we actually return. We stop producing new recursive calls. And similarly for n factorial, when computing factorial, so n always decreases by 1 with each recursive call, and when it hits 1, we just return. Okay? Let me also show you several examples of a recursion, of an infinite recursion. So the first one is shown here. So here, instead of decreasing n with each recursive call, we actually increase it. So what happens here is that it will produce just an infinite number of recursive calls, an endless process of calling the same procedure. So in theory, such a program will never stop. So n will be increased to infinity. In practice, if you run this program, so what you get, so it will crash and you will get either stack overflow message or message like maximum recursion depth exceeded. Okay? A little bit more examples. So, for example, this is the same program for computing factorial, where we just forget to add the base case. So in this case, what is going to happen? Again, this is an infinite recursion, so it is going to be infinite just because there is no base case. If you call, for example, factorial 5, it will make a recursive call for factorial 4, then factorial 3, factorial 2, factorial 1, then factorial 0, minus 1, minus 2, minus 3, and so on. It will never stop. Another possibility for an infinite recursion is the following. So in this case we have some base case, however we do not change the parameter. The parameter does not decrease. So if you call factorial 5, it will call factorial 5 again and again and again and again and again, so forever. Okay? Finally, two more jokey examples. So there is a standard joke that to understand recursion, you must first understand recursion, which again puts you into an infinite loop. So if you would like to start understanding recursion, according to this rule, you must first understand recursion. But to understand recursion, you must first understand recursion, and so on. And finally, an example by Google. You know that in Google there is this spell checking property or suggesting feature, which if you make a typo in your search query, it will fix it for you and ask whether you mean the following. So if you type recursion, the Google will ask you, did you mean recursion? And this is clickable actually, and if you click, you will get to the same page and it will ask you again, and then you will click again and again and again, an endless number of times. Now consider the following coin problem. So our goal is to prove that any integer amount starting from 8 can be paid using coins of denominations 3 and 5. Okay, so this is our problem, and let's try to investigate. So first of all, let's check whether 8 and 9 and 10 and 11 can be indeed paid. So this looks reasonable. Yes, 8 is 3 plus 5, 9 is 3 plus 3 plus 3, 10 is 5 plus 5, 11 is 3 plus 3 plus 5. So it seems to be possible. However, it is still not at all clear whether it is possible for all values. It is also not at all clear why are we talking about this problem in the lesson called recursion, because recursion was about programs or about definitions. At the same time, what we're going to do is to prove this, prove that this is possible using recursion. And in fact, we're going to implement a program that is going to change any such amount into coins of denominations 3 and 5. So for this, as usual, let's think about this problem. So we know already that we can pay 8. But this immediately gives us that we can also pay 11, right? Because 11 is just 8 plus 3. So in a sense, we reduce the problem of changing 11 into coins to the problem of changing 8 into coins. But for 8, we already know that this is possible, which means that for 11, it is also possible. Moreover, if you know how to change 8, then by adding just one single coin, you have a change for 11, right? And also 11 in turn gives 14, then 17, then 20, and so on. So an infinite number of amounts can be changed into coins 3 and 5 just because 8 can be changed into 3 and 5, right? Then we do the same trick with 9. So since we know how to change 9, then we know how to change 12, 15, 21, and so on. And 10 gives us 13, 16, 19, 22, and so on, right? So this gives us the possibility to implement the following recursive procedure. We call it change, and it is given an amount that we need to change. And the first thing to do, we check whether the given amount is indeed greater than 8. Right? Then if it is equal to 8, then we just return the representation of 8 as the sum of 3 and 5. So we just return a list of two coins. If it is equal to 9, we return 3 coins, 3, 3, and 3. If it is equal to 10, we return 2 coins, 5 and 5. On the other hand, if it is greater, then we do the following. We first subtract 3 from the amount. Then we make a recursive call, which returns us the set of coins needed to change the amount minus 3, right? So we make a recursive call, we solve the same computational problem. So at this point, we have some subset of coins, some list of coins that sum up to amount minus 3. So if we add just one single coin with denomination 3, then we have a change for the whole amount, right? And this is exactly what we do here. We append 3 to coins and we return the resulting list. Okay, so this is a recursive program which changes any amount, and the fact that it changes any amount is guaranteed by the fact that if you get any number which is greater than 8 and you start and you keep subtracting 3 from it, then at some point you will reach either 8 or 9 or 10, right? So for this reason, this algorithm actually proves, this program proves that any amount can be changed using coins with denominations 3 and 5, and it actually proves this constructively, meaning that it not only proves that it is possible, it actually produces the answer for each possible amount. Our final example is the well-known Hanoi Towers puzzle. In this puzzle, we're given 3 sticks. 2 of them are initially empty. On the first stick, we have n disks, sorted by size as shown here on the slide. Our goal is to move all n disks to some other stick, to one of the 2 empty sticks. This would be easy if not the given 2 constraints. First of all, we are allowed to move only 1 disk at a time. And naturally, we need to take the topmost disk from one stick and to put it to some other stick. Right? And also, we are not allowed to put a larger disk onto a smaller disk. Okay? So the question is whether it is possible for, and if it is possible, then for which values of n this is possible. Okay? So it is known to be possible for every value of n. At the same time, it is not clear at this point how can we be sure that it is possible for every possible value of n. We can check that it is possible for 1, for 2, for 3, for 4, and so on, but it is not so clear how to ensure that just for every even very huge number it is always possible. And of course we are going to use recursion again to show how to do this for every possible value of n. For this, we will first explain that it is possible when n is equal to 1. And then we will show that if it is possible for n minus 1, for example, then it is possible for n. This will ensure that if it is possible for 1, then it is possible for 2. If it is possible for 2, then it is possible for 3. If it is possible for 3, then it is possible for 4, and so on. So our goal is basically to show that it is possible in the beginning when n is equal to 1, and then we need to show some generic procedure of building a solution for n disks using a recursive solution for n minus 1 disks. Okay, so let's start. So the simplest possible case is indeed when there is just one disk. So in this case, n is equal to 1, and our goal is to move this disk to some other place, to some other stick, and of course it is very easy to do this. So we just move it to another stick. Now let's also consider 2 disks, just to get a feeling on how to solve this problem. Now in this case, we first move the smallest disk. So we move it to this stick, then we move the larger disk to another stick, and finally we move the smaller one onto a larger one, right? So for 2 disks it is also possible. Now let's consider a general case where we have n disks, and let's focus on the larger disks, on the larger disk, I'm sorry. So what is the condition under which we can move it? So first of all, if we are moving the larger disks, this actually means that all the remaining n-1 disks are already on some other stick. So probably a part of them are on one disk, and all the remaining of them are on the third stick. I'm sorry. So if we are moving this larger disk, so for which stick we can move it? So I'm claiming that the only stick for which we can move it is the empty stick, right? Because if there are any disks on this stick, then we will violate the rules. If there is at least one disk, I'm sorry, on this stick, then by moving the largest disk to this stick, we will put a larger disk onto a smaller one. So this means that when we are moving the largest disk, we should move it to an empty stick, which in turn means that all the other disks at this point should be should be put to the same stick. And since we know that all the disks are always in increasing order, we know that at this point all the other disks should be located as follows, right? So when we are moving the larger disk, all the remaining disks should be at some other state, which means that up to this point we've moved all other n-1 disks. So we actually solved a problem for n-1 disks, right? And this gives us an idea for a recursive solution. Because this is essentially the same problem which was solved for n-1 disks. So a recursive solution in this case is the following. So we first move n-1 disks recursively to some other state. So then we reach the following state. After this we move the largest disk. Okay? And then finally we move once again the n-1 disks, again using a recursive call. Okay, so we know how to do this because we can call the same procedure with parameter n-1, and this finally gives us a solution, right? So we reduced the problem with parameter n to the problem with parameter n-1. This problem in turn will be reduced to a problem with parameter n-2, then with n-3, and so on, until we reach 1, and for 1 we know that it is possible, right? So essentially what we've proved is that it is possible for every value of n. We can consider this, for example, like this. We know that it is possible for 1, then it is possible for 2, right? Then, since it is possible for 2, it is also possible for 3. And so on. So it will be possible for all the numbers. Or put it otherwise, to solve the problem for n, we need to solve it for n-1. To solve the problem for n-1, we need to solve it for n-2. Meaning that if we know how to do this for n-2, then we definitely know how to do this for n-1, and so on. So going backwards, we will reach 1, and for 1, we know that it is possible. So which actually proves that it is possible, and what just happened is that actually we've proved that it is possible by induction, which is a highly related notion to recursion. So saying very roughly, induction is a mathematical method for proving something, while recursion is a method of defining something or a method of implementing something.
Hi, I'm Michael Levin, and in this lesson we're going to study mathematical induction. It is a very powerful proof method. It is very similar to this example with falling dominoes. You know that if we put many dominoes on the floor, so that the second domino is right in front of the first one, and the third one is right in front of the second one, and so on, and then we push the first domino, it will fall, and it will push the second one in front of it, and that domino will also fall, and it will push the third one, and so on, and then all the dominoes will actually fall. And we can check that for maybe 1 domino, 2 dominoes, maybe 5, 100 or 1000, but how to prove that for any number of dominoes? It seems obvious from your practical life experience, but actually to prove that strictly that even 1,000,000 dominoes will fall, we will have to think about what happens in the general case. So we know that if we push the first domino, it will fall. And also what we know is that if some domino on position k falls, it will push forward the k plus first domino, and that one will also fall. And from that we can conclude that if we push the first one, then any domino in the row, even 1000th and even the 1,000,000th, all of them will fall. And mathematical induction is a proof method which is based on the same principle. And there are a lot of problems, hard problems, which can be proven only using these kinds of methods like mathematical induction. And many computer science algorithms are actually proving using induction. And we will start with an example of lines and triangles. We will consider the following problem. Several straight lines are drawn on a plane and in a sense they cut this infinite plane into pieces. And you can see an example on the picture. We have 4 lines there, and we have many pieces between segments of those lines. Some of those pieces are infinite, and some of those pieces are finite. And we require that each line intersects with every other line, so there are no parallel lines, and also all the intersection points are different, so that no 3 lines intersect in the same point. And what we want to prove is that there must be at least one triangular piece. In this picture we actually see 2 triangular pieces, the one below and the one above. And we state that if all the conditions are met, if every 2 lines intersect and there are no points where at least 3 lines intersect, then there always will be at least one triangular piece. So how to prove this statement? Well, we have the following idea. As soon as there are 3 lines, we know that those 3 lines cannot intersect in one point, and from that it immediately follows that if there are exactly 3 lines, we will have a triangular piece formed by those 3 lines. And then, if we have more lines, then we can actually imagine that we have first only 3 lines, some of those lines we have, some 3 first lines, and we can choose them arbitrarily. And then we're going to add more lines one by one. And when we add more lines one by one, every time either the same triangular piece that already existed before adding that line remains, if that line doesn't touch this piece and it remains intact, or a new triangle appears. And this is the general idea. So we start with 3 lines and we immediately get a triangle, and then when we add one more line, either it doesn't touch this piece and the triangle remains, or a new one appears. Let's see how that happens. So when we have just 3 lines, in the general position they form a triangle because each of them intersects another one, and we have 3 points of intersection. And we require that those 3 points are different, and so those 3 points together with those lines form a triangle, which is highlighted with orange here. So there is a bad case where there is no triangle, but in this case we have this common point of intersection of 3 lines, which is what we forbid. So this cannot actually happen in our problem statement because we forbid 3 lines to intersect in the same point. So this cannot happen, and so if we have exactly 3 lines, we will have a triangular piece indeed. What happens when we add one more line? So now we have just 3 lines and we are adding one more, so it will be the 4th line. And as we have 3 lines, we have this highlighted triangle. Now, we add, for example, such 4th line. And we see that it intersects the triangle. But let's see how does it intersect the triangle. So it goes somewhere from the left, and then it goes and goes, and then at some point it intersects one of the sides of the triangle. And then it is going inside the highlighted triangle. And it goes and goes, and then it intersects the triangle again and goes out of the triangle. And then it goes to the right to the infinity. And this is what always happens. Line goes until it intersects some side of the triangle, and note that it cannot intersect the side exactly in the vertex, because that would be a vertex where 3 lines intersect, the 2 sides of the triangle and the new line, so that cannot happen. So the new line always intersects some side of triangle somewhere in the middle. Then it goes inside the triangle, and we know that in the end, when it goes to the right, at some point it will be again outside of the triangle. So it has to intersect a triangle twice, not just once, but twice. So if a line intersects a triangle, it intersects it in 2 points, and it intersects 2 of the sides. So if we take these 2 points and the vertex where these 2 sides intersect themselves, those form a triangle, and this is actually the new triangle that will appear when we add a new line that intersects the current triangle. So every time we add a new line that intersects the current triangle, a new triangle is formed. What happens if we add another line, the fifth line? In this case, this fifth line doesn't touch the existing triangle which exists after 4 lines. So when it doesn't touch, we can just say that this same triangular piece remains intact, and so when we're going from 4 lines to 5 lines, the same triangle exists. Now let's consider the general case. In the general case, there can be many lines, and of course sometimes we can spot the triangle with the naked eye, but if we add many more lines, like thousands of them, it will be very hard to find a triangle by our naked eye. And we need to somehow prove for ourselves that for any possible positions of those lines which satisfy our requirements, there will be actually a triangle. So in general, we're going to do the following. We assume that we have already added some number of lines, maybe 3, maybe 4, maybe 100, and up to this point some triangular piece existed. And we're going to add new lines one by one, and we can get actually any picture with many lines we can get by adding them one by one in some order, and the order doesn't matter to us, so we just select some order, we add first 3 lines and then we add 1 more line at each step. So we assume that at some point when we added, for example, 100 lines, there was some triangle, and here is this triangle highlighted with orange. And we are focusing exactly on that triangle. We forget about everything to the side from this triangle. We only know that no lines intersect this triangle because this is a whole piece. And we know that there are a lot of lines going here and there on the plane, but we don't need them to make our proof. So there is a triangle, and now we're going to add 1 more line. And if that line intersects this triangle, then we already know that it will intersect 2 sides of the triangle, and a new triangle will be formed like this. So this happens not only when we have 3 lines, it happens whenever we already have a triangle, and it may be with 3 lines or 100 lines or 1 million lines. That doesn't matter. Still, if the new line intersects our current triangle, a new triangle appears. Otherwise, if we have a triangle and the new line doesn't touch it, then this triangle just remains. So in the general case, it happens the same way as in the case of just 3 lines. Now we're ready to prove with mathematical induction the following theorem. For any n greater or equal to 3 and any n straight lines on a plane, if every 2 of them intersect and all the intersection points are different, then there is a triangular piece among the pieces into which these lines cut the plane. So let's see the structure of the proof. First, we prove that for any 3 lines that satisfy our requirements, there will be a triangle. Then we can make a step from 3 lines to 4 lines. We note that to get any 4 lines on a plane, we can actually first get some 3 of them on the plane and then add the 4th on top of it. And we assume that for any 3 lines on the plane there will be a triangle. Given that, we prove that for any 4 lines there will be a triangle. To do that, we remember that when we add a new line, either a new triangle appears or the same triangle stays. So we can prove that if for n equals 3 our statement is true, then it is true for n equals 4. And we already know, because we proved it separately, that for n equals 3 the statement is true. So now we can make the step from 3 to 4, and we know that for any 4 lines there will be a triangle. Now we want to make the next step and prove that for any 5 lines there will be a triangle. To do that, we prove a step from 4 to 5, that if we assume that for any 4 lines there is a triangle, then we can prove that for any 5 lines there will be a triangle also. To do that, we say that any 5 lines you can get by first selecting some 4 of them, drawing them, and then adding the 5th one on top. By the assumption of our induction, for those 4 lines there will be some triangular piece. And when we add the 5th line on top, either the same triangle remains or a new triangle appears. So, for those 5 lines, there will also be a triangle. And so, we know that if for 4, n equals 4, our statement is true, then it is also true for n equals 5. And we actually already know that for n equals 4, the statement is true. So now we know that it is also true for n equals 5. And we can make the same step from 5 to 6. But what we want to do is to make all the steps at the same time. We want to go from 6 to n for any integer n which is greater or equal than 3. To do that, instead of doing one step at a time, which would take for us infinite time, we prove a more general thing. That if for some k, we have proven that for any k lines on the plane there is a triangle, then for any k plus 1 lines there will also be a triangle. And to do that, we say that to get any k plus 1 lines, we can first select some k of them, draw them on a plane, and then add the k plus first one on top of it. We know that for those k lines there will be a triangle, and we know that when we add the k plus first line, either this triangle remains or a new triangle appears. So, if for k the statement is true, then it is also true for k plus 1. And as soon as we have proven that in the general case, from k to k plus 1, we can actually make this step from 6 to n. And actually, we didn't need to prove the intermediate steps from 3 to 4, from 4 to 5, from 5 to 6. We could just go directly from 3 to n as soon as we have proven this general case from k to k plus 1. And this is how mathematical induction works. So, our proof as a whole consists of the following parts. First, we prove what is called induction base. This is the basic statement for some smallest value of n for which we need our statement. In this case, n equals 3 and 3 lines. We prove that there will be a triangle for 3 lines. Then, we prove that if our statement is true for n equals 3, then it is also true for n equals 4. After that, we prove that if it is true for n equals 4, then it is also true for n equals 5. And so on. And then we prove the more general thing, which is called induction step, from n to n plus 1. We prove that in the general case, if for any n lines there is a triangle, then for any n plus 1 lines there is a triangle. And then after we've proven both the induction base and induction step, we actually have the profit we needed. We have proven the whole theorem, the whole statement. And actually, we can shorten this path a little bit, and what we'll get is that we actually need to do only 2 things. Prove the induction base, in this case n equals 3, and prove the induction step from n to n plus 1 in the general case. We don't need these intermediate steps from 3 to 4, from 4 to 5, and so on. Just prove the general induction step. And if we have proven those 2 things, then we have proven our theorem. And we will see more examples of that in the next videos. Hi! In this video, we're going to consider 2 problems about connecting points. And actually, I assume that you have just worked on 2 interactive quizzes that we've prepared for you, and those quizzes contain 2 problems, one of them about 10 points and connecting them with segments, and another one about 9 points. If you haven't yet tried to solve those quizzes, I encourage you to go back and first try to solve them and then return and hear this lecture, because we're going to discuss the solutions to those problems, and it is very useful to first try to solve problem yourself before hearing and discussing the solution. So the first problem goes like following. We have 10 points on a plane. They're arranged in a beautiful symmetric manner, like a circle. And you need to connect some of these 10 points with segments, like 2 pairs of points which are connected on this picture, such that every point is connected exactly with 5 other points. The solution for this problem is also beautiful and symmetric. The idea is we can separate the points into the left half and the right half with this vertical line, and each half has exactly 5 points. And now what we need to do is to connect each point from the left half to each point of the right half. And we will get such picture, which is beautiful and symmetric, but the main thing is that this is the solution to our problem, because for every point in the left half, it is connected exactly to 5 points from the right half. And for any point in the right half, it is connected exactly to the 5 points from the left half. And the points in the left half and in the right half are not connected between themselves. So, for all 10 points, every point is connected with exactly 5 points as needed. So, this is one of the possible examples. I'm sure that some of you came up with other examples, but it is sufficient to show just one example for this problem. And now we move on to a very similar problem about 9 points. So now you're given 9 points instead of 10. They're also organized in this symmetric circular manner. And you also need to connect some of them with segments, so that each point is again connected with 5 other points. And now we ask you, is that possible at all? So, to solve this problem, we first need to introduce some definitions. Numbers from 0 and integer numbers starting from 0, 2, 4, 6, 8 and so on are called even, and all the other positive integers starting from 1, 3, 5, 7 and 9 are called odd. So all even integers are going with the difference 2 between them, and all the odd integers are going with difference 2 between them. And all even numbers are divisible by 2, meaning that if you divide any such even number by 2, you will also get an integer number. And all the odd numbers are not divisible by 2. Now, we are going to call points A and B neighbors in this particular problem if A and B are connected with a segment. So in our problem with 9 points, some of them will be connected by segments, some of them won't be. If 2 points are connected with a segment, they are called neighbors. And if B is neighbor of A, then A is also a neighbor of B. This is symmetric. And now we're going to define even and odd points. So let us call a point even if it has even number of neighbors. Otherwise, we call this point odd. So, looking at this particular picture with 9 points, and some of them are connected with segments, how many odd points and how many even points are there? So the answer is that there are exactly 4 odd points, and those are A, B, C and D, because each of them is connected to just one other point, and so the number of neighbors for A, B, C and D is 1, and 1 is odd number, so points A, B, C and D are odd points. All the other points are even. Points E and F have no neighbors, so they have 0 neighbors, and 0 is an even number, so E and F are even points. And points G, H and I are all connected to each other, and so each of them has exactly 2 neighbors, and 2 is also an even number. So G, H and I are also even points. And now I state that theorem that the number of odd points is always even, regardless of how many points are there, and how many segments are there, and which exactly points are connected, which points are not connected by segments. That all doesn't matter. In any case, the number of odd points is always even. So number of odd points is either 0 or 2 or 4 or 6 and so on. And we're going to prove this theorem now. The idea of the proof is very similar to the idea from the previous video. We start with the obvious statement that when there are no segments, there are no odd points, because no points have any neighbors, so every point has exactly 0 neighbors, and so every point is even. And to go to the general case when we have some points connected with segments, we can actually start with the situation when there are only some points and no segments, and then we add segments one by one. And the key idea is that when we add segments one by one, the number of odd points either doesn't change at all, or increases by exactly 2, or decreases by exactly 2. And thus the number of odd points, if it was even at some point, it stays even, because when you don't change a number or change it by plus or minus 2, it remains even. This is the idea, and now let's go through and prove it. So the easy case is when there are some number of points, and it doesn't matter how many points, and there are no segments. Then each point has exactly 0 neighbors, and so there are no odd points. And so the number of odd points is 0. 0 is an even number, so there is indeed even number of odd points. So we have proven this simple case. As you remember, this is called induction base, and we will use this for our proof. And now we need to also prove the induction step. And to do that, we need to consider what happens when we add segments. And let's start with 9 points and try to add some random segments and see what happens. So when we start, the number of odd points is 0 because there are no neighbors, and so each point is even. What happens when we add segment A and B? Well, it connects points A and B, and now point A has one neighbor and point B has one neighbor, so A and B become odd points. And before we added segment AB, there were no odd points, and now there are 2 odd points, so the number of odd points increased by 2, and now we have exactly 2 odd points, and all the points other than A and B are still even. Now let's try adding segment HI. It again adds 2 odd points, H and I, because it connects H and I to each other, and now both of them have exactly one neighbor. 1 is an odd number, and so H and I are now odd points. And so again we increase the number of odd points by 2, and the total number of odd points is now 4. Now what happens if we add segment BC? Now something different happens. Because B was odd before adding this segment and C was even. Now when we add segment BC, they switch. Now B is even and C is odd. Why is that? Because B now has 2 neighbors, A and C, and so B is an even point now, and C has only one neighbor, B, and so C is an odd point. And in this case we added 1 odd point and removed 1 odd point, so the number of odd points didn't change. We again have 4 odd points, and those are A, C, H and I. Now we want to add segment AC, and this will make both points A and C even, because now A has 2 neighbors, B and C has 2 neighbors, A and B, and so A and C now are even, and they were odd. So we have just decreased the number of odd points by 2, and now we have only 2 odd points, and those are H and I. So you see what happens. For any segment in this example, at least, when we added it, it either didn't change the number of odd points, or it increased the number of odd points by 2, or it decreased the number of odd points by exactly 2. Now let's consider what happens when we're adding a segment in general. And again, we're going to focus only on the 2 points which this segment connects, the same way as we focused on the triangle that existed in the previous video. Why is that? Well, because when we add a new segment from point A to point B, then all the other points don't change. The number of neighbors for all the other points doesn't change, and so the number of odd points among all the other points also doesn't change. The only thing that changes is maybe the oddity of point A and the oddity of point B. And now we consider several cases. First case is when before adding segment AB, A and B were even points. Then AB makes them both odd, because A and B both had even number of neighbors, and now both of them have by one neighbor more, and so those even numbers, after adding 1 to them, became odd, and so A and B now both have odd number of neighbors, and so A and B are now odd points. They were even, they became odd, so we added 2 more odd points in this case. Now, the second case is if A and B were odd before adding segment AB. In this case, adding AB makes them both even, because they had odd number of neighbors. Now they have each 1 more neighbor. If you add 1 to an odd number, you get an even number. And so A and B now have even number of neighbors, and so A and B are now even points. So they were odd and now they're even, so we removed A and B as odd points, so we removed exactly 2 odd points. And the third case is when A is even and B is odd before adding segment AB. In this case, adding segment AB swaps them, A becomes odd and B becomes even. Because A was even, it has even number of neighbors, and after adding segment AB it has 1 more neighbor, and so it becomes odd. And for B it's vice versa, it was odd, we add 1 more neighbor and it becomes even. And so we removed 1 odd point and we added 1 odd point, and so the total number of odd points stays the same. And the fourth case would be when A was odd and B was even before adding segment AB, but this is actually symmetric, and in this case also the number of odd points stays the same. So what we see is that after adding a segment in general, the number of odd points always either increases by 2 or decreases by 2 or stays the same. Now we're ready to prove the whole statement about points that always, regardless of number of points and number of segments and which points are connected and which are not, the number of odd points is always even. The proof structure is the following. First, we prove that when there are no segments, then disregarding number of points, the number of odd points is always even. Because actually the number of odd points is 0 and 0 is even. So for 0 segments we have proven our theorem. Now we're going to do induction based on number of segments, and we're going to make a step from 0 segments to 1 segments. We assume that for 0 segments the number of odd points is always even, and we prove that in that case for any 1 segment, if there are some number of points and exactly 1 segment connecting some pair of points, the number of odd points is also even. And to do that we use the fact that when we add a segment, the number of odd points, if it was even, it stays even. And we know that it was even with 0 segments, so after adding this 1 segment it stays even. And so we now know that for 1 segment our theorem is also true, because we know that for 0 it is true, and assuming that for 0 it is true, we have proven that for 1 it is also true. And so on, we can go from 1 segment to 2, because if we want to prove something for 2 segments, we can choose one of them to be the first one, and then we know that if we just add only this first segment, the number of odd points will be even. And then after we add this second segment on top of it, the number of odd points will stay even. So for any 2 segments, the number of odd points is also even. And then we can make the step from 2 to 3 and so on, but we want to make all the way to n. And to do that, we prove the general thing, that if for some k, for any k segments connecting some number of points, number of odd points is always even, then for any k plus 1 segments and any number of points connected by those k plus 1 segments, the number of odd points will also stay even. And this step can be proven in the same way. We know that in the general case, when we add a new segment, the number of odd points stays the same or is increased or decreased by 2. So if it was even, it stays even. And given this induction step from k to k plus 1, we can make the step from 3 to n. And we could skip all those intermediate steps from 0 to 1, from 1 to 2, and so on. We could just prove that for 0 segments our theorem is true, and this step from k to k plus 1 in the general case, and that would already allow us to go from 0 to any n. And actually we can skip all those intermediate steps and just prove the induction base for n equals 0, prove the induction step from n to n plus 1, and we get the profit. We have proven our theorem. Now let's remember, why did we need this theorem? We had a problem about 9 points. We had 9 points and we wanted to connect some of them with segments in such a way that every point has exactly 5 neighbors. So let's suppose we succeeded. Then all 9 points would be odd, because each of the 9 points has 5 neighbors. 5 is an odd number, and so the point is odd, and so all 9 points are odd. But then the number of odd points will be 9. But we know from the theorem that for any configuration of segments, the number of odd points must be even. And 9 is not even, so it is impossible. And indeed, for 9 points, it is impossible to find a solution. So for 10 points, we have shown an example how to connect them in a nice symmetric way so that each point has exactly 5 neighbors. But for 9 points, it is impossible. We could try proving it by drawing every possible combination of segments for 9 points and showing that it doesn't satisfy a requirement that there is at least one point that doesn't have exactly 5 neighbors. But instead of doing that, that would take a ton of time. Instead of doing that, we have proven, using mathematical induction, some supportive statement about the number of odd points, that it is always even. And then, based on that, we proved that this problem cannot be solved. And in the next video, we're going to talk about a famous mathematician and a problem that his teacher gave him in school. Hi! In this video we're going to talk about sums of numbers, and we'll invent a short formula to compute sums of integer numbers really fast. But first I will tell you a story. This man, Carl Friedrich Gauss, is often called the Prince of Mathematicians because of many things that he proved and many theories that he developed. His impact on mathematics is huge. And the story is actually about his childhood. So when he studied in school, his teacher was often annoyed by this boy who was always solving all the problems, always raising his hand, always talking, and he wanted to actually try to teach other students in his class. And so he wanted to somehow get rid from Gauss for some time to explain something to students which are not so quick. And he came up with an idea, and he gave Gauss what he thought was a pretty hard problem. Not hard in terms that Gauss wouldn't be able to solve it, but hard in terms that it will keep him busy for some time. So he asked him to sum all the numbers from 1 to 100. And what teacher imagined was that Gauss will have to sum these numbers one by one, and he will make mistakes in the middle, and he will use a lot of paper to do that, and then it will keep him busy probably for the whole lesson, and so the teacher will be free to actually explain something to other students. But it didn't happen that way. Actually, after thinking for maybe 2 minutes, Gauss came up with an answer. And teacher was very suspicious about getting this answer because he didn't know the way to get the sum so fast. But then he checked the solution and it turned out to be correct. We're going to solve this problem, but we're going to generalize a little. We're going to solve the problem of what is the sum of all integer numbers from 1 to n for any n. And the theorem below states that the sum of these integers from 1 to n can be computed using this simple formula with one multiplication and one division, n times n plus 1 divided by 2. And we are going to prove this theorem now. To do that, we will use proof by induction, which you already know from the previous two videos. To prove something by induction, we need two things: to prove induction base and induction step. And induction base in this case is for n equal 1. And if n is equal to 1, then the sum of numbers from 1 to n, 1 plus 2 plus and so on up to n, is actually just one summand. And the formula gives us the answer that the sum should be equal to 1 times 2 divided by 2. And this is actually correct. So for the easy case, for n equals 1, we have proven our theorem. This is true. Now let us make the induction step from n to n plus 1. We assume that the formula works for some n, that the sum of numbers from 1 to n is equal to n times n plus 1 over 2. And we want to prove the same thing for n plus 1. So what happens is we write down the sum from 1 to n plus 1, and then we use the assumption of the induction that the sum of the first n numbers is equal to n times n plus 1 over 2. So this exclamation mark above the equality sign is the marking that we use the assumption of the induction. And also, we need not forget the last summand, which is n plus 1. So we add n times n plus 1 over 2 plus n plus 1. We get both summands to the common denominator 2, and in the numerator we get n times n plus 1 plus 2 times n plus 1. Now we have a common multiple there, n plus 1, and we can rewrite this numerator as n plus 1 times n plus 2, and the denominator is 2. So we see that the formula is the same, but just for n plus 1 instead of n. And so we have proven the induction step from n to n plus 1. And now our theorem is already proven, because we proved both the induction base for n equals 1 and the induction step from n to n plus 1. And so we can go from 1 to 2 to 3 to 4 and to any integer number. So our theorem is true. And now we can understand how did Gauss compute the answer so fast. But the question is, how do you actually come up with this formula in the first place? So when we know the formula, it was relatively easy. We could prove it using mathematical induction, and then we can use it to find the answer. But how did Gauss come up with this, and how can you come up with this? Well, the answer is the following. The Gauss's idea was to write the sum of numbers from 1 to 100 in the forward direction, and then below it in the backward direction, so that number 100 in the backward direction is exactly below number 1 in the forward direction, number 99 is exactly below number 2, and so on. Number 2 in the backward direction is exactly below number 99 in the forward direction, and 1 is directly below 100. So we have these 100 columns. In the first one we get 1 and 100, in the second we get 2 and 99, and so on. And now we want to compute the sum of these two equations. On the left part we will get s plus s, where s is some unknown sum of all the numbers between 1 and 100. So it will get 2s on the left side. And on the right side we can sum the columns independently, and we can notice that sum of the numbers in every column is exactly 101. 1 plus 100 is 101, 2 plus 99 is 101, and so on. So we have exactly 100 columns with number 101 written in each column. So the sum of those numbers is obviously just 100 times 101. And so to get s, which is unknown, we should just divide this by 2, because the left part is 2s, and to get just s we need to divide by 2. So the answer is 100 times 101 divided by 2. And this we can already compute on paper, and it turns out that the answer is 5050. And actually, if we changed 100 to n in this slide, and we made all the same statements, and we made all the same arrangements in the forward direction, in the backward direction, then we would get the formula n times n plus 1 over 2 directly, and it actually would be another way to prove the same formula without mathematical induction. It happens in this case that we actually don't need to use mathematical induction to prove this fact. We can just go directly to the formula, we can see what is the formula, and we will get the proof immediately without proving the induction base and induction step. It sometimes happens that you can prove the same statement different ways, and sometimes it also happens that before you can apply mathematical induction, you first have to come up with the formula. And in this case, while you're coming up with the formula, you can also prove the statement itself. So this is a beautiful example of how children can be very inventive and come up with ideas that older people just don't know of. And this is a beautiful mathematical problem which shows that you can use mathematical induction to prove statements, but you can also come up with different inventive ways and prove statements directly. Hi! In this video we will talk about mathematical fact called Bernoulli's inequality. Bernoulli is a famous mathematician, and this inequality was named after him, and we're going to use his inequality to solve a practical problem, and we will prove the inequality itself using mathematical induction. So the practical problem is, imagine you start with having $1,000 and you earn 2% of what you have every single day. Will you ever get more than $1 million? Well, what happens is on day 1 you have $1,000, and on day 2 you have 2% more, so you have $1,000 multiplied by 1.02. And on day 3 you have that multiplied once again with 1.02, so you get 1,000 times 1.02 times 1.02, which is equal to $1,000 times 1.02 squared. And repeating this, we get that on day n you have 1,000 times 1.02 to the power of n minus 1. Now that we know how much you're going to have every single day, we can reformulate this problem in a mathematical way. The question is there such integer n that 1000 times 1.02 to the power of n is bigger than 1 million? Or we can divide by 1000 the left part and the right part and ask, is there such n that 1.02 to the power of n is bigger than 1000? This is a question because although we get increasing powers of this number is very close to 1, so it will increase really slowly, and maybe it won't get bigger than 2, or maybe it won't get bigger than 10. It is not obvious from the start. Let's see. To see about that, we will use Bernoulli's inequality. The theorem states that for any integer n which is greater or equal to 0, and any positive number x, which doesn't have to be integer, just any positive real number x, 1 plus x to the power of n is greater than or equal to 1 plus n times x. And first, before using this inequality, we're going to prove it. And we're going to prove it using mathematical induction again. First we need to prove base, and the base case in this case is n equals 0. Because we're proving the statement for all non-negative integers n. In this case, 1 plus x to the power of n is equal to 1 plus x to the power of 0, and any number in power 0 is just 1, and this is equal to 1 plus 0 times x, which is equal to 1 plus n times x. So In this case we have equality. We were going to prove inequality, but equality is a particular case because we need to prove that 1 plus x to the power of n is greater than or equal to 1 plus nx, and in case n equals 0 it is just equal. Now we need to prove also the induction step from n to n plus 1, and we assume that for some n we have proven that 1 plus x to the power of n is greater than or equal to 1 plus nx. Now we need to prove for n plus 1. So we look at 1 plus x to the power of n plus 1, and we separate it into two multiples, 1 plus x to the power of n and just 1 plus x. And now we mark with an exclamation the fact that we're going to use the assumption of the induction. And the assumption of the induction is that for n we have already proven our theorem, and we know that 1 plus x to the power of n is greater than or equal to 1 plus n times x. And we can multiply this inequality by 1 plus x. 1 plus x is a positive number because 1 is positive and x is positive, so the sign of the inequality won't change. And so we have that 1 plus x to the power of n plus 1 is greater than or equal to 1 plus nx times 1 plus x. Now we're going to open the brackets, and what we get is 1 plus nx plus x plus nx squared. And now we're going to group nx and x into n plus 1 times x, and we're going to remove the summand nx squared. This summand is positive because x is positive and n is non-negative, so we can just remove this, and we get an inequality that this is bigger than 1 plus n plus 1 times x. And so in the end we get that 1 plus x to the power of n plus 1 is greater than or equal to 1 plus n plus 1 times x, exactly what we needed. So we have just proven Bernoulli's inequality in the general case. Now we're going to apply this inequality to our problem. So we wondered whether there is such big n that 1.02 in the power n is bigger than 1000. So let's take n equals 50,000 and see how Bernoulli's inequality will help us. So 1.02 to the power of 50,000 is the same as 1 plus 0.02 to the power of 50,000. And now we can apply Bernoulli's inequality for n equals 50,000 and x equal to 0.02. And we'll get that this left part is greater than or equal to 1 plus n times x. N is 50,000 and x is 0.02. 50,000 times 0.02 is just 1000, so this is equal to 1 plus 1000, and this is bigger than 1000. So in the end we get that 1.02 to the power of 50,000 is strictly bigger than 1000. And so the answer to our problem is yes. Actually, this number 1.02 to the power of n grows much quicker than you would imagine. And in fact 1.02 in the power of 349 is already bigger than 1000. This is actually the smallest n is 349 when 1.02 is bigger than 1000. And what it means that if you get just $1,000 and you earn just 2% every day from it, you will get more than $1 million by the end of the year. And to make sense of that, we've prepared a separate script with which you can play with this function 1.02 to the power of n, and you can actually change it to 1.01, and you can play with different n, and you see how this function grows. It is an exponential function and it grows really fast, and this is why it is very good if you actually can improve something by 2% every day. You will improve it more than 1000 times in just 1 year. Hi! In this video we're going to study complete induction. It is also called strong induction. So what we've learned so far as mathematical induction is actually sometimes called weak induction, because it is not always sufficient. For some problems you need a more powerful method of induction, and it is called strong induction or complete induction. And we'll apply this method to solve a problem about change and coins. So the problem is you have an unlimited supply of coins with values 4 cents and 5 cents. And you need to prove that for any integer n greater than or equal to 12, you can give change of exactly n cents using only these coins. Note that n starts from 12. This is unusual. Well, that is because if you think about it, for 11 cents, you cannot actually give 11 cents using only coins with values 4 cents and 5 cents. And you can prove this yourself, and we're going to concentrate on proving that starting from 12 cents, you can give any amount of change using only coins with values 4 and 5 cents. Let's try to prove it by induction as we know it. So first we need to prove the induction base, and it is n equal to 12, because this is the smallest n for which we need to prove our statement. And indeed, for n equal 12, we can represent 12 cents using only coins of value 4 cents. We just take 3 coins with value 4 cents, and that's all. Now, we want to prove the induction step, that if we can make change of amount n with coins of 4 cents and 5 cents value, then we can make change of n plus 1 cents. But it is actually unclear how to do that. How can we prove that if change of exactly n cents is possible, then we can get from it to somehow giving change of n plus 1 cents? To do that, we would need to do something like, okay, here is the way to give change of n cents, and we know that it is possible. And now we should somehow change this solution into giving change of exactly n plus 1 cents. But to do that, we would need to give 1 cent using coins with values 4 cents and 5 cents, and that is obviously not possible. So it is unclear how to move from n to n plus 1 here. And this is why the regular weak induction doesn't work in this case, and we need to do a little bit more work. So more work is first bigger induction base. Instead of proving our induction base just for n equals 12, we'll prove it for n equals 12, 13, 14 and 15. So for all these numbers we'll prove manually that these amounts of change can be given exactly using only coins of values 4 and 5 cents. And to get 12 cents we already know that we just need to take 3 coins of value 4. To get 13, we get 2 coins of value 4 and 1 coin of value 5. To get 14, we get 2 coins of value 5 and 1 coin of value 4. And to get 15, we just get 3 coins of value 5. So we've proven the induction base that for n from 12 to 15, it is possible to give the change. Now we're going to prove induction step, but this induction step will be more complex than usual. This induction step will say that if, for some n, we know that n cents, n minus 1 cents, and n minus 2 cents, and n minus 3 cents, any of these amounts can be given as change using only 4 cents and 5 cents coins, then we can also give change of exactly n plus 1 cents. How to prove this step? Well, in particular, from the assumption we know that exactly n minus 3 cents can be given using only coins with 4 and 5 cents. So that n minus 3 can be given as a coins of value 4 cents and b coins of value 5 cents. Then n plus 1 can also be given with these coins because n plus 1 is equal to n minus 3 plus 4. And so basically we get the representation for n minus 3, we get a coins of value 4, b coins of value 5, and we add 1 more coin of value 4, and we get the change of exactly n plus 1. So this is our induction step. Now, how does it actually lead us to proving everything? Because previously we moved from 0 to 1, from 1 to 2, and so on. And here we cannot just move from 12 to 13, from 13 to 14 and so on, we need to do something else. So let's see the structure of the proof in this case. So we get this change amount which starts with 12, because this is the smallest amount for which we need to prove it. And we actually prove manually for 12, and for 13, and for 14, and for 15. And now we also prove the general thing that if for all amounts k, k-1, k-2, and k-3, it is possible to give change with these coins, then it is also possible for k+1. How we can use this induction step to prove for every n? Well, first we can take the values for which we already proven the statement, 15, 14, 13, and 12, and use them as k, k-1, k-2, and k-3, and then k+1 on the right part will be 16. And so from this induction step we get that for 16 it is also possible to give 16 cents using coins of 4 cents and 5 cents. Now we can add 16 to our knowledge base, and we can use 16, 15, 14 and 13 as k, k-1, k-2, and k-3, and then k+1 would be 17. And so using our induction step we can prove that for 17 cents it is also possible to give change using only coins of values 4 cents and 5 cents. And this way we can go to 17, to 18, to 19, and so on. We can get to any n. And so after proving our induction base for 12, 13, 14, and 15, and proving this complex step from k, k-1, k-2, k-3 to k+1, we can move to any integer n, and we have actually proven that for any n that is greater or equal to 12, it is possible to give the change. And so the complete induction comes in one of the two forms. The first form we've just used with you, we first prove the induction base manually for the first k values of n, where k is some parameter that you just choose. So usually in the previous videos it was just 1, but in this video k was equal to 4. So we take first 4 values of n, 12, 13, 14, and 15, and prove manually the base case. And then the induction step is that if the statement is true for n and also n-1 and also n-2 and so on up to n-k+1, so for k integers which go in succession, then we prove it for n+1. If we get this, then we can do the same we did with the coins. So we have the first k values, and from these k values we can move to the k+1 using the induction step. Then we take the last k values of these, and from them we can go to the k+2 value, and so on, so on. So if we have proven base for k values of n, which are successive values of n, and we have proven an induction step from k successive values of n to n+1, then we have proven the whole statement. Another way is, again, we have the same base for some k values of n, but the induction step is even more general. It says that if the statement is true for all previous n, from the smallest to this n, then we're going to prove it for n+1. The quirk is if we explicitly assume in the proof of the induction step, for example, that the statement is true for n-10, if we use this fact to prove on n+1, then we need k to be at least 10. And this is why in this particular coins problem we needed to prove for 4 values manually, because for proving induction step for n+1 we used explicitly that the statement is true for n-3. So we needed to get 4 points to prove that. And this is what complete induction or strong induction means. And this is actually a more powerful method, and later you're going to also solve some problems based on complete induction. Hi, in this video we're going to consider a problem about cutting a triangle into smaller triangles. But first, some definitions. An obtuse triangle is depicted on the image above. ABC is an obtuse triangle, and it is defined as a triangle which has at least one angle which is bigger than 90 degrees. And acute triangle is depicted on the picture below, and it is defined as a triangle where there are no angles which are 90 degrees or bigger. So all the angles are below 90 degrees. And the problem we're going to solve is it possible to cut an obtuse triangle into several acute triangles? So we're going to try to prove this theorem, that if an obtuse triangle is cut into several triangular pieces, then at least one of the pieces is obtuse. So basically we say that it is impossible to cut an obtuse triangle into acute triangles. And this theorem actually sounds very similar to the first problem we're solving with mathematical induction about cutting a plane by lines. And let us try to prove this in a similar way using mathematical induction. So something in the lines that if we get just one piece, then it is obtuse, and if we cut into more pieces, then at least one of them will be also obtuse, and so an obtuse triangle will always stay. The same way as it was with triangular piece among the pieces into which lines cut the plane. So let's prove this theorem by induction, and the induction base is very simple. N equals to 1, so the initial triangle is obtuse, and we cut it into only one piece, so this piece has to coincide with this initial triangle, and so it is also obtuse piece. So it is true that if we cut obtuse triangle into one piece, then there is an obtuse piece. Now we need to prove the induction step from n to n plus 1. And by assumption of induction, if there are n pieces, there is an obtuse piece among them. And now if we cut this piece into two triangles, at least one of them stays obtuse. And to see that, you should look at the pictures below. So to cut a triangle in two, we need to connect its vertex with some point on the opposite side. And depending on which node we connect, we get either the left picture when we draw the line from the angle C, which is obtuse, to some point D on the opposite side. And then the triangle CDB is also obtuse. And actually one of the triangles CDA and CDB always will be obtuse, because sum of the angles CDA and CDB is 180 degrees, and so at least one of the triangles won't be acute, it will be obtuse. And actually the same happens on the right picture with obtuse triangle EFG when we draw a line from node E, which is acute angle, to point H on the opposite side. Actually, nothing really changes, because sum of angles EHG and EHF is 180 degrees, and so at least one of them is not acute. So we see that when we cut an obtuse triangle in two, one of the parts is also obtuse, and so when we move from n pieces to n plus 1, obtuse piece has to stay, because either we don't even touch the obtuse piece that we have among n pieces, or if we cut this particular piece to try and make it not obtuse and try to cut it into acute triangles, we see that at least one of the parts will be again obtuse. So it seems it is not possible to avoid this obtuse piece. And we have proven the induction base, and we have proven the induction step, so we have proven the theorem that it is not possible to cut an obtuse triangle into acute triangles. And now I actually have to come out and tell you that I lied to you. This proof is actually wrong. And can you spot what was wrong in this proof? Well, first let's see this example. So we have initially this big triangle, which is an obtuse triangle, and you see that it is cut into 7 pieces, and those pieces are triangles, and actually all of the pieces are acute. So we have just proven a theorem that states that this is impossible, that we cannot cut a triangle into acute pieces if the initial triangle is obtuse. But on the other hand, we have this example which proves that it is possible to cut this particular obtuse triangle into acute pieces. So what was wrong? The example is obviously correct, so probably something was wrong with the proof, and it is often the case. We have to be very careful when making the proofs to not make some incorrect logic in our proof. So let's look at what was wrong. Actually, the induction step assumed that if we cut a triangle into several triangular pieces, we can do it by several steps of cutting a triangular piece into more triangular pieces, and actually into two triangles. So we proved by induction that if we cut our initial obtuse triangle in a particular way, when every time we take a piece and cut it by line into two triangular pieces, then it is impossible to cut the obtuse triangle into acute triangles. But this is not the only way to cut the triangle. We don't have to always cut the triangle into exactly two pieces which are triangles. We can cut it into more pieces, and in this previous example that I shown you, you see that there is no such thing that we cut our initial obtuse triangle into two pieces. We cut it into 7 pieces at once. And so this is the case that our proof didn't consider. And this is where we're wrong. So the induction step itself is correct, and the induction base itself is correct, but the assumption is incorrect, that the only way we can cut an obtuse triangle into triangles is to cut one by one. This was true when we were cutting the plane with lines, that we can add lines one by one and we can get the same picture in the end. And it was also true for segments connecting the points, that we can add segments one by one and then we will get the final picture. But it is not true that for any way of cutting a triangle into pieces, into triangular pieces, we can simulate this by cutting first a triangle into 2 pieces and then one of those 2 pieces into 2, and so on and so on. This is just not true, because there are different ways to cut the triangle. And so this is an example where mathematical induction actually fails. Well, actually, this is not the fault of mathematical induction. It is faultless. It is our fault that we applied it in a wrong way. And this shows that you have to be very careful. This is a very powerful method, but you have to handle it with care, not to make a mistake. And in the next video, I will show you even more flawed induction proofs, which will show you what not to do. And it is equally important when you have a powerful method in your hands, not only to understand how to apply it, but also how to not apply it when it is not applicable. Hi! In the previous video, we saw a proof by mathematical induction which seemed to be correct until it actually turned out wrong. And in this video, we'll consider a few more flawed proofs based on induction, so that you can get a sense of how you can make a mistake when you apply induction and you can avoid it in your own proofs. So we'll consider a few problems, and we'll illustrate that although induction is a very powerful method, as any power you should apply it with care. And you will see that often proofs by induction only seem to be correct while they're actually faulty. And the first problem is the following theorem. We want to prove that for any number of people, for any n which is at least 1, if we get n people, all of them are of the same age. Well, actually it is obviously a theorem which is wrong, because we know that people can be of different ages, but now we're going to prove it using mathematical induction. And to prove something by induction, as we know, we have to just prove base and step. Base for n equals 1 is obviously true, because we have just one person, this is of the same age as this same person, so the induction base is true. Now we want to prove the induction step from n to n plus 1. By the assumption of induction, for any n people, they are of the same age. And so in particular, if we take these n plus 1 people and we arrange them in a row and take the first n people, those are definitely of the same age. Also, by the same assumption of the induction, the last n people in the row are also of the same age. So we have first n people of the same age and last n people of the same age. And then we have n minus 1 people in the middle, which are of the same age with the first n and with the last n. And then it means that actually all the n plus 1 people are of the same age as the middle n minus 1 people. So all n plus 1 people are also of the same age. And so we have proven the induction step. And we have both induction base and induction step, so we can prove that for one person is also always of the same age, for two persons they're always of the same age, and so on. So we have proven our theorem. Now, from the other hand, we know that the theorem is not true, and we know a lot of people of different ages. So what is actually wrong is something in this proof. Can you spot it? Can you spot what was wrong in this particular proof? Well, it turns out that the induction step was wrong. It wasn't wrong at all. It just breaks for one particular case when n is equal to 1 and we move from 1 to n plus 1, which is equal to 2. Indeed, let's go through this induction step. If we have n plus 1 people, which is equal to 2 in this case, then indeed the first person is of the same age with this same person, and the last person is also of the same age by the assumption of induction. But these two people can actually be of different ages, because the middle n minus 1 people, which we use to prove that the left part and the right part are all of the same age, these n minus 1 people are actually 0 people. So there are no common people between the left n people and the right n people. When I showed you the proof, I showed you like this. N people to the left, n people to the right, here is the intersection, all these people are of the same age, this person is of the same age with them, this person is of the same age with them. But for n equals 1, there is no intersection, there's just one person on the left, one person on the right, and no people in the middle, which could help us to prove the theorem. So this is where this proof breaks. So you have to be really careful when you inspect induction steps. Now let's consider another theorem, that for any non-negative integer n, 5 times n is equal to 0. Now this is also obviously incorrect, because we know that if we take some number like 10 and multiply it by 5, we won't get 0, we'll get 50. So this theorem cannot be true, but we're going to prove it now with mathematical induction. To do that, we first prove the induction base for n equals 0. And obviously, for n equals 0, 5 times n is the same as 5 times 0, which is equal to 0. So induction base is indeed true. Now we're going to prove the induction step from n to n plus 1. And to do that, we will use the complete induction. So we assume that for all values from 1 to n, it is true that 5 times n is 0. And now we want to prove it for n plus 1. So we write n plus 1 as sum of I and j, where I and j are non-negative integers up to n. So we can just somehow make this number divided into sum of two numbers which are smaller and which are also non-negative. And if they are smaller, then they are not bigger than n. And so for them, the assumption of the complete induction is true. And then we see that 5 times n plus 1 is the same as 5 times I plus j. And we can open the brackets and we'll get 5i plus 5j. And we know that I and j are non-negative integers up to n, so the assumption of the induction holds for them. And so 5i is equal to 0, and 5j is equal to 0, and 0 plus 0 is equal to 0. And so we have just proven the induction step. And we have both induction base and induction step, and so our theorem is proven. Now, can you spot what was wrong in this proof? Well, it turns out again that the induction step was wrong. And it is wrong not always, but it is wrong exactly for one particular case when we move from n equals 0 to n plus 1 equal to 1. Indeed, we want to represent n plus 1 as a sum I plus j of two non-negative integers up to n, where n is 0. So I and j should be non-negative and up to 0, but there is only one non-negative integer up to 0, it is 0. And so both I and j would have to be 0, but then 0 plus 0 is 0, and it is not equal to n plus 1. n plus 1 is 1 and 0 plus 0 is 0. So it is actually not possible to break this n plus 1 number into I plus j, where I and j are up to n. It would be possible for bigger values of n, but the induction step already breaks at the step from 0 to 1, so it is not important whether we can make a step from 1 to 2, from 2 to 3, and so on, because already the statement is wrong for n equal 1, because we couldn't prove this induction step, and actually if we take n equals 1, then 5 times n is 5 and it's not 0. So we cannot actually make this step, because we cannot represent n plus 1 as a sum of I plus j, but because it's actually not true. And this was another example of flawed induction proofs. So what you should take away from here is not that mathematical induction is a bad thing and you shouldn't use it. It is actually that you should be very careful when you're proving your induction steps. Usually the induction base is kind of obvious, you just need to prove something for a particular value of n, and you typically prove it by hand and it's more or less obvious. But when you're proving the induction step, you should really check that your assumptions can be true, that you can use the statement that n minus 1 middle people are of the same age, or that n plus 1 can be divided into two summands which are non-negative and up to n, and things like that. So you should check that you don't use the assumption of induction for n minus 3 when n is n should be non-negative and n is less than 3. So there are many ways how you can spoil your proof, and you have to be careful in this proofs of induction steps, and maybe you should test those proofs with a few small values of n just to make sure they're correct. You only need, in theory, to prove base case for the smallest value of n, or if you're using complete induction, maybe for several. But to be sure that your proof goes well, you could also try to check it for particular small values of n and see that it goes through. Hi! This is the final video about mathematical induction, and we're going to consider a harder problem here. And this is actually a good example of a problem where it is unclear how to solve it without using mathematical induction. The problem is the following. We need to prove the equality of an alternating sum and a regular sum. The alternating sum on the left is 1 minus 1 over 2 plus 1 over 3 minus 1 over 4, and so on, with alternating pluses and minuses up to 1 over 99 minus 1 over 100. And the sum on the right is from 1 over 51 plus 1 over 52 and up to 1 over 100. It is really unclear how to solve this problem directly, because we could of course try to get all the fractions to the common denominator, but this common denominator will be a product of 100 numbers, and it will be huge, and in the numerator we will have an alternating sum of products of 99 numbers, pluses and minuses, and we'll have to do a lot of computations with really huge numbers. And instead of that, we're going to avoid computations with big numbers at all. But first we're going to use generalization. So instead of solving this initial problem, let's solve a more general problem actually. We're going to prove that the alternating sum 1 minus 1 over 2 plus 1 over 3 minus 1 over 4 and up to 1 over 2k minus 1 minus 1 over 2k for some integer k is always equal to 1 over k plus 1 plus 1 over k plus 2 and up to 1 over 2k. And you should notice that for k equal to 50, this is exactly the same as the initial problem, because the alternating sum on the left goes from 1 minus 1 over 2 up to 1 over 2k minus 1 is 91, 1 over 99 minus 1 over 100. So this is the same alternating sum. And on the right, the sum starts with 1 over k plus 1, which is 1 over 51. And the last summand is 1 over 2k, which is 1 over 100, which is the same as in the initial problem. So this is indeed a more general problem. And now that we see it as a more general problem, we can actually prove it for any k using mathematical induction. And to do that, we'll first prove the induction base for k equal 1. For k equal 1, the alternating sum on the left has exactly two summands, 1 minus 1 over 2. And the right part just has one summand, 1 over k plus 1, where k is equal to 1, so it is 1 over 2. And we see that the alternating sum is equal to the right part. So we proved the induction base for k equal to 1. And now we want to prove the induction step, to move from k to k plus 1. And to avoid writing really long formulas, let's see what changes in the left and the right part when k increases by 1. So we know that for k, the left part is equal to the right part. And we want to prove that for k plus 1, the left part will also be equal to the right part. Instead of comparing the whole left and right part for k plus 1, we will just compare the differences in the left part and in the right part. And if initially the left part is equal to the right part and the differences are equal, then the left part and the right part for k plus 1 are also equal. So for the alternating sum, when we increase k by 1, we always get two more summands. We get one with plus and one with minus. So with plus we have 1 over 2k plus 1, and with minus we have 1 over 2 times k plus 1. So this is by how much the left part will increase when we increase k by 1. Now let's look at k plus 1 and at the right part. So the right part for k plus 1 starts with 1 over k plus 2 and goes up to 1 over 2 times k plus 1. But I also explicitly wrote the last three summands, 1 over 2k, 1 over 2k plus 1, and 1 over 2 times k plus 1. Now what we can do as a magical trick in math is we can add 0 to anything and it will stay the same. And to add 0 we can actually subtract something and add something. So in the left we subtract 1 over k plus 1 and add it back. And so nothing changes, so we have an equality of the first line and the second line. Now we want to rearrange our summands. We want to notice that starting from the second summand in the second line, we get the right part for k. We get the sum from 1 over k plus 1, 1 over k plus 2, plus 1 over k plus 3, and up to 1 over 2k. And then we have three more summands which are not in this sum. Two of them are the two last summands for k plus 1. Those are 1 over 2k plus 1 plus 1 over 2 times k plus 1. And also there is this summand that we subtracted in the second line, 1 over k plus 1. So the right part changes by exactly these three last summands. 1 over 2k plus 1 plus 1 over 2 times k plus 1 minus 1 over k plus 1. And we can actually simplify this expression if we notice that 1 over 2 times k plus 1 minus 1 over k plus 1 is the same as minus 1 over 2 times k plus 1. And so actually when we rewrite it and simplify it, we see that the right part changes from k to k plus 1 by the same value, 1 over 2k plus 1 minus 1 over 2 times k plus 1, as the left part. So left part and right part change by the same amount, and they were the same for k, so they are the same for k plus 1, and we have proven the induction step. And as we have proven both the induction base and the induction step from k to k plus 1, we have proven the general statement. And we know that the alternating sum on the left is equal to the sum on the right for any k. In particular, it is also true for k equal 50, and so we solved our problem. As I said, this is the last video about mathematical induction, so it's time to make some conclusions. We see that mathematical induction is a powerful proof method because we solved a lot of problems with it, and some of the problems couldn't be solved without it. To apply it, we first need to reformulate problem in mathematical terms. Then we need to prove induction base, which is basically the proof of our statement for several small values of n. In most cases, just for one smallest value of n. Then we need to prove the induction step. And in the simple case, in the weak induction, we just prove from n to n plus 1. Assuming that the statement is true for n, we prove that it is also true for n plus 1. But sometimes we need to apply a strong induction or complete induction, when we use induction step from several values of n to n plus 1. And in this case, we need to remember to also prove induction base for the corresponding number of smallest values of n, not just for one, but for as many as we use in the induction step. Also, sometimes before induction, we often need to come up with the formula somehow first before proving this formula. We saw this example in the Gauss teacher's problem. And also, as we saw in this last lecture, we sometimes need to generalize our problem before we can see that induction can be applied. So in this problem, we were proving something for formula with alternating sum of 100 summons and a regular sum with 50 summons. We generalized it for alternating sum with 2k summons and a regular sum with k summons, and then we were able to apply induction and prove it for all values of k, in particular for k equals 50. So sometimes you need to generalize, and this makes your problem harder from one point of view, but it actually makes it simpler because then you can apply mathematical induction and this powerful proof method solves your problem. See you next week. Hi, this is Michael, and in this lesson we're going to study examples, counterexamples, and the basic constructions of mathematical logic. And we'll start with examples. Sometimes to prove a mathematical statement, just one example is enough. For example, if we want to prove the statement that white horses exist, it is sufficient to just show one white horse. We don't need to go and show many white horses. We don't need to show that all the horses are white. We just need to show one white horse, and that proves the statement. However, such examples are not always easy to come up with. And now we'll consider some more problems which can be solved by examples. First problem is it possible that for three positive integers a squared plus b squared is equal to c squared? And here we can get an example with three small numbers where a is 3, b is 4, and 3 squared plus 4 squared is 9 plus 16, which is 25, which is the same as 5 squared. So we take c equal to 5. So this example solves the whole problem. How to come up with this example? Well, you can, for example, remember the Pythagorean theorem from school, and that there exists a right triangle with sides 3, 4, and 5, and so the sum of squares of sides is equal to the biggest side in the right triangle. And so this is what this example is about. Now let's look at more statements like that. So in the previous problem, we had a statement about squares of positive integer numbers, and now we want to ask the same about cubes of positive integer numbers. So a to the power of 3 is also called a cubed. So is it possible that for three positive integers a, b, and c, a cubed plus b cubed is equal to c cubed? It would be also a solution to just show one example to this problem, and then the answer would be positive. However, in fact, this is impossible, and so there is no example. Fermat's last theorem, one of the most famous mathematical conjectures, states that for any integer n bigger than 2, there are no such integers a, b, and c that a to the power of n plus b to the power of n equals to c to the power of n. Mathematicians were trying to prove this unsuccessfully for hundreds of years. There were thousands of attempts. And some of these attempts were pretty silly, but many of these attempts led to a lot of useful mathematical theories. And finally, in 1995, Andrew Wiles famously proved it. And its particular case for n equals 3 states that there are no such positive integers a, b, and c that a cubed plus b cubed is equal to c cubed. So this answers our problem with a negative. And it means that there is no example in this particular case. Another similar problem: is it possible that for positive integers a, b, c, and d, sum of their fourth powers of a, b, and c is equal to the fourth power of d? For this problem, one could think that it is also impossible due to Fermat's last theorem. You just need to apply it for n equals 4. However, this theorem only says something about equations of the form a to the power of n plus b to the power of n is equal to c to the power of n. So it is not applicable, because in this example we have three summands on the left: a to the power of 4 plus b to the power of 4 plus c to the power of 4. And Fermat's last theorem is about the cases when we have only two summands on the left, so it is not applicable. So actually, in fact, the answer for this problem is again yes, this is possible. However, the smallest possible example is huge. So it's 95,000 something to the fourth power, and 200,000 something to the fourth power, and 400,000 to the fourth power, equal to 400,000 something to the fourth power. So this example is huge, and I don't imagine that you could come up with this example in any reasonable time yourself. Computers are often used to generate such huge examples. However, the number of possibilities in many mathematical problems can be so big that it is hard to find an example even with the help of a computer, and it would take a whole lot of time, even if we take all the computers on Earth. But here, an example was found, and it was even proven that this is the smallest possible example. There are no numbers a, b, and c which are less than these three, for which a to the fourth plus b to the fourth plus c to the fourth can be equal to some integer to the fourth power. And the last problem for which we're going to consider an example in this video is the following. Is there a power of 2 that starts with digits 6 and 5? And here the example, some of you have known this example, that 2 to the power of 16 is equal to 65,536. And this is the whole solution. We just show this one example and we solve the whole problem. In fact, we can show that for any integer, positive integer n, there is a power of 2 that starts exactly with this integer. But this problem is much harder to prove. I should also note that you've met with examples as proofs in the previous lectures, in the previous weeks of this course. And for example, there was a problem: is it possible to cover a chessboard with dominoes? And it was solved given a particular example of how we can cover a chessboard with dominoes. And there were several examples by Alexander, but it was sufficient to show just one example to solve that problem. So examples are a common way of solving mathematical problems. And in the next lecture, we are going to talk about counterexamples. Hi! In the previous video we talked about examples. In this video we will study counterexamples. Examples which prove that something is actually incorrect. Sometimes just one counterexample is sufficient to disprove a whole statement. If we want to prove that all swans are white, just showing one black swan is sufficient to disprove this statement. However, it is often hard to find such counterexamples. Let's start with this theorem. All rectangles are squares. Here it is easy to find a counterexample because a rectangle with sides 1 and 2 is not a square, because the square must have all the sides equal. And so this is a counterexample for the theorem, and so this theorem is wrong. Now let's consider another theorem. All squares are rectangles. In this case, there is no counterexample, and the theorem is true, because square is by definition a rectangle with equal sides, and so any square is actually a rectangle, and you cannot come up with a counterexample to disprove this theorem, because the theorem is true. Now let's move on to more complex theorems. So Euler is a famous mathematician, and he proved a lot of facts, but also he made some conjectures which he didn't prove, and one of his conjectures is a generalization of Fermat's last theorem. When Euler lived, Fermat's last theorem was not proved, but he still came up with even a generalization of this theorem, and he wanted to prove that for any positive integer n bigger than 2, it is not only impossible to solve equation a to the nth plus b to the nth equal to c to the nth, it is also impossible for an nth power of a positive integer to be represented as a sum of n minus 1 numbers which are nth powers of positive integers. For n equals 3, it is the same as Fermat's last theorem for n equals 3. It is impossible that a to the power 3 plus b to the power 3 is equal to c to the power 3. And so for n equals 3, this conjecture is true because we know now that Fermat's last theorem is true. It was proved in 1995. So for a particular case of the smallest n, Euler's hypothesis is true. However, for bigger values of n, this is not true, and in 1966 Lander found the following counterexample for n equals 5. And the counterexample is on the slide, and it already disproves the whole conjecture. However, it still leaves some room for questions. For example, what about n equal to 4? For n equal 3 we know that the conjecture is correct. For n equal 5 we now know that the conjecture is incorrect. What about n equals 4? Actually, in 1986, Elkis found another counterexample, and it was for n equal to 4. And you see that this counterexample is huge, and so it turned out that this is not the smallest possible counterexample, and the smallest possible counterexample was found in 1988. And actually, you've already seen this counterexample as an example in the previous video. And of course, this is often the case. Something can be an example and a counterexample at the same time, but it is just example for some statement, and it is a counterexample for the negation, for the opposite of that statement. And depending on what you want to prove, you can either make an example to prove the positive statement or make a counterexample to disprove a negative statement. And also a reminder that in the previous week when we studied induction, we were trying to prove that it is impossible to cut an obtuse triangle into smaller acute triangles. And then, at some point when we already thought that we proved it, we came up with a counterexample, and here it is on the slide. And so this is another counterexample which disproves this statement. In this case, it is possible to cut the obtuse triangle into acute triangles like this. So now we are acquainted with examples and counterexamples, and in the next lecture we're going to discuss more general things, the basic mathematical logic constructions. Hi! In this lecture we're going to start studying mathematical logic. It is a whole big branch of mathematics. But in this particular video I will tell you about some basic constructions of mathematical logic. And we will start with the most common logical operations: negation, logical and or, and if-then statements. Let's start with negation. Suppose we have some statement like all swans are white. Then the negation of this statement is that not all swans are white, the opposite of this statement. Another way to state a negation of the statement is that there are swans that are not white. Another statement for which we will find a negation is the following. There exist three positive integers a, b and c such that a to the power of 3 plus b to the power of 3 is equal to c to the power of 3. And when we're thinking about negation, it doesn't matter whether the statement is true or not, we're just formally trying to find the opposite statement. And again, there are two ways to formulate it. One is there are no such positive integers a, b and c that a cubed plus b cubed is equal to c cubed. Or another way to say the same is that for any positive integers a, b and c, a cubed plus b cubed is not equal to c cubed. And two more examples is, first we have statement 4 equals to 2 plus 2. Then the negation of this statement is that 4 is not equal to 2 plus 2. And another example is 5 is equal to 2 plus 2. The negation is that 5 is not equal to 2 plus 2. So you see that it doesn't matter which statement is true, which statement is wrong. We just apply simple rules to make a negation from a statement. And then always either the statement is true or its negation is true. In the first case, the statement is true, 4 is equal to 2 plus 2. And in the second case, the statement is wrong, 5 is not equal to 2 plus 2. So the negation of that statement is true, 5 is not equal to 2 plus 2. Negation is true if and only if the initial statement is wrong and vice versa. This is by definition of the negation. Next construction is logical AND operation. An example is on the slide. 4 is equal to 2 plus 2 and 4 is equal to 2 times 2. The logical AND of two statements is true in the case when both statements are true, and otherwise it is false. So if we write these 4 applications of logical AND, then only the first one of them is true, because both 4 equals to 2 plus 2 and 4 equals to 2 times 2 are true, and so the logical AND of two true statements is true. The second statement is false, because 5 is not equal to 2 times 2, so the second statement is false, and logical AND is only true when both statements are true. So if the right statement is false, logical AND is also false. And the last two statements are also false because the left part is false. 5 equal to 2 plus 2 is false, and it is common in the last two statements, and so logical AND is false. Similar construction is logical OR. For example, 4 is equal to 2 plus 2 or 5 is equal to 2 plus 2. And the logical OR of two statements is true if at least one of them is true. So in this case it is true because 4 equals to 2 plus 2 and it doesn't matter whether 5 is equal to 2 plus 2 or not, the OR statement is already true. And here is a similar example with OR. So the first two statements are true and the last statement is false. So the first two statements are true because 4 equals to 2 plus 2 is true, and so it doesn't matter whether the second statement is true or not. In the first case it is true, in the second case it is false, but still the OR is true. And in the third line, in the third statement, the right part, 4 equals to 2 times 2 is true, and this is also sufficient for the logical OR to be true. It doesn't matter that the left part, 5 equals to 2 plus 2 is false. Still, the OR is true. And in the last line, both left part and right part are false. 5 is not equal to 2 plus 2, 5 is not equal to 2 times 2, so the logical OR is false. Venn diagram is a way to visualize these operations: logical NOT, logical OR, logical AND. Also, in mathematics, logical NOT is often denoted by the sign on the slide, just to make notation shorter. Logical AND also has its own sign like that, and logical OR has the sign which is upside down from logical AND. And on the three pictures below, we see the illustration of logical AND on the left, logical OR in the middle, and logical NOT on the right. So on the left, we have a big rectangle which is all possibilities, and the circle denoted by X is the circle of all possibilities where statement X is true. And the circle denoted by Y is the circle of all possibilities where the statement Y is true. And then the set of possibilities where X and Y is true is the intersection of those circles. Because for logical AND to be true, we need both X and y to be true, and that's why you need to take the intersection. On the picture in the center, we have similar illustration for logical OR. We have two circles for x and y, and for logical OR to be true, we need to x to be true or y to be true, but just one of them is enough. So we take the union of the circles. Anything inside circle x makes OR true, anything inside circle y makes OR true, and anything in the intersection also makes the OR true, but everything outside both circles makes logical OR false. And on the last picture we see the illustration of the negation of x. So if the circle for x is everything, all the possibilities where x is true, then the negation of x is true on all possibilities but for these. So the red area is everything but for the possibilities inside the circle for x, and this is where the negation of x is true. Now let's study negation of AND and OR. So negation of AND is the OR of negation. So for example, negation of statement like A and B is not A or not B. For example, negation of statement that 4 is equal to 2 plus 2 and 4 is equal to 2 times 2 is the statement that either 4 is not equal to 2 plus 2 or 4 is not equal to 2 times 2. Negation of OR is symmetric. Negation of OR is AND of negations. So negation of statement A or B is not A and not B. For example, the negation of 4 equals to 2 plus 2 or 5 equals to 2 plus 2 is 4 is not equal to 2 plus 2 and 5 is not equal to 2 plus 2. Now, the most interesting part is if-then statements. We're always using them actually for all the theorems, but how to define them formally. Consider a promise. If there is an elephant in your refrigerator, then I will give you $100. Now there are the following cases. If there is indeed an elephant in the refrigerator, and I indeed give you $100 for that, I keep my promise, and so the statement is true. If there is no elephant in your refrigerator, and I didn't give you $100, I still kept the promise because there was no elephant, so I don't need to give you $100, so the statement is also true. If there is an elephant in the refrigerator, but I don't give you $100, then I don't keep my promise, so this statement becomes false. And the interesting case is, what if there is no elephant in the refrigerator, but for some reason I still give you $100 anyway? Did I keep my promise or not? Well, in the technical sciences we consider it as a kept promise, so although there was no elephant, I still gave you $100, that doesn't break any promises, so this statement is considered true. Now, in the general case, phrase if P then Q, for some statements P and Q, is true whenever either Q is true or P is false. The interesting quirk in this is that if P is false, then every statement of the form if P then something will be true, disregarding whether Q is false or true or anything. So this is sometimes what confuses people, but formally this is always the case. Examples. If n is equal to 6, then n is even. This is true, because if we take n which is equal to 6, and this statement is true, then n is also even. And so the Q, the second statement, the then statement is true. If n is not equal to 6, then the if part is false, and as we know, as soon as if part is false, the whole statement if then is true. The second statement, if n equals to 4, then n is even, is false, because if we take n equal to 5, then the if part will be true, but the then part will be false, and this is the only case when the if then actually becomes a false statement. Now the interesting parts are like, for example, if 1 is equal to 2, then 2 is equal to 3. This is a true statement. Why? Because 1 is not equal to 2, so the if part is false, and then whatever we write on the right part, the statement is true. For example, if 1 is equal to 2, then I am an elephant is a completely true statement from the mathematical point of view. Because 1 is not equal to 2, so the if part is false, and then the statement that I am an elephant doesn't matter whether it's true or false, the if-then statement is true in this case. Now we want to generalize a bit, because typically we see statements like this: if n is divisible by 4, then n is divisible by 2. What it actually means is that for all integers n, if n is divisible by 4, then n is divisible by 2. And this statement is actually true. How do we check it? For any number n, either it is divisible by 4, and so the if part is true, but then it is also divisible by 2, because it is divisible by 4. If we divide it by 4, we get an integer number, but then if we divide it by 2, we get twice that integer number, so it is also integer. So n is divisible by 2 whenever it is divisible by 4. So both the if part and the then parts are true, and so the statement is true in this case. And the second case is that n is not divisible by 4. Then the if part is false. But then if the if part is false, then if-then statement is always true. It doesn't matter whether n is divisible by 2 or not. So this general statement, if n is divisible by 4, then n is divisible by 2, is true. Here we changed if and then part, we switched them, and write if n is divisible by 2, then n is divisible by 4. This statement is false, because for a particular n equal to 2, it is divisible by 2, but it is not divisible by 4. If we divide 2 by 4, we'll get 0.5, which is not integer. So the if part is true, but the then part is false, so the if-then statement is false. Actually, we can call the first statement, if n is divisible by 4, then n is divisible by 2, the direct statement. When we switch the if and then part, we call it the converse statement to the initial direct statement. So if n is divisible by 2, then n is divisible by 4 is a converse statement. And sometimes both direct statement and converse statement are true. This is not true in this case, because the direct statement is true, but the converse statement is false. But sometimes both direct statement if p then q and converse statement if q then p are true. And in this case we write that they are equivalent like this: p if and only if q. This means that whenever p is true, q is also true. Whenever q is true, p is also true. They are equivalent. Now let's apply negation to the if-then statements. The negation of the phrase if p then q is actually p and not q. And you check for yourself that this is true whenever the corresponding if-then statement is false, and vice versa. So just check that by definition of negation, p and not q is actually the negation of the phrase if p then q. A few more definitions. Universal quantification is actually a thing that we've already routinely used for some time. Statements like all swans are white, all integers ending with digits 2 are even, for all n, 2 times n is equal to n plus n are examples of universal quantification. Fermat's last theorem states that for all integer n more than 3, equation a to the power of n plus b to the power of n equals to c to the power of n does not have solutions with positive integers a, b, and c. Thus, as it starts with the phrase for all n, it is also an example of universal quantification. Another quantification is existential, and we've also used it routinely in the previous lectures. Statements like there are black swans, there is a way to get a change of 12 cents with 4 cents and 5 cents coins, there exist such integers, positive integers a, b, c, and d, that a to the 4th plus b to the 4th plus c to the 4th is equal to d to the 4th, and there is a power of 2 starting with 65 are all examples of existential quantification. And in statements that state that something can be done, something exists, is an example of existential quantification. Now we can make combinations of quantifiers, and most mathematical statements are usually combinations of universal and existential quantifications in some combination. Here is a corollary from Fermat's last theorem. There exists such integer m that for any integer n which is bigger than m, equation a to the nth plus b to the nth is equal to c to the nth has no solutions with positive integers a, b, and c. Why is this a corollary from Fermat's last theorem? Well, because if we take m equals to 2, then it follows from Fermat's last theorem because we just change m to 2 in this statement and we get that there exists integer 2 such that for any integer n bigger than 2, equation a to the nth plus b to the nth is equal to c to the nth has no solutions. And this is exactly Fermat's last theorem. So this is a particular case of Fermat's last theorem. And so we found that this is a corollary from Fermat's last theorem because of the existential quantification. We found an example of m for which the existential quantification is true. And the statement itself is a combination of existential quantifier, there exists such integer m, and universal quantifier for any integer n bigger than m. Now, what do we do if we need to negate some quantification? Negation of universal quantification is a corresponding existential quantification and vice versa. For example, negation for all n, statement A is true. The negation of it is there exists such n that statement A is false, and vice versa. Euler's hypothesis is a combination of two universal quantifications. For any n bigger than 3, for any positive integer a, it is impossible to represent a to the power of n as a sum of exactly n-1 numbers which are also nth powers of positive integers. Thus, negation of Euler's hypothesis is a statement that there exists such n integer bigger than 3 and such positive integer a that a to the power of n can be represented as a sum of n-1 numbers which are nth powers of positive integers. And we saw an example which proves this negation, so Euler's hypothesis is actually false. Negation of combinations, things like all positive integers are either even or odd, is there exists such positive integer that is not even and not odd. So to negate we switch universal quantification to existential and vice versa, and we switch or to nth and vice versa. And examples and counterexamples, for example, counterexample for Euler's hypothesis that we saw earlier is an example for the negation of Euler's hypothesis. So examples and counterexamples are also dual as and or, universal and existential. Examples and counterexamples are dual by proving negation of Euler's hypothesis. By showing an example to it, we prove that Euler's hypothesis itself is false. And this example is just a counterexample to the initial Euler's hypothesis. And one popular way of proving mathematical statements is called reduction ad absurdum, basically proving that negation of the initial statement is false and so the statement itself is true. And you will learn this proof principle in the next lecture. In conclusion, in this lesson we've studied examples, counterexamples, and when just one example or counterexample is enough. We studied basic logical operations, negation, logical and, logical or, and if-then statements. We also studied universal and existential quantifications. And we learned how to negate different combinations of logical operations. And in the next lecture, you will study reduction ad absurdum principle, which is based on these constructions.
Hi, I'm Vladimir Podolsky, and today we are going to discuss reductio ad absurdum, or proof by contradiction. So how can we prove that something is true? One way to do it is to show that the opposite is impossible. Indeed, if you have a statement, and the opposite to the statement is impossible, then your statement must be true. And this method is called reductio ad absurdum, or proof by contradiction. This is one of the base methods of reasoning. It is used everywhere, and it is often combined with other methods, and we will use it a lot through our courses. So we will discuss this method in this lesson extensively. So reductio ad absurdum is a classical method. It is as old as logic, and one early example is Socratic method in books by Plato. Socrates did the following. He talked to his students, and he revealed contradictions in the beliefs of his students, just asking them question by question. And in this way, he showed that the beliefs of his students are inconsistent. Okay, so let's consider the following example. Let's consider the following problem. There is a class, and there are boys and girls in this class, and they are divided into two groups for the foreign language. There are students who study French, and there are students who study German. And each student picks one of the two languages. Okay, now in this situation we need to show that there is a boy and a girl who study different languages. And this might seem impossible at first. We know basically nothing, so we have a completely generic situation. It is very typical, nothing specific is known, so we do not know any restrictions, any useful information basically. So we just have a class, there are boys and girls, there are two languages, and somehow we would like to state something non-trivial. We would like to state that there is a boy and a girl who study different languages. So let's proceed to the solution. We will solve this problem using proof by contradiction. Suppose that our statement is wrong. So there are no boy and a girl studying different languages. So, okay, so we have now this assumption and we have to get to a contradiction. So we have to show that something is wrong now. Okay, and for this let's consider some girl. And without loss of generality, let's assume that this girl studies French. It could be German, it doesn't matter, so let's assume it's French. Okay, now let's consider some boy. We know that there is no pair of boy and a girl studying different languages. So if we consider some boy and we consider this girl, they should study the same language. So each boy, we can pick any boy, and each boy should study French. So all boys are studying French. So this is already suspicious. Somehow we have made our assumption, and somehow it turned out that all boys are learning French now. Okay, but this is not a contradiction yet. It might be the case. It might be that all boys decided to learn French. Okay, but let's proceed now. Let's consider some boy now. Let's consider the first boy, and let's consider some girl. Since we know, again, by our assumption, that there is no boy and a girl studying different languages, and the boy studies French, then this arbitrary girl we are considering is also studying French. So this means that all girls are studying French as well. So it means that everyone studies French. Okay, so we made our assumption, and now everyone is studying French. And we know that this is impossible, because, okay, we know that students are divided into groups, we know that there are students studying German, and now we have obtained that everyone studies French. This is a contradiction. So we have made our assumption, and we arrived at a contradiction. We have deduced that no one is studying German. This is forbidden by the formulation of the problem, so our assumption was wrong. So the original statement was true. And that's how the proof by contradiction works. Consider the following problem. We have 10 boxes, and they are filled with a lot of white balls. And we would like to distinguish these boxes. And the only way to do it, so the only means to do it, we have in our hands are 30 black balls. And they are identical, so how can we distinguish boxes now? We can place different number of black balls into different boxes. This way the boxes will be distinguished. So we have 10 boxes, we have 30 black balls to distinguish them. Can we do it or not? We will prove that this is impossible, and for this we will assume the contrary. We will assume that we can do it. And we will see that there is a contradiction. So let's assume that we have placed black balls in the boxes in such a way that there are different number of balls in different boxes. And let's see what happens. Okay, let us enumerate all boxes in the increasing order of the number of black balls in them. Okay, let's see what we can tell about the number of balls in each box. Consider the first box. There might be any number of balls there. It's below 30, of course, but that's all we know. Okay, we can make a trivial statement where there are at least 0 balls there. We basically are saying nothing, but let's just say a trivial statement here. Okay, but now let's look at the second box. And the number of balls there is greater than the number of balls in the first box. Why? So we enumerated boxes in the increasing number of black balls, and the number of balls in the first box and in the second box are different. So we should have strictly greater number of black balls in the second box than in the first box. So it should be at least one ball, there should be at least one black ball in the second box. Now let's consider the third box. Again, the number of black balls here should be greater than the number of black balls in the second box. It should be greater or equal than the number of black balls in the second box, because we have enumerated boxes in the increasing order, and it cannot be equal because we have assumed that we have different number of black balls in all boxes. So there should be at least 2 black balls in the third box. Okay, now we can proceed in the same way further. So in the fourth box we should have greater number of black balls than in the third one, so there should be at least 3 black balls. Then the fifth one at least 4, and so on and so forth. In the end, we have at least 9 black balls in the 10th box. Okay, so now that's what we have. Now let's see how many balls in the how many balls do we have in all boxes in total? Let's sum up all of these numbers. And if we sum up numbers from 0 to 9, we see that there are at least 45 balls in all of the boxes. And note that this is a contradiction. We know that we have 30 balls in total. And now we assumed that we have solved we have placed balls in boxes in such a way that is required in the formulation of a problem. And now we have 45 balls. And this is a contradiction to the original, to the formulation of the puzzle. We have 30 black balls in the formulation and 45 black balls here. So this is a contradiction, and so our assumption was wrong. Our assumption was that we can do it. And so it is wrong, and so we cannot do it, and we have shown this rigorously. Consider the following problem. There is a sequence of 10 cells. The leftmost contains number 1, the rightmost contains number 30. And the question is, can we place numbers in all other cells in such a way that consecutive numbers differ by at most 3? So we will show that this is impossible, and to do this we assume that it is possible, and we will get a contradiction. So let's assume that we can do it, and let's see what happens. And let's see what is the largest possible number we can place in the second cell. And it should differ from 1 by at most 3, so the largest possible is 4. Okay, now let's see what is the largest possible number we can place in the third cell. It should differ from 4 by at most 3, so the largest possible again is 7. Okay, next, in the next cell we can place at most the largest possible number is the number that differs from 7 by at most 3. So it's 10, and so on and so forth. So let's see what happens. So in the 9th cell we will place, in this way, we will show that the largest possible number we can place there is 25. And note that this is too far from 30. So even if we put the largest possible numbers in the cells of this, of this sequence, still in the 9th cell we have the number which is too far from 30. So why? So this is a contradiction. So we assume that we can do it, and we got a contradiction. So we have shown that this is impossible. And the reason for this was that numbers in the cells grow too slowly. And note that, observe that this problem is an important example for us. This reasoning is a very common trick for estimating the running time of some algorithm. We find some number in the algorithm and show that it grows too slowly and it should be large in the end. And that's how we can show that some algorithm should work for a long time. Okay, now consider the following problem. We have a chessboard and we would like to place numbers in all cells of the chessboard. Numbers from 1 to 64. And we would like to do it in such a way that neighboring cells that is sharing a site differ by at most 4. Okay, can we do it or not? We will show that this is impossible, and for this we will assume that it is possible, and we will again arrive at a contradiction. So let's assume that we have done this. So let's assume that we have a table filled with numbers from 1 to 64, and we are going to, we would like to arrive to a contradiction. So the first problem in here is to understand what we should look at. And the good idea is to look at the largest and the smallest number in this table. Numbers 1 and 64. So they are somewhere in this table, suppose they are here. Okay, how many steps does it take us to get from 1 to 64? Okay, it is not hard to see that in this case we need 7 steps. We need 3 steps right, and we can make 3 steps right and 4 steps up to get from 1 to 64. Okay, note also that 7 steps are necessary because we need to go to the right at least 3 times to get to the 6th column, and we need to go up we need to get up at least 4 times to get to the 6th row from the cell containing 1. Okay, so we need at least 7 steps. So we need 7 steps to get from 1 to 64. And it is already it already looks suspicious. So in the cells indicated now by green color, in the neighboring cells they differ by at most 4. And in the beginning we have 1, in the end we have 64. We can do calculations, but it is also visible to a naked eye that it is impossible to do that. Numbers grow too slowly. Okay, so but maybe we have placed numbers 1 and 64 in the wrong way. Maybe they should be placed in some other way, such that it takes more steps to get from 1 to 64. And it is not hard to see that the best way to place 1 and 64 is to place them in the opposite corners. Then it takes us 14 steps to get from 1 to 64. 7 steps right and 7 steps up. Now we have 14 steps to get from 1 to 64, and the number, in one step the number can grow by at most 4. So in 14 steps it can grow by at most 4 by 14, which is 56, which is not enough. If in the beginning we have 1, we can grow by at most 56, and in the end we have 64. This is impossible to achieve. So let's place numbers in these tables and see it by eye, that in the end we have 53, which is too far from 64. So we have shown that this is impossible, and again we have applied the same idea as in the previous problem. Consider the following problem. We need to show that there are 2 people in New York City with the same number of hairs. Okay, let's see what's going on in this problem. First of all, how many people are there in New York City? Wikipedia says it's at least 8 million. Okay, and how many hairs does a person have on his head? So again, Wikipedia says it's about 150,000 hairs at most. So what can we conclude? We see that there are way more people in New York City than possible number of hairs. And this means that there should be 2 people with the same number of hairs. Indeed, if there is only one person for a certain number of hairs, then there are just not enough number of hairs for everyone. So there should be people with the same number of hairs. Okay, the general principle we used here is a pigeonhole principle. Suppose there are n pigeonholes and there are n plus 1 pigeons in them. Then we can claim that there is a pigeonhole that is occupied by at least 2 pigeons. This is a very simple principle, but on the other hand it is very useful. We will use it a lot. So how can we check that this principle is true? We can prove it by contradiction. If there is at most 1 pigeon, if the statement is false and we have at most 1 pigeon in each hole, then we can sum them up, and we have at most n pigeons in total in all holes. So this is a contradiction to the statement where there are n plus 1 pigeons. We know that. So by contradiction we show that the principle is correct. And in the previous example, people of New York City played a role of pigeons, and a possible number of hairs played a role of holes. So we have shown that there are much more pigeons than holes, not even n plus 1 pigeons, but much more. So there must be a pigeonhole, the number of hairs that is shared by more than by 2 people. Consider the following problem. We have a 3x3 table, and we would like to fill it with numbers -1, 0, and 1 in such a way that the sum of each row, the sum of each column, and the sum of numbers on both diagonals produce different numbers. Can we do it or not? Okay, let's try to do it. Let's fill the table in some way and let's see what happens. Okay, let's look at it for a bit, and we can observe that if we look at the first two columns, then they sum up to 1. And we have not, so the sum of these columns is the same, and this is not, we haven't solved the problem in this way. Okay, so maybe it's impossible, and if we can try it more, it doesn't work. Okay, so it turns out to be impossible, and let's show it. And let's see how many restrictions do we have. So there are 3 rows, 3 columns, and 2 diagonals. In total, we have 8 numbers to be different. On the other hand, if we sum up numbers over some line, then the result ranges in between -3 and 3. It is -3 if all numbers were -1 in this line, in this row, or in this column, or in this diagonal, and it might be 3 if we are all ones. So it is something in between -3 and 3. So there are 7 values in total, from -3 to 1, to -1, from 1 to 3, 6 values, and 0. So there are 7 values in total, and we would like to have, so we would like 8 numbers to be different, and we know that these numbers ranges, so can obtain 7 possible values. So this is impossible. Here, possible values are pigeonholes. Numbers, lines in the table, rows, columns, or diagonals are pigeons. So we have more pigeons than pigeonholes. So there should be 2 pigeons, 2 lines in this table that are equal to the same, so that sum up to the same number. So we have shown that this is impossible using Pigeonhole Principle. The next problem we are going to consider is a bit more tricky. Suppose we have 30 persons in the room. Some of them had shaken hands. We need to show that there are 2 persons who shaked equal number of hands. Okay, we have applied Pigeonhole Principle before, we are experienced, so let's count. There are 30 people, and they will be pigeons, and possible number of handshakes will be pigeonholes. So we will show that we would like to show that there are less pigeonholes than pigeons. Okay, so how many handshakes can person have? The minimal possible number is 0. The person might have not shaken hands at all, and the largest possible is 29. If a person shakes hands with everyone else, it is 29 handshakes. There are 29 persons except the person himself. 29 other persons. Okay, so there are 30 options for handshakes. There are 30 pigeonholes, and it doesn't work. So we have the same number of pigeons and pigeonholes. So we cannot apply Pigeonhole Principle. It doesn't work. Or maybe it does. So maybe we just are not smart enough. And indeed, if we look at this a little bit more, we observe that we can see one more detail in this picture. Observe that it is impossible to have 0 handshakes and 29 handshakes in the same room. It is impossible that someone, so in the same room there is one person who hasn't shaken hands at all, and there is another person who had shaken hands with everyone. Because these persons either had shake hands between each other or not. So if we had, then the first one doesn't have 0, and if they didn't, then the second one doesn't have 29. So if we have a room with people, and so there are 0 and 29 handshakes are impossible simultaneously, and this leaves us with 29 pigeonholes. So, and now there are two people who had the same number of handshakes. So using this additional observation, we make our Pigeonhole Principle work for this problem. Let us summarize what we have learned in this lesson. We have discussed proof by contradiction. This is one of the most basic ways of reasoning. It is used everywhere, it is usually combined with other ideas, but sometimes it can help on its own. We have seen examples of that. Next, we discussed Pigeonhole Principle, one of the most basic proof ideas. It is used a lot in mathematics, and we have seen examples. We will see other examples later. On the other hand, it's a very simple principle and basically amounts to counting. Hi, I'm Vladimir Podolsky, and today we are going to discuss double counting. Let's start with the following general idea. It is useful to look at the same problem from two different angles. Indeed, this way we can get information from two different sources, and sometimes it is crucial. There is a special case of this simple idea in mathematics, to look at some number at your problem from two different points of view. Let's consider the following example. Is it possible to fill a table 3 by 5 by integers in such a way that sum of integers in each row is equal to 20 and the sum of integers in each column is equal to 10? Okay, let's try to do it. So let's fill the first row in some way. So in the end we have to be careful so that the sum of the first row is 20. Now let's fill the second row in some way. Again, in the end we have to be careful so that the sum is equal to 20. And so now we are going to fill the third row, and now we have to be careful every time, because in each column we have to have sum 10. So here we have to put 3, then 3 again, then 4, then 0, and then we have to put 0, since the sum of the column should be 10. But on the other hand, we see that the sum of the row is 10, and so we failed. Okay, let's try to show that this is impossible. And how we are going to do it? Let's assume that this is possible, that we can fill the table with integers. So we use proof by contradiction here. Okay, let's look the crucial idea here. Let's look at the sum of all numbers in this table. From one hand, the sum of each row is 20. So in total we have 3 rows. So in total we have the sum of all numbers in this table is equal to 60. On the other hand, the sum of each column is 10. So the sum of all columns, the sum of all numbers in all columns is equal to 50. So on one hand, the sum of all numbers in the table is 60, on the other hand it is 50. So this is a contradiction. So we have shown that this is impossible, and let's summarize how we have done this. We have shown impossibility by computing the same value in two different ways and obtaining two different answers. So the key difficulty here, the main problem, is to find the right value to compute. Let's consider one more application of double counting. Consider the following problem. There are 20 students in the group, and each has solved 3 problems in the homework assignment. On the other hand, each problem was solved by 2 students. So how many problems were in this assignment? Again, we will look at some value in this problem from 2 points of view. And this time this value will be total number of solutions of problems by all students. So on one hand, there are 20 students and each solved 3 problems, so there are 60 solutions in total. On the other hand, each problem received 2 solutions. So the number of problems is 60 divided by 2, which is 30 problems. We note that this problem is very similar to the previous one. We can consider a table where columns correspond to problems and rows correspond to students. So let's put 1 in the cell of this table if the corresponding student solves the corresponding problem. And let's put 0 in the cell of this table in otherwise. So in total, we will have 60 ones in this table. On the other hand, in each column there are 2 ones, so there are 30 columns. Hi, I'm Vladimir Podolsky, and today we're going to discuss invariants. Looking at the right property is important in general and in particular in mathematical problems. Sometimes we have to look at numbers, sometimes it is some equality or inequality or something else. We will see examples later. The properties that do not change after some operations or during some processes are called invariants. And double counting can be viewed as a special case, though a bit artificial. We look at some number and note that it doesn't change no matter how we count. Let's look at the following problem. There are two cups, one with coffee and another with milk. And they do the following process. We take a spoon of coffee from the first cup and add it to the cup with milk. After that, we take a spoon of a drink, of a resulting drink in the second cup, and put it back in the first cup. What is larger, the amount of milk in the cup with coffee, or the amount of coffee in the cup with milk in the second cup? So it might seem in the beginning that some serious calculations are needed. We have to count proportions, what happened after the first stage of the separation, then what happened after the second stage. Besides that, we do not need the sizes of the cup and the size of the spoon. So maybe the result depends on these parameters, so we do not know. But it turns out that no calculation is needed here, so the problem can be solved without any calculations at all. Let's look at the picture. In the left column we have what we had before the process, and in the right column represents what we have after the process. And let's observe the following. The size of the first drink is invariant. Indeed, in the beginning we take one spoon out of the first drink, and in the end, in the second part of the process, we put it back. Maybe with some milk, but still the size of the drink doesn't change. So this means that the amount of coffee that is missing in cup 1 is the same as the amount of milk we added to cup 1. So since the size of the drink didn't change, then we substituted with the coffee we removed from cup 1 by exactly the same amount of milk. But note that the coffee that is missing in cup 1 is exactly the same as the coffee that was added to cup 2. So the amount of milk that we added to cup 1 is the same as the amount of coffee we added to cup 2. Consider the following problem. There are two equally sized cups, one with coffee and another with milk. Both cups are half full. So we prefer the first cup, and also we prefer our coffee with lots of milk. We would like to have 1/3 of coffee and 2/3 of milk. And we are allowed to pour coffee and milk back and forth between two cups. And can we get our favorite coffee in our favorite cup? And the amount doesn't matter. We would like to get our favorite proportion. So in the previous problem we have discussed coffee and milk, and we have shown that if we do this process, then the amount of coffee we move from the first cup to the second cup is the same as the amount of milk we moved from the second cup to the first cup. But it doesn't help here. We would like to have the right proportion in the first cup, and it doesn't matter for us what happens in the second half. We are fine if it is mostly coffee, so it doesn't help. But yet, invariants can help here. So the problem is to find the right invariant. For this we will show the following claim. During this process, the proportion of coffee in the first cup is always greater than in the second cup. That means that in the first cup, the coffee is always stronger. Why this helps? Indeed, this inequality will be our invariant. It doesn't change, so we always have this inequality. The coffee in the first cup is stronger than the coffee in the second cup. So, on the other hand, it doesn't allow us to have more milk than coffee in the first cup. Why? Indeed, if it was the case, if we had more milk than the coffee in the first cup, then the same true for the second cup, because there the drink is contained even smaller proportion of coffee. So then in both cups we have more milk than coffee, but this is a contradiction since the total amount of coffee and milk is the same. So we if the claim is true, we cannot have more milk than coffee in the first cup, and so we cannot have 2/3 of milk there and 1/3 of coffee. So why the claim is true? Let's look at the picture. We will look at one step of the process, and we will show that if inequality is true in the beginning of the step, that is, if the coffee in the first cup is stronger in the beginning of the step, then it will be stronger after the step. So there are two possibilities of what we can do during one step. The first possibility is that we can pour some drink from the first cup to the second cup. And in this case, we take part of the drink from the first cup and we pour it into the second cup, where the proportion of milk is greater. So we milk down our coffee from the first cup in the second cup. The proportion of coffee in our drink reduces when we mix it with a part of the coffee in the second cup. Okay, for the second case, in the second case we can pour some drink from the second cup to the first cup. So let's look what happens. In our second cup we have mostly milk, and then we pour part of it into the first cup. And there the proportion of coffee is greater. So we coffee down our milk from the second cup in the first cup. So the proportion of milk decreases when we put some part of from the second cup to the first cup, and the proportion of coffee increases. So the inequality still holds. The proportion of coffee in the first cup is greater than the proportion of coffee in the second cup, and the claim follows. In the next problem, we will see how we can use invariants for counting. Consider the following problem. Bob is debugging his code, and when he starts, he has only one pending bug. But once he fixes one bug, 3 new bugs appear. After several hours, Bob fixed 15 bugs. So how many pending bugs he has at this moment? Okay, let's see what's going on with this problem. So in the beginning we have the following. Bob has fixed 0 bugs, and he has 1 bug pending. After fixing this one bug, he has 1 bug fixed. Okay, but now he has 3 pending bugs. Why? He fixed the one which was initially there, and 3 new appeared. Okay, now he fixes the second bug. Then he reduced the number of pending bugs by 1, but then 3 new bugs appeared, so we have 5 pending bugs in total. Then he fixes the next bug, and again he reduced 5 by 1, and then 3 new bugs appeared, so he has 7 bugs. Then he fixes the next one, he reduced 7 by 1, then 3 new bugs appeared, so he has 9, and so on. Okay, what we can note from this is that the number of fixed bugs and pending bugs are related. Indeed, we can observe the following formula. The number of pending bugs is equal to 1 plus the number of fixed bugs times 2. And indeed, we can see that after fixing one next bug, the number of fixed bugs is increased by 1, and the number of pending bugs is increased by 2. So this formula is true in the beginning, and then it is true after each next step. So it is true always. And this is our invariant. This equation is our invariant. It is always true. And now we can use it to compute the answer to the problem. We know that the number of fixed bugs at the point we are interested in is 15. So the number of pending bugs is 15 times 2 plus 1, which is 31. Hi, I'm Vladimir Podolsky, and today we are going to discuss termination of processes. We have used invariants before to show impossibility, and for us invariants were properties that do not change. In a more wide sense, we can call by an invariant a property that changes, but in the right way. For example, if it is a number, it might be only increasing or only decreasing, so it mostly depends on the problem you are currently considering. And another standard use of invariance is showing termination of some processes. And that's what we are going to discuss in this lesson. Consider the following problem. There is a town and there are two football teams in this town, whatever football means in your country. Each of the citizens is supporting one of the teams. And if among someone's friends there are more supporters of the other team than of his own, then this person switches to supporting another team. Each day one such person switches, exactly one. Is it possible that this process goes forever? Is it possible that people switches from supporting one team to another forever? And okay, we have a mathematical course, so we will assume here that friendship is always mutual. So if someone is friend to another person, then this another person is friend to him as well. The population of city doesn't changes, and friendship also doesn't change. So it seems natural that this process will stop. Maybe more popular team will just gather all of the fans or something like that. It seems natural. But how can we prove it formally? So how can we prove it mathematically that the process will stop? And the idea is to look at the right value, to look at the right number. Okay, we will look at the following number. Consider all friendships, all pairs of people that are friends and that are supporting opposite teams. So, and let's see what happens with this number after one day. What changes after one day? There is a person who can switch to supporting the opposite team. And when this happens, it happens then, so in this picture we represent people by circles and we represent friendship by lines. And this person on this picture switches to supporting another team if there are more friends, there are more of his friends supporting the opposite team than than the number of his friends supporting the same team. Okay, in the beginning, the edges on the right of this picture are counted. The lines on the right of this picture are counted in the number we are considering. Okay, now let's see what happens when this person switches to support the other team. Okay, now the edges on the left are counted in the number we are considering, instead of edges on the right. And note, since there are more circles on the right than on the left, then the number of edges we are counting for this person decreases. And this is all what changes during the day. So it turns out that the number we are considering, the number of friendships, such that friends support opposite teams, it always decreases. It decreases during each day. So, but it cannot decrease forever. It should be a non-negative number. So the process should stop. In the next problem, we will see that invariance can help us not only to show termination, but to show also how long does it take for the process to terminate. Consider the following problem. King Arthur has a shelf of his works consisting of 10 volumes, numbered from 1 to 10. And over the years, the shelf with these volumes, the volumes on the shelf got disordered, and Arthur hires Merlin to sort the collection. Okay, but the volumes are valuable, so he doesn't want he doesn't want more than 2 volumes to leave the shelf at once. And on the other hand, volumes are very heavy. These are large books. So it is possible to switch 2 volumes on the shelf in one day. Only 2 volumes, not more than that. And Marilyn doesn't know what is the current configuration of volumes on the shelf. So how many days Marilyn can guarantee, in how many days Marilyn can guarantee to sort all of these volumes? Okay. It turns out that it is always possible to do it in 9 days. If you can try to sort arbitrary order of arbitrary permutation of volumes, then it is always possible to do it in 9 days, and we can just act the following. On the first day, we can find the first volume and place it to its right place. So we find the first volume and we switch it to the first position. On the second day, we can do the same with the second volume. We find the second volume and we place it to the second position. Okay, let's do it. On the third day, we can find the third volume and place it to the third position. And so on and so forth. After 9 days, we will place the first 9 volumes on their places. If by any chance some volume at some day already stays at its own place, then we just save a day, and that's even better. But in the worst case, in 9 days, we will place the first 9 volumes on their positions. What is on the last position? Okay, there is only 1 volume left, it should be there. So the 10th volume is also on its own position. So 9 days is enough. Okay, now what is the minimal number of days? Is 9 minimal? Is it optimal? And another question, what is the hard permutation of books? What is the permutation of books that is hard to permute back in the right order? Okay, it might seem in the beginning that the hard permutation is then all books are positioned in the opposite order. Let's look at this permutation. Here it is, so all books, the order is just reversed. Okay, it turns out that this is not actually a hard permutation, because let's do the following. In the first day, we can pick the first and the last book and switch them. And in this way, we place both volume 1 and volume 10 in the right positions. On the second day, we'll do the same with the second and the 9th volume, and we see that we place both of them in the right positions. We can do volume 3 and volume 8 in the next day, and so on. And just 5 days is enough in this configuration. So it is not really a hard permutation of volumes. Okay, so what is the right number of days finally? So we have shown that it's possible to do it in 9 days always. We have tried to consider hard permutation. We obtained 5 days. We could do it in 5 days. So what is the right number? And more importantly, how we are going to show this is the right number. Okay, the idea is that we need to find some invariant. Invariant in a more wide sense. Invariant is a number that change, but it changes according to some rules. And the rules are the following. The number, this invariant we doesn't want it to change too fast during this process. It shouldn't change by too large value in 1 day. And on the other hand, it should change substantially while we are ordering the books. So from the beginning to the end, it should change substantially, and in 1 day it should not change too fast. And if we find such an invariant, we will show that we need a lot of days to order the books. Recall the following problem. It is very similar to the problem we had in the first course, so let's recall the following problem. There is a sequence of 10 cells, and the leftmost contains number 1, and the rightmost contains number 30. And the question was, the question problem we considered was, is it possible to fill other cells with numbers in such a way that the consecutive numbers differ by at most 3? And we showed that this is impossible, because numbers do not grow fast enough to reach 30 from 1 in just 10 cells. And this is the same idea, so we just using the same idea we used in this puzzle before. Okay, now we can name our invariant. There are several choices of it, but we will just pick one and discuss it. The invariant will be the invariant we are interested in is the number of books that stay to the right of their intended position. They stand to the right of the place they should stay. Okay, and let's check the properties. This number is small in the end. It should be 0. If all books are staying in the right position, then no books are staying to the right of the correct position. Okay, next. This number decreases slowly. It can decrease only by 1 in one day. Why? In one day we change positions of 2 books. So this number might decrease by at most 2. But note that we change position of one book. We move one book to the left and one book to the right. And if we consider the book that we move to the right, it cannot lose this property we are considering in this invariant. If it was to the right of the intended position, if we move it further to the right, it will still be to the right of the intended position. So in this invariant, in this number of books we are considering, in one day we can lose only one book. The one we move to the left. So this number decreases by at most 1 each day. Okay, so what is left? We need to show that this number is larger in the beginning. And now we need to choose the permutation of books, the ordering of books, such that this number is larger in the beginning. So how we can do it, and can we do it at all? And yes, it is possible to do it. This number can be made larger in the beginning. Just consider the following permutation. The 10th volume is on the first position, and all other volumes are just shifted one position to the right. And that's exactly what we need. Volumes from 1 to 9 are to the right of their initial position. So in the beginning this number is 9. We can reduce it by at most 1 in each day, and we should reach 0 in the end. So we need at least 9 days to do that. Hi, I'm Vladimir Podolsky, and today we are going to discuss the properties of numbers to be even or odd. Even numbers are integer numbers that are divisible by 2. And odd numbers are all other integer numbers. For example, numbers 2, 4, 6, 8, and so on are even, they are divisible by 2. And numbers 1, 3, 5, 7 are odd, they are not divisible by 2. What about number 0? Yes, 0 also is an even number. It is divisible by 2. We can divide 0 by 2 and obtain 0. It is also an integer, so 0 is even. It is also useful to look at numbers on number line. Let's position all numbers in the increasing order, all integer numbers. And let's color even numbers in green color and odd numbers in red color. Now we can see that odd and even numbers are interchanging on this line. 0 is even, then 1 is odd, then 2 is even, then 3 is odd, and so on, and the same in the reverse direction. So even and odd numbers are interchanging, and this is good to keep in mind. The properties of numbers to be even or odd are important invariants that are used very often. Let's see it on the example. Consider the following problem. We have a chessboard and a piece which can move in one move. In one move, it can move to one cell that is adjacent by edge to the current one. It can move one cell to the right, to the left, up or down. Can it return to the original position after 17 moves or after 18 moves? So there are two questions in this problem. So let's proceed to the solution, and let's start with a more simple case of 18 moves. This case is more simple because it's possible to return to the initial position in this case. And it is usually more simple to show possibility to do something than impossibility to do something. Okay, let's see how to do it. It turns out that we can return to the initial position after just 2 steps. And we can do it, for example, in this way. We can move to the right first, and then on the second step we can move back. And so we are back in the initial position after just 2 steps. And now we can just repeat it 9 times. And we will be back in the initial position after 18 moves. And note that here in this solution we used that 18 is an even number. it is divisible by 2, so we can return to the initial position in just 2 steps and then repeat a certain number of times and get to the initial position after 18 moves. So now let's proceed to the second part. The previous solution doesn't work because 17 is odd and we cannot just apply the same argument. We used that 18 is even. So now we have to do something else, and it turns out that even more, in this case, this is impossible. And let's see why. It turns out that we can make the following observation. After even number of steps, this piece is always on the white field. And after odd number of steps, it is always on the black field. Indeed, initially after 0 steps, it is on the white field. Then it moves, after first steps, the number of steps becomes odd, and the piece should move to the black cell. And then after the second step, it moves to the white cell, but now number of steps is 2, and it is even, and so on and so forth. So we can observe that this property always is satisfied, and this is our invariant. And this means that there is no way to get back after odd number of steps. Let's observe that 17 is odd again. Because after 17 number of steps, we will be on the black square, and our initial square is white. Consider the following problem. Is it possible to place signs plus and minus before numbers 1, 2, 3, and so on, and till 9, and sum the resulting numbers up in such a way that as a result, we obtain the sum 100, and the second question, can we obtain the sum 2 as a result? Okay, let's start with 100. Note that the sum of these numbers is maximal if we place signs plus everywhere. And let's do it and see what is the resultant sum in this case. Okay, let's plus signs here, and the result is 45. We can do calculation and see that it's 45. So this is the maximal possible number we can obtain. So if we place some other signs there, the sum will be even smaller, so 45 is the maximum, and we cannot obtain 100 as a result. Okay, let's now proceed to the second question. Can we get 2 as a sum of this sequence? Here is the place where we will need to consider properties of the numbers to be odd and even. Okay, is it possible to get 2? The main observation here is that in this sequence there are 5 even numbers and 5 odd numbers. And as a result, no matter how we place signs there, the sum will always be odd, because the sum of 2 odd numbers is even, sum of even and odd number is odd, and sum of 2 even numbers is even. So if you sum up 5 even numbers and 5 odd numbers, it can be seen easily that the result will be always odd, no matter how we put the signs here. And so the sum 2 is impossible. Okay, and let's also consider the more general question. So actually, what are possible sums we can get here? What are can we list all possible sums we can obtain in this placing signs in this sequence? And we have two constraints, 2 obstacles. We have shown that the sum is always odd. We cannot obtain even number as a sum. And we have also shown that the sum is at most 45. The maximal possible sum is 45. And symmetrically, if we place all signs to be minus, we obtain minus 45. So these are constraints that we have. And it turns out that this is all constraints that are present here. So all other sums are possible. So if some number satisfies both of the restrictions we have found, then it is possible to obtain it to place the signs in the right way. The sum is equal to this number, and we will not discuss it in details. But you can try to do it yourself. It is not very complicated, and to do it, you can consider the following greedy algorithm. Let's consider this sequence of numbers 1, 2, 3, and so on till 9, and let's go from right to left, and let's place signs greedily. You have your current goal number, so you have your goal number, and you have your current sum. Initially, current sum is 0. When you place some sign before a number, you add it or subtract it from your current sum. And if your current sum is less than the goal, you increase your current sum. You place the sign plus. And if the current sum is greater than the goal or equal to the goal, let's place the sign minus. So it turns out that this greedy algorithm gives you always gives you the right sequence of signs plus and minus, and it can be shown using some other invariant that we haven't considered for this problem yet. So you can try to think about it yourself. Consider the following problem. We have a table 4 by 4, and in top left corner there is a sign minus, and in all other cells there are plus signs. And in one step we can do the following. We can pick one row of this table or one column, and we can switch signs, all signs in this column or in this row. And the question is, can we after several steps obtain a table consisting of all pluses? Okay, we can try to do it, and we can see that it somehow doesn't work. So now we will try to show that it is impossible. And for this we will observe the following thing. If we try to do this, if we try to switch signs of columns and rows, we can see that the number of signs always stays odd. So let's just show that it is always the case. If a number of signs is odd in the beginning, then it will be odd all the time. And for this we should do the following. We should show that if a number of signs minuses is odd before the step, before one step, it will be odd after one step. And for this we will have to consider some row, and we will have to consider several cases. What is in this row, and we will see that the number of minuses stays odd. Okay, consider the first case. This row is filled with pluses. And by the way, the case of column is the same. So still, four cells in the column, 4 cells in the row, it's the same. So suppose there are 4 pluses in this row. So after the step, there will be 4 minuses. The number of minuses increased by 4. If it was odd, it stays odd. Okay, now consider the next case. There are 3 pluses and 1 minus. After the step, we will have 3 pluses, 3 minuses and 1 plus. So the number of minuses increased by 2. And it also stays odd. By the way, note that the case of 1 plus and 3 minuses is symmetrical. After the step, we will obtain 3 pluses and 1 minus. So the number of minuses decreased by 2 now and also stays odd. And the last case is the following. We have 2 pluses and 2 minuses. After the step, we still have 2 pluses and 2 minuses, just in different positions. So the number of minuses doesn't change at all. So indeed, after the step, the number of minuses stays odd. And so this is an invariant. It is odd in the beginning, and it is odd after each step. And so this means that we cannot switch to all pluses in the table, since if we do this, the number of minuses becomes even, equal to 0. 0 is an even number. So we cannot do it. We cannot obtain such a position. So thus we solve the problem. Let us consider now a more advanced version of the previous problem. Again, we are given a table 4 by 4. Again, there are plus and minus signs in all cells of the table. But now all 4 corners have minus signs, and all other cells have plus signs. Can now we switch this position to all signs by switching signs in rows and columns several times repeatedly? Okay, let's consider this problem. We can try to do it, and if we try to do it, we will see that this problem looks way more tricky. It still doesn't work somehow. We still can, if we try, we will not succeed. On the other hand, the previous argument doesn't work. In the previous argument, we used that the number of minuses initially is odd, and in the end we want it to be even, and it is an invariant, so we cannot do it. So, but here the number of minuses is also even in the beginning, so this invariant doesn't work. So it doesn't forbid us to obtain all pluses positions. So what can we do instead? If you know already about residues modulo 4, we will learn them later in later courses. You can try to use them, but they also doesn't help. Still, if you try to use it as an invariant, it doesn't help. It is satisfied in the end, and it is satisfied in the beginning. So, still yet, there is a very simple solution to this problem. And if you do not know it, I suggest you to think a bit more before watching further. This way you will get more from this lesson, and besides that, you enjoy a solution more if you thought about the problem in the beginning. Especially it applies to simple solutions. So now I will proceed to the solution. Okay, so we have this table, and the idea of the solution is very simple. Let's look at the smaller problem. Let's look at a small part of the current problem. And that's a very basic and natural idea, and somehow it works very good in this situation. More precisely, let's do the following. Let's consider a subtable of this table, a 2 by 2 corner, top left corner. And let's observe the following. If we switch a column or a row in the large table, we also switch a column or a row in the small table, or do nothing. So if we switch one of the two top rows in this table, then we switch a row in a small table as well, in this small subtable we are considering. If we switch one of the first 2 columns, again, we switch columns in our small subproblem we are considering now. We are ignoring everything else. If we are switching last 2 rows or last 2 columns, we just do nothing with our small subproblem. So if we make a move in a large table, we either make the same move in a small table, or we do nothing in a small table. So what does it mean? It means that if we want to solve the large problem, if we want to make all signs to be pluses in large problem, at the same time we will make all signs to be pluses in a small subproblem we are considering. And we will apply exactly the same operations. We will switch rows and columns in this small subtable. Okay, but now this 2 by 2 problem is unsolvable by the old argument. It has odd number of minuses, and if we switch a row or a column here, the number of minuses stay odd. So we cannot solve the small problem, and from it we get that we cannot solve the large problem as well. If we could solve the large problem, we could have solved a small problem as well, and this is impossible by our old argument. Okay, now let's get a glimpse beyond what we are considering. So we have noted that we have found a very powerful obstacle. We noted that if we are given such a table filled with pluses and minuses, and for it to be possible to switch to all signs to pluses, there should be even number of minuses in all 2 by 2 squares in this table. And this is a very powerful obstacle. For many tables, this this is not satisfied, and then we can immediately say that this table is not possible to. It is not possible to switch all signs in the table to get to pluses. Okay, and it turns out that these are the only obstacles. So we have found a lot of obstacles, and they are very powerful, and they are. This is a complete set of obstacles. That is, if our table satisfies all these restrictions, if for all 2 by 2 squares the number of minuses is even, then it is always possible to switch all signs to plus. You can think about this problem yourself. We will not discuss it, but you can think about it yourself. It is not it's not complicated. It's on the same level of complexity. I will give a hint in the next slide, so if you would like to think about it yourself, please stop now. So I'm switching to the hint. Let's consider the table, and let's assume that our invariant is satisfied. So all 2 by 2 squares has even number of minuses. And let's do the following. The first step, switch the first row and the first column to all pluses. This is always possible. It is not hard to do. So you can perform this. So you can perform switches or rows and columns in such a way that you obtain this position. And you do not know what is in the blank cells. And the second step, use this invariant to show that if you achieve this position, then all the rest cells are also contain pluses. So now we're done with this problem, and let's summarize what we have learned in this on this week. We have studied invariants, and we observed they are important, and they can help a lot in different problems, in a wide range of problems. And they can help to prove impossibility of something. They can also can prove to count something, and also another important application is to show that some process terminates, or even we can show with invariants that we can show bounds on the running time of some algorithms, and this is important especially for computer science. This is a very important application of invariants. Invariants can take many forms. It can be numbers. It can be properties of a number to be even or odd. It can be some equation. It can be some inequality. There are a lot of forms of invariants. The important thing is it is something that doesn't change or changes in the right way. So double counting can be viewed as a special case of an invariant. And this is not all. There are other forms of invariants we haven't discussed. For example, residues. And we will discuss some of them in the future, in the next courses.
Now we are looking at an old puzzle of more than a century old. It's called 15 puzzle. And let me explain the rules. So you have a small rectangular board, and there are 15 small pieces, small squares. And what you can do, you can move them. There is one empty space here, and you can move, if you have an empty space, you can move a piece to this space. So here are the game rules. So you can move pieces. And the goal is to reach some configuration. So for example, you start with the initial configuration, as you have seen, and you want to get the same configuration with one change. 14 and 15s are interchanged. So the question is, of course, whether it's possible or not. And if you want to do this, maybe it's more convenient to start with the configuration you want and then to get back the initial configuration. Of course, it's just like you can go back and forth. If you can get a new configuration from the first one, then you can go back and return to the standard position for the new one. So it's equivalent question. And try this. If you succeed, if you can get exchange to pieces 14 and 15, we will pay you some price. Not much, but reasonable. So would you try? let me tell you a story of this game. It's not very clear actually. It's clear that it's invented in 19th century, and there is some complicated history. I looked in Wikipedia, and you can look yourselves, but it's not very clear who invented it the first time. But what is clear that it was popular at some times, and indeed, like in our case, there were cash prizes announced in the newspaper, so a lot of people were trying to do this. And so the question is how the organizer, decided that they could do this, why they take the risk, because of course if many people will ask for a prize, they will not have enough money to pay them. So why they take this problem not seriously? Because they have a proof. At that moment, before they started this publication, there was a proof that such a thing is not possible. And so, okay, maybe you believe that our proof is incorrect, so you still can try to get your prize, but at least it's not that easy. And for now, our challenge is to reinvent this proof. So we want to understand what is the proof of possibility, and in this way, we will develop some small part of group theory, like about permutation group, as mathematicians say, but forget about this mathematical words, but just want to solve the puzzle. Now we want to actually generalize the question, as usually in mathematics, if you cannot solve a simple question, not a simplest formulated question, you try to find a more general one, and then you think about this more general one, and then you come back with new knowledge, and then you solve the original one. This is the scheme. So we will try it for our puzzle. So first observation is another view of the game. So you can think that this cell, which is empty cell, is filled by the neighbor. But let's look in the other way. Empty cell is now active. So empty cell moves in some way, and when it moves, it exchanges the place with the neighbor. So every move is now an exchange of an empty cell and the cell which moved. So you may imagine that empty cell is, say, 0. So you have now not from 1 to 15, but from 0 to 15, and at every step you exchange 2 pieces. Okay, what the matter? Why it's better? And it's better because we can now consider a more general question. Instead of forget about pieces, about this board, we have just n object in n positions and places. And we want to permute them. A permutation is you want to move one thing in the place of another, and so you want to somehow do in new order, put them. And what you are allowed to do is pair exchange. And in mathematics it's called transpositions. So what you are not allowed to take all the objects away and then put it back in a different ordering. What you are allowed to do is just to exchange 2 of them. And this is called transposition. For example, if you want, there are four letters S, T, or P, and you want to get from stop, you want to come to spot. And of course, one transposition is enough. You just exchange T and P, and that's all. But if you have a more complicated thing, you want to get post, then more transpositions are needed. So we will see later, but you should try yourself and count how many of them is needed. And if you are afraid of permutations, this is a video which should convince you that it's a very simple thing. Even a cat can deal with permutations quite efficiently. Okay, just kidding, but it's a really nice video. You should try it independently of the permutations. And now our main thing is a classification of permutations. So they can be even or odd. This is 2 classes. And let me explain what does it mean. So first, let's see some examples. So if you want to make stop to spot, then you should make one permutation is enough. But of course, you can make also 3 permutations. Just after this one useful, you can put twice do some permutation, or just repeat the same permutation 3 times or so on. So you can make 3 or 5 or 7 or whatever you want. But it's not so clear whether you can get any other number, but at least these are possible. And if you want to get post, it's not possible to do in one permutation because all the letters are in wrong places, so you need to move all of them. So if you try, you can see that 3 is enough, and then you can make 5, 7, and so on. But again, 2 is not enough, and it's not 4 is not clear how to use 4 permutations together. Try it, and you will see that there is some reason. By some reason, it doesn't happen. But if you say not post by pots, then 2 permutations are enough, and you can also use 4, 6, and so on. So let's see how to make 2. So stop. What you do, first you put, very easy. You exchange S and P, and then you exchange T and O. So you can make 2 permutations, and then you can make redundant ones. So the general observation, if you can make n, then you can make n plus 2, because twice permutation is nothing. Okay, and conjecture, which will be a theorem, is that permutation are of 2 types. Some of them require, like here, require like here, they require an odd number of permutation, and this is an odd permutation, but this permutation, so it's odd, and this permutation is even. You need always even number of transpositions. You need even number of transpositions here and odd number of transpositions here. So this is a conjecture. And before proving it, let me try to cheat. Let me show you a counterexample, and you will probably see where I'm cheating. So look, here we want to make, from totem, we want to make motet. Why not? And here we do this with 1 permutation. We exchange this T and M. And here we do the same thing with 2 permutation. We exchange this T and M, and now we exchange this T and M. So we achieve the same motet with 1 permutation and also with 2 permutations. So what do we have? An even permutation with 1 transposition and 2 transposition. So the question is whether we have even permutation or odd permutation. How it's possible? Our classification says that it's not possible. So what is the problem here? So let me tell you the answer. And the answer is that there are actually 2 letters T. So if we see that this is T1 and T2, then here we have T1 and T2 here. And here, if we look here, then this is T1, this is T2, and then here is T1, and this is T2. So we get not the same motet, but we have actually these 2 motets are different by 1 transposition, exchanging this and this. So everything now is cleared. It's not really a counterexample. So now the theorem, let us say it seriously. Each permutation can be obtained by a sequence of transposition. In mathematician will say it's a product of transposition, but just can be obtained by a sequence of transposition. And the number of transposition in the sequence is somehow predetermined partially. So some permutations can be obtained only by even number, while other can be obtained only by odd number. So there are 2 cases and they do not mix. And this is the theorem. Now let's prove the easy part. The easy part is that every permutation can be obtained by transposition. So you can always get whatever you want with transpositions. And this is very easy, and probably you have seen in our example what we should do. We should just place the letters, or not the letters, whatever we want to place. We should place them one by one. So first we see what should be in this place and find the letter and make a transposition. Then here we have a correct thing. Then we look at the next place, find whatever should be there and make a next transposition and so on. So let's see how it works. Imagine, we already have seen this, but let me repeat it slowly. So imagine we want to convert stop to post. So at the first place, we need this P. So what do? We take stop and exchange P and the letter which is currently in the first place. So we get ptos. And now P is in the correct position, but the toss is not good. So we need to have O. So what we do, we exchange O and T, which is currently there. So this should be exchanged. We have pots. And now the rest, T is not in the, there should be S here, and here is T. So we should replace them and get in one step, we get the final answer. And actually you can think if we have n letters, we have n, not n, but n minus 1 step. N minus 1 because the last letter is automatically in the right place if the previous are in the right places. Okay, the easy part is now done and we have to switch to difficult part. Okay, so we show that even is not odd, of course not the numbers, just the even permutation cannot be at the same time odd permutation. That's our claim. And let's start with a special case. It's actually a rather general situation. So there is a theorem, there is some special case. And then we see that the special case is in fact equivalent to the theorem. So if we know the theorem for the special case, we can easily get the theorem in the general case. So in our proof, we will repeat this trick twice, but let's start with the first one. So this special case is the case of identity permutation. So identity permutation is just everything is correct, nothing should be done. So it can be obtained by 0 permutation, and 0 is an even number. So if we believe in our theorem, we will know that the identity permutation can be obtained by odd number transpositions. And actually, the general case can be reduced to the special case. So if we believe in the special case, then the general case is also true. Why? Imagine we believe in the special case, let's prove in the general case. So we have we have the same permutation from A to B, but we have two ways to get it. In this way, we have an even number of steps, and in this chain, we have an odd number of steps. So you see that I have drawn the arrow in the other direction. So of course, we can just, if we can come from A to B, then in the same number of steps, we can come from B to A. And now probably you see what we will do. So what we will do. So we go back and forth. We go from A to B in this way, and we go from B to A in this way. And then we return to A, of course. So we get the identity permutation. But what the number of steps? What about the number of steps? We made first the even number of steps and then the odd number of steps. So even plus odd is odd. So you see that we started from A, we made even plus odd number of transpositions, and then we get A back, which is not possible if we believe in our special case statement. So we have shown that it's enough to prove the theorem in the special case. Then in the general case, it's also true. So what remains is to prove the theorem for this special case. Okay, how do we do this? And then we look at the more special case, the special case. And this special case is transpositions of neighbors. For that, we should imagine that our objects are on a line. Of course, for the theorem, it doesn't matter. You can imagine whatever you want. Just any position will work. So we can put them on a line. And then if they are on a line, there is a notion of neighbors. When we exchange the letters which are which have no letter in between. So these are neighbors. And this special case is just that identity permutation cannot be obtained after an odd number of neighbor transposition. So this is a special case. Let's see why it's true. It's very simple actually, because we can classify all the transposition according to the pair of letters which is involved in them. So for every pair, what happens? So that we have some pair of letters, then maybe they move somehow, but at some point they are involved in the neighbor transposition. Both letters of the pair are involved. So we just change them. And then the order is changed. What was left is now right. And then they move somehow maybe, and then they come back and they go in an original position. So after each transposition of this pair, the order is changed, and the transposition of other pairs, other neighbor pairs, do not matter for that. So each transposition of these pairs change the order, and in other pairs the order remains the same. So for each, we should return to original order in each pair. For that we need an even number of steps. So the total number is even the sum of even numbers, so it's even. Okay, so this special case is proven. And now we should reduce special case to special case. So how can we do this? And imagine we have a transposition of non-neighbors like this. So we want to exchange A and B. And there are some K letters in between. So how can we do this? First, we should move B to the left. So we exchange B here, then we exchange B is now there, we move it again, and so on. So B should cross all the intermediate letters, and for that we need K steps. And then B and A should change the places, as here, and then, because we want B is now in the right place, but A is not, and A should go back, so it makes K steps back, and after that we achieved what we wanted, because here this intermediate part, I don't know, X, this intermediate part is now here. Here we have X, and then because A just jumps over X, and so the X is just moved one position, and then it moves back. So no, and these parts, of course, are unchanged. So after 2k plus 1 steps, we get the transposition of non-neighbor letters. So I think, yeah. So we have 2k plus 1 neighbor transpositions to make one non-neighbor transposition. But what is important, that if we are interested if we distinguish only even number and odd numbers, then this 2k is not important, because it's just an even number of steps. So from the viewpoint of even and odd numbers, we can believe that we made one transposition plus some even number, which doesn't matter for us. So non-neighbor transposition is somehow the same as neighbor one, just some additional even number of steps, which doesn't influence our statement. And here is written, mathematicians say it's 1 modulo 2, and we will speak about this modular arithmetic in the part about number theory. But now you should just distinguish between even and odd numbers. That's enough for now. So we are done. We reduced the neighbor case to neighbor. We reduced the general case of transpositions of identity permutation to the neighbor case, and in the neighbor case we know the proof. And we reduce the general statement about the arbitrary permutation into a statement for identity permutation. So there is a chain of reductions, of 2 reductions, and now we are done completely. Where we are. So what do we know and what we do not know? So we started with the 15th puzzle, and we wanted to prove that one cannot exchange 14 and 15. And for that, we developed some theory about permutations, transpositions, but this theory has nothing to do with our puzzle. We even have some general classification. There are even permutations, odd permutations, but what is the connection with the puzzle? Not clear. So we need some last step to get the result about the puzzle. Now we apply the general theory of permutation. As mathematicians call it symmetric group, but it's a very simple part of the theory. So we apply this theory to show that our mission to exchange 14 and 15 was impossible. Okay, why? Why cannot we exchange 14 and 15? Because we need to make even and odd number of steps at the same time. So first, we know that from the general theory, we know that each move is a transposition of empty cell and neighbor So if we want to make our odd permutation, one exchanges an odd permutation because it's one transposition, so we need to make an odd number of moves. This is one part of the argument. And for some different reason, we'll prove that we require an even number of moves to exchange 14 and 15 and come back to the original position. Why? Do you see why? This chessboard thing is important. How does it help? So let's look at the empty cell. Now it's not important what are the numbers, just look on the empty cell. And at each step, empty cell moves. And each move changes its color. If it was black, it becomes white, and so on. And after our the entire thing, the empty cell should be at the original place. So it should switch from white to black, to white to black, to blah, 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 and return to white. So it needs to make an even number of moves. Bringing it back requires an even number of moves. So this is the reason why we need an even number. And for permutation theory tells us that we need an odd number. So this is not even number cannot be odd, and we get the contradiction. So we can make suggest to pay you $1,000 without any risk to lose money. Now we come to a programming assignment, which is just to classify a given permutation. So how it looks from the programmer's viewpoint. So permutation can be just instead of letters, it's easier to deal with numbers. So imagine we have n numbers, 1, 2, 3, 4, n. And they are in some array in arbitrary order. They are permuted. And the question is whether this permutation is even or odd. And you should return 0 and 1, for example. No, 0 is an even number, so it's more natural to use it for even permutation. How will you do this? One of the possible approaches, not the most effective one, but still easy and rather effective. Probably you have taken a programming course, and maybe you have seen a problem when a permutation was obtained by a sequence of transposition. Do you remember something like this? Sorting is the answer. So when we want to sort an array, initially the array is some random order, and we need to bring it to the normal order, and many sorting algorithms use permutation for that. Not all. There are some more advanced algorithms like merge sort or whatever, but many of them use permutations, use transpositions, exchanges. So at each step you exchange two elements of the array. And if the sorting algorithm uses exchanges, it can be used to find whether permutation is odd or even. Just counting, you count the number of exchanges and you see whether it's odd or even. And we even have a piece of code. But let me tell you that there is an intentional error here. So you should be careful to understand where the error is. But let me explain what is happening. So this is the array given to us. We want to sort it. And this is an additional variable which is not in the original sorting algorithm. It's just a number of transposition modeled with 0 or 1. It flips back and forth. So how do we, there is a simple algorithm of sorting. We put first element in the right place from left to right. So we put first a minimal element in the first place, then the second element in the second place, and so on. So here is how you write this algorithm. So there is some variable s which counts how many elements are at the right places. Initially there are no of them. And at the end we want to have n elements. So while s is less than n, we continue doing things. So we can even, so s elements are already okay, and this is the rest. So you start with s plus 1, you put u here, and also t here. And now a of t is minimal element among the rest, because not among the rest, not among this part between s plus 1 and u, because it's only one element. And then the idea is you move u, you increase u, and always you keep a of t minimal among this element. So you increase u, and there is a new element, last one, which is not checked. And if this last one is smaller than the current minimum, then we need to move the current minimum in a different place. And after u is equal to n, here u is equal to n, so a of t is minimal among all the rest. And then it's what remains to do is to exchange this minimal element, somewhere here is minimal element t, and you exchange it with u and get one more element in the right place. And you here as additional operation, we keep track of whether we make an even or odd number of exchanges. Okay, so it looks very convincing, but do you see the error? There is maybe there are some unintentional errors, but there is one intentional error in this program. Can you see it? Okay, you can try it for some examples, and then you will see the problem. Actually, you will see that the answer doesn't depend on the array for some reason, and then you can think what is the reason and how to correct the thing. What is wrong with this code? You should find, and you should find how to correct it. There are some additional questions, natural questions you can think about. So first question is the running time of this algorithm. So we sort the array, but how many steps we need to do? From probably you think you thought about this while considering sorting algorithms, and it's O of n squared. It's proportional to n squared because there are two nested loops, and one you go from 1 to n, and the other one you go first from 2 to n, then from 3 to n, and so on. So it's more precisely, it's like n squared over 2 iterations approximately. But anyway, it's proportional to n squared. Not very good. And there are better sorting algorithms, and you can use one of them to get better algorithm for also for our problem. But something even better is possible. There exists an algorithm where number of steps is proportional to n. And okay, let me tell you the idea. If you want to think, stop the video now. But the idea is that there is a permutation. So you trace where the element moves. So if this element moves to this place and this element moves to that place and so on, you look, there is a chain of elements until you come to the back to the original place. This is what is called a cycle. And this permutation can be split into cycles, and only the number of cycles and the length of cycles is important for finding whether the permutation is even or odd. And this splitting into cycles can be done in an O of n steps. So this is a faster algorithm without sorting. What remains to do if you want to complete your investigation of 15th puzzle is to look at the reverse question. So we know that if the permutation is odd, then you cannot obtain this. But also it's actually necessary and sufficient, as mathematicians say. So if the permutation in a puzzle, if you read the permutation in a normal way and it's even, then the puzzle is solvable. This is some new statement. We did not prove this, and it's more complicated thing. But it's true, and the algorithmic counterpart of this statement is that you should write a program that decides whether the puzzle is solvable, and if it's solvable, this program provides the sequence of moves needed to solve it, and for each move how to encode this sequence, how to output this sequence. It's very easy. There are many ways, but the simplest one probably, you just write the number of a piece that is moving at a given step. So you just write the sequence of numbers, which shows which piece are moving on the first, second, third, and so on steps. So this is a task, and if you are ambitious, you can try it to write this program. Let me try to give a short, not that short, hint for the last problem, how to show that every even permutation is possible in the game. We already know that every possible permutation is even, but now we want to prove that the reverse statement, that we can achieve every even permutation. And this is a mathematical account, and then it should be translated to programming side. So you should write a program using this proof. This is a standard situation. You have mathematical proof and you need to implement it. Anyway, first we start with some mathematics, which is not related to this game, puzzle, which is just the general things from group theory. So let me tell you what is the 3 cycle. So 2 cycle is transposition. So 2 cycle we have A and B, and we want A to go to the place of B and B to go to the place of A. This is transposition. And then you can get what is 3 cycle. It's just we have A, B, and C. And A should go here, B should go here, and C should go here. So it's a 3 cycle. So is it even or odd? That's the question, first question. And then it's easy to check that it's even. We know how to check this because we just need to present it as a sequence of transpositions. So first you want put A here, B here, and C here. So first you make a transposition with A and B. So after that you have here you have A and here you have B. So A is in the right place, A should be here. But B and C are in the wrong place, B should be here and C here. So the second transposition is needed to exchange B and C. So it's an even permutation. So this is our first step. The second step is that every even permutation can be obtained by 3 cycles. So we know that if we make several 3 cycles, then we have an even permutation because each of them is a sequence of even number of transpositions. So in total we have also even thing. But now we want to show the reverse statement, that every even permutation can be obtained in this way. It's rather easy. We should recall how we did this for 2 cycles. For 2 cycles, we just placed a right thing here, then the right thing here, then the right thing here, and each can be done with a permutation. And now, if we want to place something, in the right place, then we cannot do a transposition. We need to do a 3 cycle. So we need some temporary location, and so we make this 3 cycle, and this is what we need. The problem is that at the end, we don't have temporary location. So if we here everything except the last thing is correct, then we no more are able to do this. But then we have only two things, and so they can be either in the order we want or in the reverse order. But if they were in the reverse order, then the entire one more transposition is needed, and this is impossible because both our goal, our permutation which we want to get, and our current permutation are even, so they cannot differ by one transposition. So automatically we get to last thing in the correct order. Before we had the last thing in the correct place, but now we have 2 last things in the correct order. So every even permutation can be obtained by 3 cycles. Okay, so this is about general things about permutations. Now we return to our game, and there are two observations about this game. So the first observation is that at least some 3 cycles are very easy. So we have the board, and there is a special 3 cycle which is very easy to obtain. So imagine we have this red things. We have here, it's 10, I think it's 11, yeah, 11, 12, and here is 15. So this 3 cycle is easy to obtain. So we can get in this place, we can get 11 here, 12 here, and 15 here. No, and of course, you see how you do this. You just need to make one step, a rotation in this direction, and then you will, 550 is going here. No, first you move 12, then you move 11, then you move 15, then you move this, and everything is okay. So at one 3 cycle is possible. So let's a special 3 cycle. Or if you repeat this twice, you get 3 cycle in the other direction, but it's okay in both cases. Okay, so the question is how to obtain every arbitrary 3 cycle if we know how to get this one this special one. And then we need a next step is that every 3 pieces can be placed into this red zone. So no, I make some symbolic things. So if we take any 3 places in the rest, of course, there are not so many possibilities, but if we have any 3 places in the rest, you can, and you want to put them there in the red zone, it's always possible. If for each of them you know where you want to put it in the red zone, and this is possible without any restriction on other pieces. So other pieces can go wherever they want. You just look at this 3. Now, actually, if you played 10 minutes in this game, you know that it's easy. The problems start when you are close to the end. If you need put only 3 pieces, it's just trivial. But of course, we need some proof, and this proof unfortunately requires some case analysis. So imagine we want to put this piece here. Then how can we do it? First, we can put it to the left side. If we put the empty piece somewhere, and then we make a rotation along a cycle. So we move this piece until it goes. Now it's already on the left side, but if it were somewhere, we can just put it there. Then we can make a rotation along this line and put it here. And then after that, we make rotation in this cycle and put it there. So in this way, we can put it here. So now this thing is in the correct place, and then we need to put other 2 not touching this one. So you should not make any changes here, but you should make cycles like, okay, if you have, I don't know which one. If you have, for example, this one, and you want to put there, you can move it first out of this, then move it here, and then bring here, and so on. It's not difficult. So every 3 pieces can be placed in the red zone. But maybe now you are confused why we do all this, because first we do something in the red zone, and there is another completely different story how to put 3 pieces in the red zone. But now there is the most important part of the argument is some trick from group theory. So imagine we want to make, let me show it like this, symbolically. So imagine we want to make some cycle. First, we make some S sequence of 3 cycles, and put the sequence, not of 3 cycles, sorry, sequence of moves in the game, and these 3 pieces are placed in the red zone. So these 3 pieces go somewhere, I don't know, like this, this, and this. Then what we do, we make the cycle in the red zone. So in the red zone we make a cycle. Oops, it's not the red zone, okay. So we make cycle here. So it goes here, and it goes here, and this goes here. So this is the cycle, red cycle, which is, we know it's easy. And now what we do, this is the most important step. What we do the reverse. So we do the same movements as in S, but in other directions. So they usually is denoted by S minus 1. So we put things here, and now these three things go back. So this one goes here. Okay, this one goes here. This one goes here, and this one goes here. So what have we achieved in this way? If you see that these three things are moved in the red zone, then cycle is made there, and then they are brought back. So we achieved the cycle we want. And all other pieces here, they are moved somehow. They are not untouched. They are moved some in an unknown place. But then here we don't move them. So here on the second stage, they remain in the same place. So on the third stage, they will go back exactly where they were initially. So we get any three cycle, we get a three cycle here, and all other pieces are on the same places. So we obtained every three, so we conclude that every three cycle is possible according to game rule. And now we know that every permutation is a combination of three cycles, and every even permutation is a combination of three cycles, and every three cycle is possible. So these two things show that every even permutation is possible. So this is the proof. The only thing which it remains to do is to implement this in terms of a program, and it's a bit complicated because here it's easy, and as mathematicians we can make hand waving and say that look, it's easy, blah blah blah. But as programmers we need to consider all the cases carefully and not miss any case. So you should be very careful in this second part. And then the other things are less complicated. And final remark, that there is another problem which shouldn't be mixed with this. When you are asked to provide the shortest path, so you need to provide a minimal sequence of moves which gives the desired permutation. This is much more difficult problem. It's required a lot of memory and some tricks to optimize them, so it's not that easy, and it's another story completely. What we did is only the existence proof, so we prove that some path exists, and therefore there is also some shortest path, but we have no tools to find the shortest path up to now. Okay, so sorry for this was kind of since it's a most complicated thing. I tried to explain it fast and didn't make slides, so but it's more challenging probably to follow this. So, but I hope that's more or less clear.